Hello, and welcome to a Grasshopper course for beginners. I'll start with a little bit of an intro first. From my experience in teaching, ideally learning Grasshopper is done in two waves. First, controlled and structured learning, where you gain technical knowledge about how the tools work and also you figure out what kind of a mindset one should have when operating these computational design tools. And the second wave, you learn by making. You learn while making, while doing things. You begin a project and you struggle. At every step there are things that you don't know and that you need to figure out. You Google them, you search for them on YouTube, for tutorials on YouTube, and you figure them out, right? And you push forward. And once the project is finished, you have learned those things. And then you start another project and continue on. The aim of this video is to get you over the first wave. I will build up enough of a knowledge for you, and a knowledge foundation, I guess, for you, to be able to do simple parametric models on your own. The course will be divided into chapters so that if you'll need a refresher, you can easily just check out some of them here. All of them here. Cut! A portion of this video is sponsored by PCBWay. Hey, we all design stuff. But when it comes to making things that we have designed, not all of us have a literal factory at our homes. This is where PCBWay comes in. They offer 3D printing, even in metal, CNC milling, even in metal, sheet metal bending, as well as injection molding services. You just send in your files, you get the price, you approve the price, your stuff gets made and sent back to you. Great service. Link in the video description below. Back to the video. Okay, course chapters. Chapter list. If you struggle, find a chapter that you struggle with, watch it again. Easy. I'm not sure why I'm struggling with explaining this concept to you. Anyway, we move on. There are virtually no prior knowledge requirements for this course. Of course, I do expect you to have basic understanding of Rhino, but when it comes to Grasshopper, we'll start from scratch. Rhino for Beginners course, by the way, is in the video description below. While I'm at it, all scripts, models, and drawings that I've produced in this channel, with this video included, of course, can be downloaded by the Patreon supporters. Also, link in the video description below. You'll be able to follow along without these files, of course, but it's a nice thing to have in case you get stuck somewhere. And one last thing before we begin, the mindset. I think it's extremely important not to think about Grasshopper as this typical design tool. For example, if you're working on a design of a teacup, with Grasshopper, you're not designing the 3D shape of the teacup, but rather you're designing a system, a set of rules, a set of logic of how this 3D shape should be constructed, should be made in the first place. The shape itself is simply just an output of the system that you design. Was that good? A better analogy. A car, you're not designing the car, you're actually designing a factory that builds the car. And then if you change a parameter within this factory, right, a single parameter, it can build then a different type of a car, right? Parameters, parametric modeling. Hopefully it's beginning to connect. Okay, enough blah, blah, blah. I'll save some for the outro. By then you'll get what I mean. For now, let's jump right into it. All right, let's begin. Let's begin at the beginning. So first of all, I guess, how do you start Grasshopper in the first place? So of course, as with everything in Rhino, there are two ways. There's a tool, a tool icon, Launch Grasshopper, that's available in the standard tab right here. Or there's a command. So you can just simply type in Grasshopper and it's going to launch it. For you, if it's your first time launching Grasshopper, it's first of all going to take a little bit longer, and second of all, you will be presented with this Getting Started with Grasshopper window. once you have launched it. These are just simply tutorials by the developers to, give you a very basic understanding of how Grasshopper works. After you have finished this course, this video, you can check these ones out as well as for a refresher. If you're completely new to Grasshopper, I suggest not unticking this Show Tutorial Browser when Grasshopper starts tick mark, keeping it ticked just so that you always have access to these tutorials. For now, we will have this closed. All right. So now, once this is loaded in, once Grasshopper is loaded in, what you see is an empty screen, empty Grasshopper screen with 9 3x3 icons, I guess, in the bottom center of your screen. So those icons are previously used files. I believe, if I remember correctly, if there are no files used, then these icons will be the tutorial files for using Grasshopper, but once you will begin working on your own scripts, on your own definitions, those will appear here. The ones that are available will be green. The ones that you have deleted or moved will appear red, right? So that's just color coding. For now, we will, of course, ignore this. Then simply just going through the menu to explain like different clusters of the menu. You have the typical program, file, edit, view, display, solution, blah, blah, blah. You have the typical tab here, ribbon, I guess, here. And then under it, you have a bunch of tabs that correspond to different types of tools. Like in Rhino, you have standard, C-planes tab, set view tab, display, select, viewport layout, visibility, and so on. All of these tabs, which change the tools that are available for you. So it's almost like modes in which you work. In Grasshopper, it's kind of similar, right? You have your mathematics tab, so all of the math formulas and so on are here. You have your, let's say, surface tab. Everything that has to do with surface manipulation or surface creation is here. Intersections tab, anything that has to do with intersection of, let's say, two geometries, all of that math logic is here, and so on. So different tools, different tabs. You will immediately notice that in your case, you have much less tabs than I do, and that's simply because Grasshopper has an insane amount of add-ons, an insane amount of plugins that are made by the community, and it's great. It enhances the program itself quite far beyond the reach of how the vanilla software what the vanilla software can do. But in this case, we will mostly be working with the base base Grasshopper tools, and we will only be delving into some of these plugins at later stages of this course. For a beginner course, I think learning too many plugins will be overwhelming. Right. So that's the general idea of this kind of UI logic, is that you have this ribbon with the tools inside of it. And of course, there are different ways of how you can create tools, which I will cover in just a few minutes. And for me to continue explaining the UI, what we need to do is we actually need to create a node. We need to make a single function inside of Grasshopper, just so that we can actually save a document, right? Save the Grasshopper file. Grasshopper files are saved separately, but I'll talk about that in just a second. Let's go to the Maths tab here, Maths, and let's click on this addition node right here. Click, right? And you might see, shall I do it again? I'll do it again. I click once on the plus sign here, the icon with the plus sign, and I click once anywhere on the screen. And thus I place the node. Nodes are functions. In this case, this function takes two numbers and gives you an addition result. So 10 plus 5 is 15. We'll talk about that much more a little bit later. So now when at least one node has been placed, this has been converted into this whole Grasshopper file. It has been converted into an actual Grasshopper file, which we can save. So now if I go to File, save document is not grayed out, I can choose to save document, and I can save it, for instance, simply into my desktop, and I can call it my first file, right? My first file. And you can see I already have two files, lamp and shelf Grasshopper files on my desktop here. So if I hit save, that's it. Now this particular function has been saved and I can access it anytime I want. I can also go to File, New Document, File, Save Document, and I can save this as my second file. Hit save. And now I have created two files. So the question is, how do I now go back to my previous file, right? Do I need to open it, or is it still open? And the answer is everything is still open, right? So here on the top right corner, where you see your file name, in this case, my second file, if I click on it, there's also my first file, right? Which I can select. And now I just jump into the first file that we have created with the node, right? So Grasshopper can run multiple files at the same time, right? It can, at least it can have them opened at the same time. That's an important thing to know and to understand. Typically Grasshopper auto-saves after every node place. So when you place a function or a node, I'll keep calling them nodes, Grasshopper saves your file. Great. For auto-saving purposes, for crashing, this is excellent. It's also very lightweight, so the auto-saving does not really destroy performance. Okay, let's move on. Let's move on to this actual node and what it does, what's the reason behind it. Okay, so nodes. As I mentioned before, nodes are basically functions. Grasshopper calls Rhino, the functionality that you already have within Rhino as a function, and can do stuff with that functionality, with those functions, right? So in this case, it's just simply adding two numbers together to give you a result. If you don't see it in this view, if the node appears different, then you can fix it by simply going to Display tab here in the top. And these three, or these two, draw icons and draw full names. Draw icons should be turned off. Draw full names should be turned on. Let me just show you what happens if I turn on draw icons. Now the name of the node has been replaced by an icon. And if I turn off draw full names, the result output, the name for the output, has been shortened to R. This is very useful when you want to make a physically compact script, but it's really bad for readability of beginners. So instead we go for display, draw icons turned off, display, draw full names turned on. Tells you what it does, tells you what's what, right? As I already mentioned, A is input, B is input, result is output. You always construct a script in Grasshopper, with a few exceptions, but 99.9% of the time, from left to right, meaning you have some numbers here. I can actually show you. Let's follow along. Let's go to Parameters tab, and let's select this panel tool right here. Click, the orange one, right? Double click the panel tool and type in 10. Don't hit enter, simply click anywhere else on the screen. If you hit enter, it's going to, actually I can show you. Let's make one more panel. Click, double click, and let's do 22. And this time hit enter. You can see that when I hit enter, it jumps to a second line, and that second line will be empty. So this is going to be, I think now there are, let's click outside, let's see if it's going to complain or not. No, it's not, okay. So there are already kind of checks involved that eliminate the spacebar or the empty line that we have created by accidentally hitting enter. But previously, this would have made this node complain. In this case, it doesn't, so we're kind of happy. But just in case, I'm going to delete that break, that new line, so that we have just 10 and 22. If I hover my mouse over the top right corner or any corner of the panel, I can shrink it, right? Of course, I forgot to mention, apologies, scroll wheel zooms in, zooms out. Right click and holding pans the view. There's no rotating. With the left click and dragging, you can select multiple nodes, right? Now with panel 10, if I drag out from the right-hand side corner or right-hand side output of panel 10, click and drag, you can see this wire appear while I'm holding the mouse button, of course, and I can select where I want to plug it in. So I can just take it and plug it in into input A. For panel 22, I can plug it in into input B. And we have our now addition node adding up these two numbers, and the result is spitting out a number for us. If I grab one more panel here, connect, result to the panel, now we have the number 32 being sped out. A very simple function, but hopefully helps you understand the flow, the data flow that's happening here. Of course, if I now double click on any of the panels and I type in, instead of 10, 63.128, hit OK. Now I get the output here, 85.128, right? So it's real time, like it updates real time, of course. Okay, so that's that. In terms of like different types of nodes, I guess, there are different ways of how we can look at it. First one being, if I zoom in to this node right here, you can see that this in particular has a possibility to increase the amount of inputs, right? So there's A, B, and I can click this plus sign here, plus icon here, and now there is C. So I can create one more panel, 88, and I can plug in the, one more input to the addition node. Not all nodes have that, but most of the nodes that deal with addition, subtraction, multiplication, that deals with lists of items, they usually have a possibility to increase the amount of inputs or outputs that they have. If you have some sort of a node that is creating just a line between 2 points, for instance, then of course, since it's creating a single line between 2 points, you can't have 3 points, for that node, right? So it's just keep in mind that some nodes you can change the amount of inputs and outputs, right? And I have noticed, by the way, when working with Rhino 8 in particular and Grasshopper, that there have been made quite a few changes to how nodes react to weird stuff that you're trying to do. Before, they would break much quicker. Now they kind of just ignore you. Example would be if I were to just double click here in the panel, and instead of number 22, we would use a number called cat or something like that. You can see that it kind of just ignores you, right? And as if it's not even connected. Before, this would just throw an error and this wouldn't work. I believe if we were to just create, let's create some geometry, and I'll explain what happens when you connect a cat to the geometry. So if I were to go to curve tab right here, under primitives, let's find one that says circle, C and R. Oh, by the way, I forgot to mention, if you click on any of these tabs right here, vector, curve, surface, right? So under curve, if you click on this primitive sub tab, then not a bunch, but all of the tools in the sub tab show for you. That's the same thing as clicking this little triangle here next to, let's say, the surface tool. Oop. Brings you to all of the tools that are surface related in Rhino, right? So back here under primitive, circle CNR, click on that, get it in here. Basically creates a circle around the center point, around the normal point, around radius, with a certain radius, and that's it, right? So to give it a center point, we can actually, it's waiting for us to give it a point, but instead of actually giving it a point, I can just lie a little bit and grab a panel. So params tab, panel. By the way, shortcuts. Let's start talking about shortcuts. If you double click anywhere on the screen, you can type in what you want. Panel, right? Gives you a panel. Addition, gives you addition. CNR, circle CNR, center normal radius, gives you that. So in this case, panel, enter. Much faster than trying to fish out the nodes from here. And we just simply double click here, and for the center, I can just type in XYZ coordinates of the point. 0, 0, 0. Hopefully it makes sense, right? So if it doesn't, let me just really quickly explain. If I look into the perspective tab, not tab, viewport, 0, 0, 0 is located, it's the origin of the world, right? It's located where the X and Y axis meet, right? So 0, 0, 0 is actually right here. That's the point, right? That's where it is. And at least those are the coordinates of the point. So what here we're saying is, and that's all the point is, by the way, in the language of Grasshopper, or generally speaking, in programming, it's just a set of 3 numbers, basically a location. That's all point has, because it's a 0-dimensional thing. Anyway, so if I connect the panel to the center, bam, automatically this node becomes light gray, right? Before, if I control and disconnect, oh yeah, if you hold down the control key, I believe in Mac it's going to be the command key, and you drag backwards, so from center, you can see if I hover my mouse, it changes the icon. You drag backwards into the panel, it disconnects. So you will see that the node in this case was orange. Why was it? It was orange because basically if a node is orange, it's a warning that the node is not generating any outputs, or that it's generating only partial outputs. In this case, this node was not generating a circle, that because it didn't know where to generate the circle, and because of that, it was orange. If I were to zoom in, or I don't really need to zoom in the top right corner of the node, you can see this little balloon here, icon here. Well, note icon here. If I click it, you can see you can see why it's orange. If it's complaining, it tells you why. Sometimes it's readable, sometimes you don't understand what it wants from you, even when you read it here. Input parameter center failed to collect data. In this case, it's pretty straightforward. Center, no data, no circle. Give it the data, yes, circle. Zoom, 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 zoom. Circle appears here in the middle of our world. The question is why? Because normal and radius are not, we are not giving it anything, right? So how does it know what's the radius of the circle? How does it know what's the normal? Normal, by the way, is a 90-degree vector or direction from a plane. So if you have some sort of a book thing, right? A normal of this surface would be this, right? 90 degrees. That's the normal. Important concept is being used a lot in Grasshopper, not just in Grasshopper, generally speaking, is being used a lot. So why does it manage, and in this case, by the way, it's using normal to understand the rotation of the circle, how is it rotated in the world. So if I hover my mouse over normal, you can see that it says one locally defined value, 0, 0, 1. So in X, the vector has 0 strength. In Y, the vector has 0 strength. In Z, the vector has strength of 1, meaning that by default, normal is already predefined, right? And it has the vector Z, right? It's upwards. And that's why in this case, the circle appears flat. If I hover my mouse over the radius, you can see that the radius of the circle is set to 1 by default, right? So this is 1 unit. And of course I'll keep creating panels, honestly. If I create another panel and I say 1, 0, 0, that's a vector going in the X direction, you know, aligning with the X direction. And if I connect that to the normal, the camera doesn't rotate properly, but you get the idea, right? Now this is the normal direction for this circle. If I give it a panel with a radius of 11, now it's a much bigger circle with a radius of 11 actually. So now if I change the radius to cat, the node turns red. Red node doesn't mean a warning, oh, nothing is being pushed out, you know, no geometry is being generated. No, it means you just literally gave me like a cat instead of a radius. You know, that kind of an error where never is this going to work. Unless it's like solution exception index out of range, you will see that a lot and then you cry. Anyway, that's later. So now if I click on this error sign here, data conversion failed from text to number. Always, if there is an error, always read the error. It's going to help you a lot to troubleshoot. So in this case, data conversion, you know, translating the data from text, which is, you know, I have a guess which input is text, to number, you know. Radius wants a number, we give it a cat, doesn't know what to do with the cat. We give it a number again, is happy again, right? So a node can be white, a node can be orange when it's a warning, a node can be red when it's a error, critical error, and the node can be dark gray. You still haven't seen the dark gray node. A node is dark gray when, well, actually, sorry, node can be gray and node can be very gray. Okay, I'll explain it. So a node can be gray when the preview of it is disabled, when you can't see it in Rhino. So if I select this node and I right click on its name, here I have the preview option, right? Which I can just click on. And now the node, if I just click anywhere else, the node is gray. If I select the node, right click on it and click on enabled and click anywhere else, the node is very gray. This means that the computer does not calculate this node at all. It's ignored by the computer. So it's disabled. Disabling a node and hiding the node are two completely different things. Because if this circle is hidden, I can still use it in further operations. For example, don't do this, but just as an example, if I want to then take the circle and move it along a z vector with a slider, you know, ignore these, but just to clarify, the circle still exists because we take it and we move it now along the z vector, right? With a given number. If this circle was disabled, this would be an orange this becomes an orange line, meaning that there is no data going through this line, and this move node doesn't have anything to move, right? So it stops working. It still gives a transform information, so it's not orange, but it doesn't get the circle. So let's enable this, and let's click on preview as well. Let's preview this. There is another menu that you can access that helps you with this. So if I select the circle and I click a scroll wheel, the middle button, the scroll wheel button, if you click it, then you have enable preview here, disable preview here at 2 o'clock, around 2 o'clock or 1:30, right? And then at 3 o'clock, you have enable or disable. And there's of course more options here that I will teach you how to use in just an hour or so, honestly. Okay, so that's that. That's with the nodes. Let's move on. So another important thing that I should note is that you can have multiple things connected to one input. You can. So addition is kind of boring, isn't it? Let's just delete it. You can just select all of them and just hit delete button, or backspace also works. And you can click or you can drag around, select all of the nodes and drag them around like so, place them wherever you want. And in this case, let's say I want to make 2 circles, right? Technically, I could select all of them here, like this arrangement here, Control C, copy, Control C, Control V, paste, and drag it to the side. And now this is my second circle where I can change, let's say, the center position of it to be 10, 0, 0, right? So one circle is created around 0, 0, 0 point, the other one is created around 10, 0, 0 point, and the radius of the circle is like 5 or whatever, right? So I have two circles. Sure, I could do that, but that becomes a little bit annoying to keep track of. So instead, for this example, I will create, I deleted it by the way, I will create one more panel here, double click, and I'll type in 10, 0, 0, click, a point at 10, 0, 0, and now I will connect the second panel into the center. And you can see that as I connect the new panel, the old one gets disconnected. If I connect the old one, the new one gets disconnected, and so on. Doesn't work. But if I hold the Shift key, click and drag and connect and release the Shift key. If I do that, then I can connect 2 wires. Great. Honestly, later, just for the sake of pedagogy, it's better to use one node in between here called merge. So double click, merge, like that. Panel goes into data 1, panel goes into data 2, and then result comes into center. And you can see I just really automatically clicked on this minus sign here, just so, because I don't need the third input. So I just release or reduce the third input. It really doesn't matter. You can have it. Anyway, this is exactly the same thing as taking, with the Shift key, as connecting the 2 panels into the center mark, except that in this case, with the merge, you know which one comes first. So which circle later, these are 2 circles that are generated now, right? And if I were to create a panel here and I were to look at it, like so, you can see, 2 circles are being generated. So with merge, I know that the first circle in the list, this circle, is actually at 10, 0, 0 coordinate. And second circle in the list is at 0, 0, 0 coordinate, right? If I were to disconnect and connect them this way, Control to disconnect, by the way, Control and drag backwards to disconnect. So if I connect them other way around, now the first circle in the list, or first circle in this list is at 0, 0, 0, and the second circle in the list is at 10, 0, 0. So I know which one comes in first, which one comes in second. If I just simply use the shift key to connect, to center, visually, I can't tell, right? I go off to make some coffee or whatever. I come back, I watch my my definition here, and I don't know which circle is which. So of course there are ways of how you can figure it out, but just generally speaking, the merge command, when you need to plug in multiple things into one input, is very, very useful. So keep that in mind. Okay. Now, what if you want to actually not type in the coordinates here, but you want to have a point somewhere in Rhino, a point in Rhino that around which this circle is created? How do you link Rhino and Grasshopper? Well, first of all, let's get rid of these two coordinates. And instead, what we need to do is we need to create an empty point container, which we will fill in with a point from Rhino. So empty point containers, or empty containers for that matter, I'm going to cover them much more in depth in the next chapter, but empty point containers are container is located under parameters tab, geometry, the first one in the list, point. You can also double click and type in point to see it here. It's a black hexagon icon. All empty containers are black hexagon icons. What I mean by empty container, and I selected it by the way, what I mean by empty container is that it does not do anything. It just holds geometry, right? So it's not a function. Circle CNR, for example, creates a circle. Addition adds two numbers together. Point holds a point. That's it. References a point, right? But for what we want to do, it's excellent. So this is going to be like a bridge. Then in Rhino, we need to actually create a point. There, it's done. Then how do you take this point and connect it here? Well, for the point container, you right click on it and you choose set one point. And you then click on the point that you have created. Pop. And that's it. Now you can see if I select this object here, this node here, it turns red. This is not red. What do you mean? It turns green. If I select this point component here, it turns green in Rhino, meaning that these are linked. And now if I just simply connect my point component to the center input here, it is going to create a circle around the point, and I can move it, right? Wherever I move the point, the circle moves. Can I have 2 points? I'll answer by having 5 points. Well, 5 extra points. I will right click on this point component here, and I'll choose to clear the values. So I break the bridge, clear values. Then I select or I right click on this point component again, and I choose to set multiple points. Not one point, multiple points. And I just simply drag around all of these. It's going to give you this kind of weird zigzag. It basically just tells you, this is going to be the first one, the second one, the third one, fourth, fifth, sixth in the list. That's fine. We don't care. We hit enter. And now 6 points generate 6 circles. It's weird that they're vertical, so I'm going to change it from 100 to 001. So Z, vertical. If the perpendicular vector is vertical, or if the normal vector is vertical, that means the circles will be flat. It's always 90 degrees, like that. Right. So now we have a bunch of points. and a bunch of circles created up around the points. I forgot to mention that if you select a node, it's going to show that geometry, that the node has, that the node generates in green, right? If you don't select the node, it's going to be this red color. So for instance, circles not selected, the node is not selected right now. They're all brownish reddish color. And then if I select it, it turns green. Unselect, brownish reddish again. Okay, so that's how you reference stuff into Grasshopper. How do you get it from Grasshopper back into Rhino? Because you should, right? So in this case, the circles that are generated, let's get them back into Rhino, right? Right now, I can't operate, I can't select the circles in Rhino, I can't do anything with them in Rhino because they only exist as part of the system in Grasshopper, right? We need to manufacture them, to bake them. So if I right click on the circle output here, and I choose to bake right here, egg, it's going to ask me what's the layer into which I bake, and would I like to group them up. Everything else is whatever. If I would like to group them up. So yes, please, I would like to group them up. I would like to bake them into the default layer, and I just hit OK. Boop. And now now they have been baked, by the way. I can select them and I can move them wherever I want, right? I have my circles in Rhino. And you will notice that, sure, I baked them out, I got them into Rhino, but they still exist in Grasshopper. And that's because, yet again, Grasshopper is not a 3D design tool. It's a 3D design system. It's a system tool for 3D design, meaning that now I can change the panels to, to the radius panel to 6. I can bake this again with radius of 6, right? So you basically are just freezing the output, you're freezing the system and you're outputting the current state of the system, right? Back into Rhino. Any geometry that has been baked in Rhino will not automatically update if you update your Grasshopper file, right? So most of the time you have, you only work within Grasshopper, and only at the last step do you bake it into Rhino to actually, produce drawings or whatever, or manufacturing, the detailization, not the documentation for manufacturing in Rhino, right? So that's baking. A shortcut to bake is the insert key on your keyboards. That bakes in not grouped geometry, but it bakes immediately to any active layer that you have. So insert key in your keyboards, usually located above the delete key. Also, to bake something, you can click the scroll wheel. Hovering above a node, just click the scroll wheel, and at 4:30 o'clock in the radial menu, you'll see the bake tool right here. Okay. What else? I think that's about it. That's about it with the basic user interface. I guess I can just simply show you a few little tips and tricks. So the first one is under display, under canvas widgets, you can click on this profiler. The profiler will, okay, it doesn't show anything. 1 second. If I extrude, okay, there we go. So I had to give it a little bit of a heavier task. So in this case, extruding the circles and the z-axis, unit z, along the z-axis. And you can see it says 6 milliseconds. So under display canvas widgets, the profiler calculates how long does each node take, right? How long does it take to calculate? And it's a very, very good way to see if you have some nodes that are just destroying the performance and to troubleshoot. This is going to come in handy, of course, much later. So that's the first thing that I wanted to show. Don't forget, even though the auto-saving does indeed work and it's great, but don't forget to file, save, document, have it saved. The points that are currently referenced, right, from Rhino file, if you open up this Grasshopper file without the Rhino file present, this will complain because it won't be able to find the points that it should reference. So of course the Rhino file should come together, with Grasshopper file. So I will go to File, Save As, Desktop. I'll just call it my first file RH for Rhino. Hit save. Alternatively, if you don't want to save the Rhino file and you just want the points to actually be, hard coded in or to live inside of this node, you can actually right click on the node, on the point node, and you can choose internalize data, which will break the link between the points that you have here and the points here, but it's going to basically save the data from here in this node, right? So let me show you. Right now I still have the points here, but if I right click, internalize data, I can now select these points, simply delete them, don't need them, just have all of them deleted, and this still works, right? And now if I select this, by the way, it gives me the option to still move the points, but now they are completely within Grasshopper. As long as you're internalizing points or curves, it's fine, but keep in mind that you can really slow down the system if you internalize too much, right? So I would strongly suggest simply having a Rhino file paired with Grasshopper file, and Grasshopper just simply references geometry from the Rhino file rather than having it internalized. Okay? Okay. There's a scribble tool, this pencil thing here where you can draw stuff. Hit accept. That really doesn't matter. It's very useful for when you need to write down notes when you're explaining things, and I'm sure I will be using it, but just for the general design, purposes, doesn't really, is not really necessary. For teaching, for sure. Okay, enough blabbing. Let's move on. Let's move on to talking about what kind of data types we have. All right, let's talk about containers then, and about referencing or geometry types, I guess, within the containers, these empty geometry containers. And I say geometry containers because that's what we will be focusing on. The purpose of this chapter is just to give you an understanding of what kind of node. In this case, we created the point node, but there are more, clearly, there are much more nodes that you can use to reference things. What kind of nodes should be used to reference things? So a very, very easy answer to it is just go here to the geometry tab, parameters tab, geometry subtab, and find the geometry node, black hexagon icon. Place that, and this node can reference literally any 3D geometry or any geometry that you have in Rhino. Let me just place a point, place a line, place a polyline, a curve perhaps, a box, a surface. What else? Let's create a mesh, or rather let's create a sub-D shape. Like that. Let's create a mesh, mesh. Sphere, whatever. Okay, so we have all of these geometries. I'm not sure why the curve just went down, whatever. We have all of these geometries. I can select all of these geometries, right click on the geometry node, choose set multiple geometries, and it literally can just reference all of them. So this is like foolproof way of how to get Rhino geometry in Grasshopper without really thinking about it. The clear drawback is that now you have a node here that has a crap ton of different types of geometry, so you will need to be filtering it out somehow, because now I can't really use this node for the circle. Is going to complain like crazy, right? It does give me output a circle on the point. It does so, sure, but then everything else, it just throws me error, you know, null, null, null. Null is basically error. Null, 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 right? And this is never a good thing to later deal with, all of these nulls in the list, right? So while geometry node is very, very powerful, in terms of just getting geometry in here referenced without really thinking about it, it's also messy. So how do you make it cleaner? Well, you need to use a type of geometry. You need to specify what's the type of geometry. And there are five main ones. Type number one, we already covered this, point. I'll just double click, type in point. We need to get used to typing point, right? And clearly, you know, if I right click, set multiple points and drag around all of this, only single point gets selected right here, right? Then for under geometry tab, I can find curve. So this is 0 dimensions, 0 D. Okay, Scribble is a useful little tool here where I can just write 0D like that. It's basically for note taking, and curve is one-dimensional object, meaning that point does not have any dimensions, curve has a length. So out of these, what has a length? This straight line segment, this jagged line segment, and this curved line segment. Line segment. All of these, right click, set multiple curves, are curves. So I noticed that students tend to think that curve component can only hold curving things, you know, things that are swoopy, curved, but not really, no, not at all. It can hold polylines, it can hold line segments. Curve component deals with one-dimensional objects, such as curves. Then you have this box and you have the surface. A surface is a two-dimensional object and a box is a three-dimensional object. For a surface, you could use a surface tool, or surface node, right? Right click, set one surface, bam, it's here. Or you could use, and actually that is a 2D. thing. It has a length and a width, but you can see that I'm kind of putting surface here a little bit lower and making room here for one of the other main ones, which is a BREP, BREP, boundary representation. If I hit enter here, BREP can be both a surface and a polysurface, a box or whatever, a sphere. A sphere is a surface, a duck that's shaped, like a Nurbs geometry that's shaped like a duck or whatever, right? So BREP is basically, you can think of it as polysurface that can also be made out of a single surface. Right click, set multiple BREPs. Oh, sorry, I should select both of these. Set multiple BREPs, and now we have, you know, both of these referenced by a BREP. So while surface is kind of a part of it, part of a BREP. So a BREP can be 2D as well as 3D geometry, right? So it can contain surfaces, but it can also contain enclosed volumetric objects, as long as it's Nurbs. All of the Nurbs stuff, all of the polysurface stuff is BREP. Okay, moving on. Two more. We have a mesh and we have sub-D. Well, that's what we're gonna use. Mesh. Black hexagons, don't forget. Oh, actually, I want to experiment. If I select sub-D, can I reference it as a mesh? No, that's a no. I can only reference the sphere. And then for sub-D, you also use black hexagon icon for the sub-D. You reference that as well. Okay. So now we have 1, 2, 3, 4, 5 main ones, and the Nurbs geometry has like a sub component that's surface. If you want to specifically only reference in two-dimensional objects without referencing in three-dimensional ones, right? So, and I guess I should also say like that. Geometry can be anything, right? So this is like the mindset that you should have when you're referencing in stuff. What's the dimension and what's the type? Because you have NURBS, you have meshes, and you have sub-Ds, right? Of course, there are components, there are much more components here, like point clouds, and you have fields and block instances, and you have primitives such as booleans and integers. Not all of them are used for referencing geometry in the first place. Some of them are just containers that can hold geometry. For example, here we have the point component, and I can just simply say, well, actually, pop. Point component goes into an empty point container, and now this point container also has 6 points, right? So there are instances where this is useful, this kind of methodology is useful. So that's why we have containers for literally anything, any type of data that you can have in Rhino, in Grasshopper, both actually, both in Rhino and Grasshopper. I guess the daddy of this geometry node would be data node under primitive data. Because if I right click, maybe I can't, wait. Set, no, it won't let me, okay. I thought that it's also going to let me to reference in literally everything in Rhino, but it doesn't. But I can do this. I can take the geometry node and I can literally connect it to the data node, and it doesn't care. It's just going to parse through the information, so it has the capacity to hold everything that the geometry node does. And also, cat with the shift key. And if I were to check not just the geometry, but also textual information, right? So the data node is actually able to hold even more stuff like numbers and text and so on, fields. So this is like the overall, the umbrella node that can be used for, referencing. Well, not referencing, you don't use it for referencing as I showed you, but that can hold literally everything that these can and even more. Okay, I think we're starting to scratch a little bit too deep right now. I'm actually going to keep this. We're starting to scratch a little bit too deep, so I will stop here, and hopefully, that this should be enough. All right, and while we're still on the topic of data, and not data management, but just generally data that you can work with in Grasshopper, I think it's important to also cover this input sub-tab right here. So this is what kind of input data can you generate in Grasshopper to later use. So at this point in time, we already know the panel, right? We have used the panel here to input numbers. We have also used, in some examples, I have also used the panel to input text, right? So panel is useful for text and numbers, and also honestly, panel is quite useful for checking what kind of data is generated by different nodes. You just hook up a panel to, for instance, the output of the circle CNR, and you get a list of circles. So you know that it's 6 circles that have been generated by this circle CNR node. A shortcut to creating a panel is if you double click anywhere on the screen, on Grasshopper screen, and you type in // 2 slashes, then that generates, or that suggests a panel. That's a shortcut, right? // Also, panels can have, if I were to type in dog, cat, mouse, 1, 2, 3, like that. If I were to right click and untick this multi-line data option, a panel can hold a list of things as well. But I will cover this in much more depth in later stages of this course. So for now, just think text and think numbers. And also, of course, 3 numbers corresponds to either a position or a vector. So it can go a little bit, how do you say, a little bit more complex than just simply text and numbers. Moving on, here you can see under the input subtab, you can see a number slider. If I select this and I place it here, right, a number slider is basically, it always generates a number, right? And you can slide it, that's the number slider, from left to right, and you can adjust the number, right? In this case, by default, the number slider generates a number between 0 and 1, and you can choose whichever you want. If I were to delete this panel for the radius of the circles, and I were to connect the number slider here, I will need to zoom into this. You can see that as I change the number slider's input, the circles, change in radius, of course, right? How do you control the number slider? Well, if you wanted to generate a larger number than 1, well, you right click on it anywhere, you click on edit, and here you access the options for the number slider, right? So the first one being the name, I can call this radius of circles, right? And it's going to, I'll just hit OK to show you, it's going to change the name of the number slider. For clarity purposes, this is quite useful, especially if you tend to forget, what different number sliders are controlling. You can give them names. I strongly suggest you do so. It's a overlooked feature, but definitely a useful one. Then here we have an expression. An expression is basically, you could say x times 100, right? Like that. Hit OK. And now you can see that that whole range between 0 and 1 has been multiplied by 100. So you can bake in a mathematical function. Let's go back here. You can bake in a mathematical function that takes a number that you have in the number slider and multiplies it by, in this case, by 100, but you can also do a square root of it and so on, right? In this case, I will keep the expression empty. Grip style, shape and text, usually we just do that. We have shape and text. If you just choose to choose shape, it doesn't show you the actual number that you're getting. So we usually want the little dot as well as the number, just to give us as much information as possible. So shape and text. Then, before I go for the accuracy, let's look into the numeric domain. This is the range. This is how far the slider can go, right? So what I can do is I can say, well, between 0 and, let's say, 100, right? So I can change this to 100. You just double click on it. Hit OK. And now I have a slider that goes between 0 and 100. Easy peasy. Edit. You can also, of course, the minimum can be minus 100. I wonder how that would work. Yeah, it just inverts. That's fine, right? So now it's between minus 100 and 100. Edit. Now, of course, numeric value is the current value that is set, and you can adjust it to any value you want. If you want to be accurate, you double click on it and you type in, 50. And now it's going to be set exactly at 50. Double clicking this, well, I'll show you, but that is also how you can set a precise value. And then we have the rounding. So usually you have either a floating point number, that means a bunch of digits after the comma, it has accuracy, and you can choose how many digits after the comma does it have, like that. So that's the accuracy, or you use integer number. So it's full numbers, right? It has no digits after the comma. For this kind of application, I do want to have digits. So I do want to have a float number. So I'm choosing that with 2 digits after the comma, hit OK. And now it's set to 50, right? With a certain accuracy attached to it. I can also, as I mentioned before, if I double click on the range here, I can type in whatever, 25. I can type in whatever number I want, right? So if you want an accurate, some sort of accurate number and you don't want to wiggle the mouse too much, then you can adjust it this way. Of course, a number slider can be enlarged, right? To give you a more granular, movement, I guess. Right? More accurate movement. Now on to shortcuts that we can use with the number sliders. So if you just double click anywhere on the screen and you type in the number 50, hit enter. You immediately get a number slider, right? That is set to 50. And the range of it is going to be between 0 and 100, because 50 fits quite well between 0 and 100. It automatically guesses what's the range that you want. If I were to type in, double click, type in 50.50 or 5123, let's do this. So 4 digits after the comma, enter. Then it generates a slider with that amount of precision with the same range between 100 and 0, right? So, for instance, if I were to do a slider 101, then suddenly my range will be between 0 and 1000. It tries to guess what kind of range you want. If I were to type in 9, slider with 9, that's going to be between 0 and 10, right? So how do we pre-describe the range while we're generating a slider? That's quite easy, actually. I will double click and I'll type in, first you type in the minimum range. What's in this case, we're dealing with radius of circle. So what's the smallest radius that you want to have? Let's say 6, right? Then I type in ... 6 ... Then I type in the actual number that I want. Let's say 25 ... again. And now the maximum. 55. So the full syntax is 6.25.55. Minimum is 6, maximum is 55. The actual value that we will get currently is 25. I hit enter and that's what I get. A slider set at 25 between 6 and 55. I can connect it to the radius, like so. So that's the slider input, and now you know everything that I know about sliders. Okay, moving on. Besides sliders and panels, you also have like multiple different instances, I guess, or not instances, apologies. You have multiple possibilities of how you can input different types of data, or rather how you can manipulate data. And these are most of them you learn about once you really need to learn about them. But I will cover 4 more really quickly, and then all the rest we will cover once we actually need them. Because calendar or clock, I don't think in 10 years I have ever used the clock in Grasshopper. Anyway, Boolean toggle. This bad boy right here. This is true or false statement toggle, where if I were to / panel, if I were to hook up a panel to it, it just gives me false or true statement. Meaning it's quite useful if you have certain nodes that are asking you, for instance, polyline. The polyline node, right, asks you for a bunch of points. Since we have points here, I can show you. So I'm going to really quickly, actually, I'll just borrow those, Control-C, Control-V. So these 6 points right here, I'm borrowing them, and I'm connecting them to the vertices. Vertices and points are virtually the same thing, right? So I'm connecting them, and it draws this polyline for me. Let me hide the circles real quick. To hide them, I right-click, I click on preview, or unclick preview, right? Disable preview. So I have 6 points, and it draws a polyline through those 6 points. But here I have this Boolean, which asks me, is the polyline closed or not? Should I, connect the last segment between the last point and the first point? And here, let me just grab this like that. If I connect this as true, it creates the segment. If I connect this as false, it doesn't create a segment. So this is a way, and of course you don't need a panel for this. The panel just shows, there we go. So this is a very useful thing that you can, use to generate, or not to generate, but to input yes or no statement. Another way of how you can do it, like true or false in Grasshopper, is literally either 0 or 1. So if I just do //1, enter, it automatically generates a panel that has 1 in it, and I can connect that to closed, and now it reads this as true. If I change this to 0, it reads this as false. If I use 3 or 325, it's true. Anything other than 0 is considered to be true. 0 is considered to be the false statement. So technically you could also use a panel for that. Let me just check one thing. Okay, that's true. And if I type in false, okay. So you can literally just write in the panel as well, true or false. Then we have this button. Button is basically the same thing as Boolean toggle, but it works in a little bit different way. If I just connect the button to here, you can see that it's always false, except for when you click it. Or I should click and hold so that you can see. If I'm clicking and holding my mouse button, it's set to true. At any other given time when I'm not clicking and holding, it's set to false. So false, click, true, release, false. This is very useful for nodes that need a special trigger to run. In the future, especially in simulations, you will see those kind of nodes. For now, we just know that it exists and we skip over it. Okay, moving on. We have our control knob, which is basically this the same kind of a slider thing, except that you can just keep rotating it, right, until you reach the number that you want. And of course you can edit it, and there are exactly the same ranges and minimum maximum ranges and so on that you have in this number slider. You have the same thing in the control knob. I have noticed that some people tend to use the control knob. I personally never do, so I will not talk about it as much. Just know that it's an alternative, just like we have the number slider, we have the control knob, I guess. And the last one is digit scroller. If I plug this in here, you can see that it's at 0.25, and I can just make adjustments to the digits like so. Cute, quite useless in my opinion. If I can't even edit this. That's weird. But I guess, the useful thing is that you can choose which digit do you adjust at which given time. But whatever. Number slider is where it's at, and Boolean toggle is where it's at, so you should focus much more on those as you're learning the basics of Grasshopper. So those are the main inputs. Of course there's more, and you can use a color swatch, right? So for this polyline, if I were to use some sort of a custom preview, you don't need to follow along with this, and I give it a color swatch as its material. Now the polyline is drawn as white, and I can click on the color and I can adjust it to be drawn in any color I want. So that's of course there are much more inputs than just simply numbers, but for creating numbers or toggles, but for creating geometry, usually you just use sliders, or panels. So I will be skipping over these, and I will be revisiting them once we actually need them. Okay, and I think that is, just give me a second. Yes, I think that is it with the data types and the inputs and the what kind of data does Grasshopper use, and we move on to the next chapter. All right, let's do some basic operations now. So I will be deleting all of this in Rhino, just so that it's not in the way. And I will be keeping these guys right here, just so that, if we need to, we can look at them, back at them. I will just group them up. Oh, I should probably mention how do you group things. So if you select a group of data, right? A group of nodes, just like that. And you click your scroll wheel, the middle button. At 12 o'clock, here you will see the group option. If you select this group option, it's going to draw a group or this rectangle around your objects. Then you can, if you just click anywhere on the rectangle and you drag it, you're dragging all of the objects together. The nice thing about it is that you can right click on this group, anywhere on this rectangle, and you can name it. So I can name this data types hierarchy. That's not how you write hierarchy, but it is what it is, right? Or is it? I'm not sure. So data types hierarchy. I can also right click and I can choose that the outline should not be a bounding box, but rather should be a blob outline, right? For more organic definitions, I guess. In this case, I will be using a box outline. We use groups quite a lot to just color code and differentiate different parts of the definition of the Grasshopper script just to make things easier for us. Speaking of colors, if you right click on the group, you can choose to color and you can choose whichever color you want, right? So I will do this, right click, color, drag it over here, or rather this should be white as well, because it all belongs to the same chapter. So the first chapter will be white, like that. And then I will just select all of these and group them up all together, right? So now I have the large group here, and I have like subgroups inside of my large group. Quite a useful thing, right? Moving on, let's select everything in our Grasshopper script. Click the scroll wheel anywhere, middle mouse button, and choose to disable preview. This inherently will just hide literally everything that was selected, so you don't see it. Just helps. Okay, and now we can move on to not regular, but basic operations or simple operations. We'll start with non-geometrical ones, where I just explain, I guess at this point you already kind of get the sense of it, but this is just to lock it down. Under math, I will just explain a few operators here and how they work and how we can how we can operate with them. So somewhere on the right hand side, let's create a slider that is going to be, just double click, that is going to be between 5 ... 32 ... 50, right? 5 ... 32 ... 50. So minimum 5, maximum 50, currently set to 32. Let's create another slider that's, or actually we can just borrow this one. So I'm just going to select it, Control C, Control V, make a copy of it and maybe change the slider to somewhere closer to 20, something like that. I can add them up by either going to operators here and choosing addition, or I can just double click anywhere on the screen and just use the plus sign, right, for addition, like that. Connect these two, and let's create a sphere, right? So this, let's say this is our mathematical kind of equation for calculating the radius of the sphere. So then I can go to Surface, tab, go to Primitive, Sphere. You can also, of course, just type in sphere and choose that one, right? Both work. asks me for a base. By default, the base is set to the world XY 000 position. And it asks me for the radius. So I connect the result as the radius, right? And I have myself a sphere. And of course, now if I change the radius of it, if I change either one of the sliders, the sphere radius changes. Super simple, works exactly as how you would think. And this really showcases left to right, flow of within Grasshopper. So let's say we have this addition here. Back in the math, there are of course multiple operations that we can do, that we can use. For example, I can divide it, so division. I can divide it by a number, let's say 5 times less, right? And now we are adding up these two numbers, then we are dividing them. I can show you with panels, so // to create a panel. 31 plus 19 is 50, divided by 5 is 10, and I have a sphere with radius of 10, right? Then I can also take it and I can produce, apologies, give me a second. I can raise it to the power of 2, for example, so I can get the power of 2 of 10, which would be 100. And so on, right? There's like multiple mathematical formulas that we can get from this. If you're really into it, you can also, where was it? Give me a second. Was it under utilities? No. Trigonometry? No. Scripting? Evaluate expression, there we go. You can also write an expression, right? Which, if you really want a heavy mathematical formula, you can write an expression here. I would suggest not to, honestly, because it can be, x plus y divided by z in brackets, x and y in brackets, like that. Of course, x, y, and I need one more variable that I change this to z, I believe. I'll just name this y, name this x, like that. Invalid name, only use on full. What? It's not, okay, anyway. And then if I connect these, this should work. Yeah, it does work. And then I get the same result. I don't know why it was giving me an error. I think just plugging in different values triggered the recalculation of the node. So now it's happy. And now I can use, this mathematical equation instead of these two nodes, right? Which does exactly the same thing. So I see a lot of people use this, but I personally prefer to, honestly, I prefer to use this instead. This just for me, I don't know why, but for me, that flow of what happens after what, first we add, then we divide, then we get the radius, much more clearer than trying to read a complex function. But it is there, the possibility is there, right? So I'm just grouping it up. That's the non-geometrical kind of simple operation that I wanted to show you. And now for a geometrical one, let's do a easy, simple one. I select all of these, I click the scroll wheel, I choose to disable preview, I also group them, right? So this is a simple operation, non-geometric, or math. Let's just call it math, right? Then for something a little bit more geometrical, let's just get, one second, I'm just really quickly thinking. Let's just get some points in here. So in Rhino, apologies. So I'll just grab 2 points in Rhino right here. the gap between them doesn't matter. I'll just put them into Grasshopper. So I create a point component, point container. You already know this. Right click on it, set multiple points. And as long as I have these 2 points selected, it already will put them in. If I didn't have these points selected in Rhino, then it would minimize Grasshopper and I would actually need to select them, hit enter, and then we would be at the same page. Okay, so I have these 2 points. Let's say, one second. I want to create a line between them. How do I do that? Well, the logic is that you go, okay, a line is a one-dimensional object. It's a curve. So I go to the curve tab. Okay, that's it. First step. Second step is, okay, it's not going to be an analysis. I'm not analyzing anything. I need to create a thing. So it's going to be a primitive, right? Either a spline or a primitive, honestly. So I choose primitives. And here, just looking through the icons, I see this, create a line between 2 points. You know, there's 2 points shown and a line. I have 2 points. Great. So I used it. I can also, of course, type in line and just find it. It's super useful when you hover your mouse over a node, over any, apologies, any icons, to just read the description of what those nodes do. Create a line between 2 points. Great, that's exactly what I want, right? So this node right here asks me for a start point and an end point. But hey, there's a problem. And the problem is that here I have 2 points in one node, and here I need 2 separate inputs. And I can't really do this. You know, it doesn't work, doesn't create a line. That's because there are, now if I plug it in like so, since there are 2 points here, there are 2 start points and exactly same 2 end points. So the line between 2 points node does not know what to do, or rather it creates 2 line segments that are 0 in length, but it doesn't matter, right? You want 1 start point, 1 end point. So we need to, I'm holding the control key, by the way, to separate this. We need to somehow separate this list of 2 points into separate outputs, right? Into point A and point B output. And technically you might be thinking, oh yeah, you could just do this, right? Set 1 point, right? And now I have 1 point here, 1 point here, and this would work indeed, right? But usually what you want is you want to have the least amount of reference nodes that you can, because simply re-referencing stuff is very annoying. So in this case, we have 2 points in one node, and we just need to separate them in Grasshopper, right? The way you do it is with a list item. I will be covering lists in, I believe, the next chapter, something like that. But for now, all you need to understand is we have a list of 2 points, and if I use list item node right here, and I connect my points to the list, then by default, the list item will spit out the first item on the list. Because by default, the index is set to be 0. And these numbers here on the left-hand side that you can see in the list, those are indexes. Basically the number at which position in the list does the geometry exist, right? So in this case, by default, index is 0 here, meaning that it reads, you know, the first point from this list and it spits it out. And I can use that as my start point. The question is, how do I get the second point? You know, how do I get index 1? Well, I could create another, like, I could just do this, index 1, right? And that would give me the second point on the list. But a much faster way is just to scroll into this list item node and to click on this plus sign here, insert parameter. And you can see it says +1, right? So if my index here is 0, right, and spits out the first item, then +1 means that it adds 1 to 0. So this is index 1, which is the second item in the list. And we have our endpoint. So this is how you separate out a list, right? Now, as I have my my line here, right? I can choose what I want to do with it, right? So for example, I can create a pipe, right? I just double click and type in pipe. I can also go in here. Where was it? Curve? No, sorry. Pipe is a surface. Under primitives, I believe. That is not under primitives. Utilities. Oh no, please don't start struggling. No, 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 no. Okay, under freeform, pipe exists. Right? Asks me for a curve. A line is a curve, a type of a curve. Connect that. Immediately gives me the pipe here, which I can zoom into. A radius, that's going to be a slider. Let's say 2.22.222. Enter. A slider between 2 and 222. Connect that to the radius. There we go. There's our pipe that I can control. Basically makes a cylinder, right? And then for the caps, you can see if I hover over the input of the caps, it has suggestions. It has a suggestion of what kind of inputs you could have. If you give it a 0, it says none. No caps will be created. If you give it a 1, a number 1, it's going to create flat end caps. If you give it a 2, it's going to create round end caps. So since this is like a value that I will not be changing that much, I will be creating a panel with a number. Let's say I want flat caps, or let's be fancy. Let's do round end caps. Those are, by the way, very heavy. So be careful when you have a lot of curves in the future, but I will do it. So I just do // 2, because 2 was round end caps, right? Like that. Connect that. And now I have this pill looking thing, right? If I change this panel now from 2 to 1, it gives me the flat end caps. If I changed it to 0, it gives me empty, no end caps. Side note, side note, a Nurbs pipe tool is the heaviest way of how you can create a pipe. I will talk about this a little bit more later, but the multi-pipe tool is the fastest, I would say. Or mesh pipe, but mesh pipe tends to become messy. So multi-pipe tool is what you want if you have like a huge network of curves. Multi-pipe, this bad boy right here. As you can see, much more settings, much more inputs, but gives you a much more controlled sub-D geometry. Not Nurbs, sub-D, but sub-D can be converted into Nurbs very, very easily. Okay, so that's that. Now let me show you exactly the same thing. Let's group this up and hide it. And let me show you exactly the same thing, but with more than 2 points. Because right now what we have is we have 2 points, we create a straight line and we pipe it. But what if you want multiple points? I already kind of showed it here with 6 points and a polyline that's that's being created through those 6 points, but I will show it again in a much more controlled or pedagogical way. So I will be reusing these 2 guys right here, but I will also be adding a third one, or maybe 4. Let's do 4. So 4 points in total. I will double click, type in point, get a container in here, right click on it, set multiple points, and then I will not just drag over all of them all together. I will very meticulously select which one is first, second, third, and fourth, because that is how it's going to be read when it tries to draw a line through them, right? Hit enter. And then now through these, I can draw a polyline. That's easy, right? But the polyline tends to be quite naughty when it comes down to piping. Actually, I kind of want to check it out, how it's going to work. So I'm going to Control C, Control V, copy paste the pipe tool, connect polyline to the pipe tool, check it out, and you can see that, you know, when it has a pretty sharp turn with a large radius, it tends to crap the bed, as they say. And if I increase it even further, it breaks all together, right? So that's an issue. So for now, I'm deleting that. So polyline, it's not great, not great. Instead of a polyline for this kind of application, I will be using a Nurbs curve. And there are two ways of how we can create smooth curves through a set of points. There's the, actually, let's go here, under curve, under spline, there's the interpolate curve, and then there's the Nurbs curve. And of course, there's like a more advanced interpolate curve, but we one step at a time, right? What's the difference between them? A Nurbs curve, if I just get it in here and connect my points to it, bam, uses these points as weights, right? So it's exactly the same thing as me taking this control point curve here and just drawing through the points, enter. Just drawing through these points. You can see the control points of this curve being used, right? And of course I can still use it like that. Alternative to this Nurbs curve is interpolate. So under spline, I have this interpolate tool, which also asks me for vertices. Again, vertices are points, like that. And you can see that interpolate actually forces the curve to go through the points. So it really depends on what you're after and which, you know, what kind of a geometry you want to create. Sometimes you want your control points to be weights or anchors, I guess, of a Nurbs curve. Sometimes you want your curve to really go through the points. So you choose either one of these. For this particular example, I will be using the Nurbs curve, right? Nurbs curve can have degrees, right? You can specify a degree. Anything beyond 3 is, for you as a beginner, is not important. I almost never use anything beyond 3-degree curves. So what's a 3-degree curve in the first place? Well, let's create a slider between 1 dot dot 3 dot dot 3. A slider between 1 and 3 set to be at 3. Hit enter, right? We have the slider. It can be 1, 2, or 3. And I'll connect it to the degree node here. Input, sorry, to the degree input here. This is at degree 3. It's a continuous curve that cannot be exploded into separate segments. Degree 2 is a non-continuous curve that can be exploded into segments. That it's basically a curve that is made out of arcs, right? Well, in this case, I guess that wasn't is that an arc? Well, pretty close. But the idea is that it can be exploded into segments. That's the main idea, right? Most important one, right? So that's degree 2. While degree 3 is continuous and always perfectly smooth. Degree 2 is smooth, but is not necessarily continuous. It's made out of segments. And degree 1 is a polyline. Sharp edges between them, right? So technically this and a polyline tool are literally the same thing, right? Then the last bit is in here we have this periodic curve toggle. So which is literally remember, periodic, closed, that's a toggle, a Boolean toggle. It asks us, is it do the endpoints connect, right? So if I choose that it is periodic, so let's just type in toggle, Boolean toggle, like that, connect it, double click on the false, then it closes off the curve for us, and we can kind of adjust it, something like this perhaps. you know, you are able to make a blob kind of a thing. There we go. Banana. Well, crappy banana. And then with this curve done, we get three outputs. First, we get the, well, it says that it's a periodic and a planar curve, and it's planar because it's flat, right? If I were to move this up, like so, now it's going to say only periodic curve. It's not planar anymore. Perhaps you don't see it. I'll just create a panel. It says periodic curve now. If I have all of the points in the same plane, it's going to be periodic planar curve, right? Flat. If it's planar, it means you can create a surface inside of it very easily by using a boundary surface. I'll cover that a little bit later. Then we have the length of the curve, 512 millimeters. And we have the domain of the curve, 0 to 4. I have no idea what that is. What? That makes no sense. Oh, is that the points? Okay, that's cool. Okay. So that's the 0 to 4 is the amount of like control points that it's using. And if we don't have it closed, then 0 to 1. I will not be explaining that because I have no idea what's the logic behind it. I've never in my life used it. Okay, we continue. Curve and length is the things that we use. Right, so now let's do the exactly same thing and let's create a pipe through it. I'm lazy, so I'm just going to borrow this. Or actually, no, pedagogically, let's actually create it again. Pipe, tool, bam, curve, connects to curve, radius, 5 dot dot 25 dot dot to 100. That's gonna be the radius, and then the caps / 2 for the caps, right? If this is not periodic, then the end caps are whatchamacallit. I'm gonna get there. Give me a second. The end caps around it. If it's periodic, it doesn't matter because it's, you know, looping onto itself. And you can see that the pipe is, you know, trying its best. Let's call it like that. It's trying its best to, you know, not self-intersect, but typically it does, you know, especially if your curve is bending at a steeper angle, or the radius of the bend is steeper than the radius of the pipe. Clearly, you know, just geometrically speaking, the pipe will be self-intersecting, right? So you just need to, you have a limitation of how thick the pipe can get, you know, when you're bending it so much. Right. So now we have ourselves a nice little pipe tool here. Okay, this was like a little example, I guess, of the workflow and of the logic of how you can take stuff in, how we can manipulate it, and how we can convert one thing to the other. One last thing that I would like to mention, very important one that I would like to mention before we move on, is that students tend to forget that, okay, here we have the pipe, right? But the Nurbs curve does not disappear anywhere. Like, it's still being generated, it's still here, right? If I hide the pipe, it's, you know, it's not like we are, the moment we use the Nurbs curve, it's not there anymore, right? It is there, which means that then, you know, on this curve, we can say, what would be a good example? Let's say we can say divide curve. We can use divide curve component here and connect our Nurbs curve to the divide curve component, which automatically, since this is set to be 10, it automatically will give you 11 or 10 segments, like these segments here, and 10 segments corresponds to 11 points because the start and end points don't match up. Anyway, or wait, will it? If it's periodic, oh, if it's periodic, it's actually 10 points. If it's non-periodic, then it's 11 points because the end points don't match up, right? So since we have it periodic, since count is by default set to 10, we get 10 points. If I change the count to 50, you know, 50 points, and so on. So we can do this, and then on top of these points we can create spheres. Sphere. Come on, come on. And we can use these points as the base for the spheres with a given radius of, if the radius of the pipe is 10, so let's say 15. Bam. Right. So now you will have, and actually let's have less of them. Right. So now you have a pipe and spheres going through the pipe, and of course it's a messy geometry, but this is just to show you that the curve can be reused for multiple things, and also just to show you that when you are creating a large definition, a large Grasshopper script, start hiding things. That's important. To join because it's going to overwhelm you with amount of geometry that will be present on the screen. To join in these 4 nodes into the existing group, you just select them, you right click on the group, and you choose to add to group. And then they are joined. Disable preview. We're good to go. So that's single operation math, simple operation pipe. Simple operation curved pipe. Right. And all of that is grouped under, I want to group it, hello? Grouped under, let's do like greenish color and simple operations. Okay. So that's our second chapter or third chapter, I lost track. Completed. Now we can move on to a little bit more tricky things such as lists and vectors and planes. Next chapter. All right, let's talk about lists and domains. 2 quite important concepts to get a hang of. So domains, all of the tools that are domain related are located under math, under domain here. And all of the tools that are lists related are located under set tab, list, as well as sequence to a certain degree, right? So for example, in the top view, let's just create some sort of a curve. Doesn't matter what kind of curve, just a curve, right? And let's reference it in as a curve. Set one curve. Select it. I'm just creating this curve container, right? You have done this quite a bit by now, so you should understand how it's done. Then this curve, I want to create a bunch of points going along this curve, right? So what I'm going to do is I'm just going to say divide curve. Divide curve into equal length segments. Perfect. Divide curve. Curve connects to curve. Oh, by the way, when I type in divide, there's divide curve, divide distance, divide length. Those are different ways of how you can divide curve. In our case, we are just using divide curve simply because that's the simplest one. The distance between the points along the curve will be the same. Right? Then we have count. That's how many segments there are. Not points, important, not points, but segments. So if I were to use count of 5, like that, you will see 1, 2, 3, 4, 5. Sure. But then if I count points, 1, 2, 3, 4, 5, 6. Right? There's always one extra point at the end because that's the end point. You start from the start, and the last segment has an end point, right? So no matter how many, no matter what kind of a number you plug in to the count for the divide curve, as long as it's not a closed curve, it's going to have one extra point that you will need to account for. So 6 actually 7 points. Right, so we already kind of touched upon this, but how does Grasshopper actually showcase or work with multiple outputs? You know, because suddenly this node is not generating a single point, it's actually generating 7 points, right? Also 7 tangents and 7 parameters. I'll talk about those a little bit later, but most importantly, single point. How does that work? Well, the first thing that we need to do is to create this panel node here, and we just connect the points to the panel node to see what the hell is going on, and I'll make it bigger as well. And you can see that it generates this list of items, right? Actually, it's 7 items, just like we have 7 points. What a coincidence, right? And those points, of course, are described by their X, Y, and Z position. So every time when you see like X, Y, and Z, it's either, or sorry, when you see 3 numbers divided by a comma, it's either a point, a vector, and it can also be a color, red, green, blue, right? But it's either one of these 3, right? In this case, it's clearly a point, right? And if it were a vector, it would be a vector that's starting later. Next chapter is going to be about vectors. For now, we're just talking about points. So we have this list of points, right? And let me make it a little bit longer, just like that. What can we do with it, right? So of course, now if I have this list and I just create a circle, either circle CNR or just circle, doesn't really matter. I'll just use circle CNR for this. And I use them as a center point for the circles. And I use a radius of, let's say, 5 for the radius. You can see that it creates, it takes this list of points, it goes through the list, and for every item in the list, it creates a circle. And thus, if I connect this here, we get, 10 items, in this case, 10 circles, right? On each corresponding to a point. That's great. What would happen if we change this number? Of course, the amount of circles shrinks as well. Easy peasy. It starts getting tricky when you need to operate with the list, or rather when, for example, when you want the circles to be different lengths or different radius, right? Different radii. So let's shrink down the list to like 3 or something like that, right? So only 2 segments, 3 points in total. And instead of giving it 1 slider, let me disconnect this. I'm going to Control C, Control V. Control C, Control V. I'm going to give it 3 sliders. And 1 slider is going to be set to 2. 1 slider is going to be set to 5. And the last slider is going to be set to 8. And I already taught you this, but first one connects easy. Second one and third one, you need to hold the Shift key. Like that. Shift key, like that. Now it starts getting a little bit weirder, right? Well, it's kind of, you can guess that it's going to work this way, but it's nice that it does, I guess. But you also need to operate around this notion of how it works. So 3 points come in here as a list and receive 3 different radii. Also, since we use the Shift key as a list, right? And thus they produce 3 circles. The first point generates a circle with the first value, first radius value. Second point generates a circle with the second radius value. Third point generates a circle with the third radius value. Easy peasy. And I think, again, pedagogically speaking, I should disconnect these guys here. Come on, Control. Like that. And I should use merge tool instead. Merge, data 1, data 2, data 3. What merge does, it basically, I'll show a separate example. Cat, dog. You would think mouse, but actually horse. It could be mouse. Cat, dog, horse. like that. Don't bother trying to figure out why sometimes it says panel and sometimes it doesn't. I don't know as well. It doesn't matter. We use merge, cat, dog, horse, and we check the list that we got. It creates a list, right? And it's pretty straightforward. The first thing that comes in is a cat, the second thing that comes in is a dog, third thing that comes in is a horse. And then you can use the cat again, and you can use then a horse and a dog and a cat, and so on, right? So you can build up a list with merge. That's how it works. That's what it's used for. So in this case, it's not cat, dog, horse, but it's rather 2, 5, 8. And if I check with the panel, it is indeed a list of 2, 5, 8. If I check with a panel the points that I'm generating here with the white curve, it's, you know, just 3 points, first, second, third, right? So now what it does, it matches up. Index 0, this is, by the way, the index, the position in the list, right? It starts counting from 0. Keep that in mind, very important. It doesn't start counting from 1, it starts counting from 0. So index 0, radius 2 corresponds to this point right here, and thus once we create a circle around this point, it's going to fetch this radius. Then this point, this radius, this point, this radius, right? So that's pretty straightforward. If I connect it, voila, right? It just matches up. Easy peasy. What happens if we have more points than we have radii, right? So if the list of points is larger than the list of radii, well, let's check. Oop, one more. So suddenly we have 0, 1, 2, and here we have 0, 1, 2, 3. We have 4 items here and 3 items here. It just keeps repeating the last item in the previous list, right? So it just keeps on repeating the last radius. So no matter how many we add, the circles after index 2 will all have the repetition of what we had for index 2, because it ran out of numbers, right, to use, so it's just going to use the same number. So keep that in mind as well. When two lists don't match up, it's going to force the lists to match up by taking the last item on the list and just repeating it until, you know, for as much as it needs to. Easy peasy lemon squeezy. Okay. What else? Let me just, I'm just cleaning this up a little bit. Actually, yeah, I'm gonna clean this up. Let's do something like this, something like that. Okay. So now on to different ways of how you can manipulate these lists, what you can do with them, right? So in this case, we are giving it, you know, 2, 5, 8, like we're giving it specific values for the radius, but perhaps we want to do something a little bit different with it. Perhaps we want to generate a list, right, for values to give for the points, for the radii, sorry, for the circles. So instead of us giving it predetermined values that we ourselves manipulate, instead we want to generate it. We want to generate them. So what we can do is we can use a random number generator. That's one. I'll actually go to, I believe it's under sets. It should be under sets. If we go to sequence, there's random right here. So you can use a random number generator, or you can create a sequence of numbers. Sequence. Wait, I'm being stupid. 1 second. I did something wrong. No, it's not sequence, it's something else. Oh, series. Oh, my bad. Lost my mind there for a second. Series of numbers. So I'll cover both of them. First, I'll start with a more controlled approach of series. So if I just grab a panel here and I show you, it just generates, it's a counter, right? It just counts from 0 until, in this case, until 9. So it generates 10 numbers in total. I can change from which number does it count. So in this case, it starts counting from 0. I can // you should start counting from 5, from the number 5, right? Like that. I should give it a step size of how, what's the gap between the numbers. So in this case, the step size is 1, meaning that it just goes 5, 6, 7, 8. If the step size was 8 or something like that, it would be 5, 13, 21, and so on. If the step size is 0.01 or 0.2, it's going to be 5, 5.02, 5.04, and then so on, right? So I can control the step size. In this case, I'll keep the step size as it is, set to by default value of 1. The count, the actual amount of numbers that is being generated is very important, right? Because that needs to correspond to the amount of points that we have in this divide curve list, right? That are generated here, right? From the divide curve. So I could honestly do, there are 3 ways of how you can do it. Way number 1 is you take this number and you keep in mind that it's always going to be 1 extra. So you can take this number, you can say plus, connect it like so. So 7 connects to A, and for B, I'm just going to use //1. So we always connect 1 to it, and we have we use it as a count here, like that. So this is like a, it's automated, but it's not elegant, I think, right? But it would work, right? It would always correspond, I have this set to 8, meaning that it generates 9 points, meaning 8 plus 1 is 9, and it generates 9 numbers, right? This would work. But I think, I feel like a much better way of doing it would be to, let's make a little bit of room here. And probably this should be in the top. Yeah, something like that. Come on, go here. So a much more elegant way would be to actually ask the question of, okay, how many points are you making, right? Before giving it, before generating the different numbers for the radius, for the future radius of those points. And the way you do it is you just go to sets, list length. Am I blind? Hello? Is it seriously not? Okay. List length. And I'm going to Control-Alt-Click. It is here. There it, okay, it was here. Okay, list length. I just connect my list of points to here, and I get an answer, right? Again, I love to show you things with a panel. 9, 9 points. So then with the 9, we just give the series the count of 9, like that, right? Now we get the 9 points. I'll disconnect the merged values. I'll have these grouped up for you just so that you don't forget. But now we will be using the new values generated from generated with this series node. Plug that one into radius. And now we can see that point 1 is going to have a radius of 5 because it starts counting from 5, and the last point has a radius of 13, right? So that's series. And the nice bit about that is that, we can mess around with this. Actually, let me edit this and increase the maximum range to like 20. Oops. To like 20. Increase that. So it corresponds quite neatly. So that's that's a controlled way of how to do it. You can change the step size and then blah blah blah, yada yada, right? Semi-parametric, well, not semi, quite parametric model. Another thing how you can do this is with a random number generator. So if I do // and I connect the random number to the panel, you can see that it generates some sort of a number somewhere between 0 and 1, and actually always between 0 and 1. First notion is that there's no truly random numbers in programming. Everything is pseudo-random, meaning that there are algorithms that generate numbers that seem random, that, because there are so many operations that happen with them, that they seem to be random, and they sometimes are connected to, I'm gonna get there. Sometimes are connected to the stock market fluctuations. Sometimes they're connected to the date, and then so on. But it's all quite random. I think the most random ones are like they have to do something with chemistry or physics. Don't quote me on that. Anyway, since they are pseudo-random, they deal with seed inputs. Seed is, if you change this, it will generate a different seemingly random number. So if I change the seed to 5, a different value. 6, different value. I go back to 5, same value, right? So a seed is like you can choose a different random number from this jar of random numbers. The question is, how do you control, the minimum and the maximum? And that's the range. And this is going to be our first look into domains, right? A domain is basically, first of all, we'll start with a one-dimensional domain, which is literally just a scale between two numbers, right? Boop, boop, 0, 1. That's the, you don't see it. There we go. That's the domain, right? So a domain is basically all of the possible numbers in between this range, right? And that 0 and 1, that can be anything you want. That can be minus 55, and in here it can be pi or whatever, right? But that's basically the domain. And then if you say that, oh, I want the middle of this domain, then you ask what's right in the middle between minus 55 and pi. You need to add them up, divide by 2, and you get the middle of the domain. And the reason why we use domains is because it's very easy to get different ranges, and it's very easy to then divide them up and extract numbers from them and manipulate them as well. So you can take a domain and you can stretch it out or compress it to like different values. And I'll explain that a little bit more in just a few minutes, but that's the basic premise of it. It's a range of numbers, right? That's the domain. So here, where you have random, that also is set to be, it uses a range. So this is, when it generates a random number, it asks, within what kind of domain should it generate the random number in? And in this case, the domain is set to be between 0 and 1. We can change that. We can say that the range actually should be, we need to go to maths, domain, construct domain, right here, the first one. Not construct domain squared, that's later, much later. Construct domain. Simple one. Asks us for domain start and domain end, and I can say that, okay, I want a random number between 5 and 25. So domain start will be, I'll just create a slider, 5. Domain end will be 25. Right? Something like that. Should make a little bit more room here. And now if I check the output of it in my panel, bam, between 5 and 25, easy peasy. If I connect that to the range, now every time I change the seed, it's going to be generated within that range. Okay, that's great and all, but how do we generate, this amount of numbers, or I should show here probably, this amount of numbers that correspond to the amount of circles? Well, that's the number input, right? I can use exactly the same trick as what I showed with the series. So let me just disconnect the series node and disconnect the list length node here. Grab those in, group them up just like that. And let's use this random number generator instead. like that. I can actually delete this. The construct domain is so huge. Okay, I'll just put it here, right? Now for the points, I ask with list length, I ask what's the length of the list, connect that to the number, input of randomness, of random number generator, and it generates a bunch of random numbers at this particular seed, right? And I can change the seed. And then I can use those random numbers to plug those into the radius. And now I have random circles. If I say that, oh, no, the big circles are too big, I can very easily just say that I just squish the domain, right, down to 11 from maximum 25, right? So the maximum range of how far it can reach is now 11. The minimum range, I can also squish that down to 2. I can increase the amount of points that there are, and so on, right? So I have, even though this is random, I have control, at least a little bit of control over this. And then if, for example, I don't like the pattern that I get, I can always change the seed until I get something that I like more, right? So that's the basic premise of a domain and how it works. Okay. With that out of the way, let's make a fancier definition. What I will want to do is I will want to, well, first of all, let's make all of this clean and nice and dandy. So I'm going to select all of this, group it up, lists and domains, part 1. And I'll also select all of this and hide it. And now I'm going to draw beautifully of what I want to do in this next example, right? To continue talking about domains and how you can operate with them, and lists, of course. We have our curve. Beautiful. Let me just try it one more time. I know I can do better. Sure. Okay, we have our curve. I want to have a point somewhere here, like that. I create it in Rhino. I want to divide the curve up 1, 2, 3, 4. That's way too many. Okay, why am I doing this to myself? Okay, sure, whatever. We explain it with a lot of points. I want to divide up the curve. I want to measure the distance between the point that I have created and all of these points, right? And then I want that distance to be remapped to radii of the circles that I will be generating on top of these guys, right? So the closer the point is to a circle, to a point on the curve, the smaller the circle. The further it is away, the larger the circle, right? So the distance controls how big the circles are. This is like the most basic attractor point kind of a tutorial, I guess, that I can do, but that will highlight a few notions about the domain and generally lists that I would like to specify. Before we actually, let's do this, and then I will kind of cover a few more instances of where lists are useful and how they can be used. So for now, let's do that. I reference in the curve component. Set one curve. I reference in the curve with the component. Set one curve. Then I divide up the curve. Just same repetition of what we did here. And I will use a number slider of 20 for the count. So I have 21 points here. I will create a single point in here. Bam. Like that. Single point. And I will reference it in as well. Point. Set one point. Select it. There we go. Now I will measure the distance between this point and all of these points. distance. You don't know this node. I haven't used it before, but it's kind of self-explanatory, right? Compute Euclidean distance between 2 point coordinates. Compute distance between 2 points. Point A is going to be my point here. Point B is going to be a list of points. Since this is going to be a list, the distances output is also going to be a list, right? I can visually show you what it's doing by creating a line between point A and all of the points, right? It's measuring these distances. And these are the lengths of these lines or the distances, right? Then I could be very kind of simple about it, and I could just say CNR, circle center normal radius, the center are the points, the radius are the distances, and call it a day, right? And the nice thing that is that since all of the distances are, give me a second, all of the distances are the radius of the circle, you're making sure that the circles will always hit the point that you have placed, right? They will always try to follow along the point that you have placed. That's just mathematically, you know, how it works. But that's not what we want. We want to have more control over the radius. We want it to be an influence, but to have control over the maximum and the minimum range and how fast does it fall off and so on, right? Apologies. I'm sorry. How fast does it fall off and so on. So I'll move it quite close to one of the points just to see better, right, of what's going to be happening. And I'll disconnect the distances from the radius for now, because we need to make a few changes, a few adjustments, right? So the first thing that I want to do is I want to, one second, sets, no, that's going to be under parameters, utilities, come on. Yeah, it's a remap. Okay, sorry. What we're going to do is we're going to use this remap numbers node. It's a very, very useful node that will enable us to take a range like of these guys. Take a range from the smallest, which is 4.94, to the highest, 83.148,133. You know, so you have the minimum and the maximum, and then squeeze it or expand it or move it to any other range that you want. I will explain this graphically. So first of all, let's just place it so that you can see what we're talking about. Remap numbers asks us for a value, a source domain, and a target domain. Example, value is 5. Source domain is, oh, by the way, you can write it like so, / 0 to 10. That's a domain. It's going to accept it. Target domain, 0 to 100. Target. And if I look at mapped output, it gives me 50. What just happened? Let me explain. We have one domain, the source domain, that is between 0 and 10, right? That's our source domain. And we have another, the target domain, that is between 0 and 50. Oh, sorry, 0 and 100. I'm stupid. 0 and 100. Right? Then let me just use red. And those domains have infinite amount of numbers, you know, divided, can be divided infinite amount of times, right? So the scale is like that. You know, a bunch of numbers exist in them. And one of the numbers in the source domain is 5, the value of 5. And you know, just reading through proportion, 5 is literally going to be right in the middle, right? The value 5. So then the question is, if we take this domain and we just look at the proportion, right? And we map according to this proportion onto the new domain, what will the value be, you know? Oh, that's an ugly color. Let's not use that. Yeah, sure. So if I were to, you know, I just map it like so in this domain, you know, it hits here. The question is, what's the value, right? And since it's quite straightforward, between 0 to 10, 0 to 100, clearly it's going to be 50, right? But sometimes it's not so easy, you know, if the range is actually 0 to, well, actually it's always going to be easy because 5 is right in the middle of the domain. So 0 to 200 is going to be, you know, going to hit at 100, 0 to 500 gonna be hitting at 250 and so on. But you get the idea, right? You have like a domain and you can shrink or expand it, and since it only cares about the proportion of where the number is in the source domain, it will find a new like numeric value at the same proportion in the target domain. Why is this useful? Well, and I probably should, this is going to stay, but let me just, that should be 100. There we go. Like that. That's going to be saved for you. So why is this useful? It's useful because currently we have all of these distances that we need to squeeze, right? That they're too big. Radius, they're too big. I could divide them, you know, I could use division, divide them by 5 or whatever. You know, and that would kind of work, but that's not a lot of not a lot of control, because I can't control what's the smallest value, I can't control what's the largest value. All I can do is just divide it, right? And then try to get it to work. So instead of that, I'm going to use remap numbers. I'm going to say that, well, the distances are the values that I'm going to be remapping, you know, to new values. The source domain, you know, I need to somehow know what's the smallest value in here and what's the largest value in here. And thankfully there is a node for that. So under domain, under bounds, we have that node. It's called bounds. I just give it like a set of numbers and it produces a minimum and maximum value for me. 4.94 to 83.15, right? 4.94, 83.15, right? So that's my starting domain. And then for the target domain, I can use whatever value I want, right? So here I created a panel. Usually I do create panels, but as you saw here, you can also use construct domain, right, to create one. But in this case, just simply to make it a little bit smaller, I will be creating a panel, / and I will be saying, well, the smallest diameter or radius that I want should be 2. Then spacebar, 2, the word 2. Let's say the largest one, 15. I can always adjust it, right? Enter. 2 to 15. Connect that to my target. I get all of my values remapped. You know, the smallest one becomes 2, the largest one becomes 15, and all of the rest are in between. And I can now connect the mapped values to the radius, like so. If I then look at this and I say, well, 15 is a little bit much, I can replace this with 7, like that. Increase the amount of points here to 100. And now I have a system that reacts to where my point is located. Quite useful, right? This is like the beginning for parametric modeling. Quite a useful thing. Of course, when you're dealing with domains and so on, there are more use cases for them. But as long as you know the pure basics of how they operate, then you'll get the sense of, what's a curve domain, what's a surface domain. You're going to get that much faster. And we're going to revisit domains quite a bit in this course. So don't worry if you're not, completely clear about how it works. So we have our circles. And one more thing, one more thing that I would like to note is if I then take these circles, right? The circles that we have, if I take these circles and I were to extrude them, so I can use extrude tool, asks me for what's the geometry that I want to extrude. That should be the circles. And asks me for what's the direction. So basically it asks me for a vector in which direction should I extrude, and the vector can have strength associated with it. Thus, you just don't describe just the direction, you also describe the amount. So I will, in the next chapter, I'll cover this much more, but when it comes to vectors, you have the basic ones, X, Y, Z directions that you can access through vector tab, vector, unit X, unit Y, unit Z. So in this case, we use the Z direction, like that, connect that. And by default, the unit Z has a value associated with it as 1, meaning it extrudes upwards as 1, but you can use any factor that you want. So for instance, if I use 50, connect that, now the strength of the Z vector is 50 millimeters, 50. Can we make the extrusions correspond to where the circle is, where the point is? Yeah, of course we can, right? We already have the distances here, we can just reuse them, right? And we have the bounds here, we can just reuse them. So what I can do is I can just say another remap numbers, right? The values are the same. We measure the distances like that. The bounds are the same, the minimum, because the values are the same, right? So we reuse that. And the only thing that we change is the target domain, the target domain. So // let's say the smallest one is 5 and the largest one is 50, right? Connect that to the target, connect the map to the unit Z, and now it corresponds to the height of it also corresponds. Question, what happens, or rather, how can you make it so that they're tall where the point is and they're small where the point is further away? By the way, this point is called attractor point. If you want to Google for tutorials, more tutorials on this, you Google attractor point tutorials. So all you need to do is just flip it, right? So the smallest number, or the number that corresponds to the smallest number, should be 50, and the number that corresponds to the biggest number should be 5. So I flip this, 50 to 5. Now, the closer you get to the point, the taller the structures will be, but since this is not flipped, they're still going to be pretty wide here, right? So they're going to be narrow and tall here, and wide and low here. Make it even more narrow, like that. So that there's almost like a, not almost, but a gap in here. Last bit to do is just to take the extrusions and to cap them. Oops, that's the wrong, here, cap holes. Just creates a surface on the top. I'm disabling the preview of literally everything except, the final cap holes node. Right click, bake, default, group, yes please. Just to show you, I will be deleting it soon. Like that, we have our first, kind of parametric model. Arctic view. Neat. Stepped weird, weird stepped thing. Shigeru-ban paper tubes. All right, back in here. This definition is finished. Let me delete that. Back to shaded. And I will just so that we are all kind of just so that it doesn't get lost, I will right click, internalize data for the point, right click, internalize data for the curve, delete those, group this up, call it part 2, or list of domains part 2. Okay, so that's done. And then we have remap explanation. Okay. So now one last bit about in terms of domains. Currently, that's all I want to show you. There are of course more stuff to show, but in this particular beginner tutorial, that's all I want. But for the lists, there are a few more things that I would like to showcase. And I will be showcasing them in just a theoretical framework. So the Rhino file doesn't matter. I'll just show this in Grasshopper. So I'm going to create a panel, and I'm going to go for cat, that's cad, or actually sure, cad, dog, cat, mouse, horse, 5, 23, false, that doesn't matter. Let's just have this list here. So this is still not a list because you can see it does not have any indexes, right? It's not regarded as a list, it's just regarded as poetry, right? By Grasshopper. It does not understand that this is a list. So I need to right click, I need to choose multi-line data for this to be turned off. If it's turned off, then immediately it just takes every line and it just places it at its own object into the list. So now it's a list. Things that we can do with the list. Number 1, use list item. If even here, right? Oh, actually, I said I won't show it in Rhino, but I will in this particular example. Cap holes, right? I have a bunch of these cylinders, right? What if I want cylinder number 23 out of these? Well, I can go for the list, I can connect this list of cylinders with capped holes to my list item node. And for the index, I can say //23. Connect that here. Visually, nothing really changes as much. That's because it's, the geometry that it gives us overlaps with the geometry that already exists. So I need to hide the capped holes one. And now I can see it. It's cylinder number 23. What about number 24? That's the next one. What if I say, give me 23 and 24? It's going to complain. Why does it complain? It complains, we click on this little error. Data conversion failed from text to integer. Oh, this is not text, this is 2 numbers. Don't forget, there are 2 lines right now, but they are not a list. So it reads this as poetry. If you right click and you choose multi-line data to be turned off, suddenly it works, right? So now we get 23 and 24. I can also fetch out 5 and 69 and so on, right? And I get those cylinders here as well. So list item is useful for fetching geometry. If I showcase it here in our cat, dog, cat, mouse, horse example, list item, by default with the index 0, it gives us the first item in the list. If I want the last item in the list, the index should be -1. It's smart like that. It counts backwards as well. So if my index is -1, pop, gives me the last item in the list, which is 23, right? Don't forget that you can also always click this little plus sign, and then we get +1 here. So what comes after 23? CAD. It just keeps wrapping around, right? It keeps repeating. +2, dog, and so on, right? So you can zoom in. Also, you can, of course, go backwards as well if you want to. right? So in this case, I'm just going to have index set to 0. So it's cat, dog, cat, right? It gives us that. Very, very useful for extracting geometry. The wrap is what happens when it reaches the end. Should it then, well, actually I can show you. Toggle. Oh yeah, what kind of input should you give it? Just look at the icon. So wrap has an icon for the toggle, right? Index, come on. Index has an icon for integer number. List has an icon for any type of data, right? And the outputs also are color coded or icon coded, I guess. So if wrap is set to be no, don't wrap, and then I say, give me an index 7, which does not exist in this list, all of these will freak out, right? Because it can't even fetch the first one, not to mention the second and the third one. If I make this wrapped, if it can loop, then 7 is going to be back to the start. So it goes through the list and it goes back and it fetches cat, dog, cat, right? So that's how this works. Panel, let's set it to 3, just so that it's not as extreme. Okay, that's the first thing. Let me place it here. We're going to reuse this same list. Then if I want to insert an item, let's say into this list, I use insert items node. I'm just going through these nodes right here that I find to be quite useful. So insert items, I have my list, and the item that I would like to insert is going to be, let's say, octopus. Come on, again, octopus with a capital O because they're great. Connect that. And it asks me, okay, where indices, at which index would you like to insert it? So I can just do // and I can just write, or I can actually create a slider, 5. Please add it to index 5, right? So it's going to push 5 and 23 downwards. If I look with the panel, right? Now octopus has been added to this list. And I can choose where it gets added. Of course, when it's wrapped, it loops through and it can, it goes through the list and then it keeps on going. If this is not wrapped, then it's going to start complaining. We already covered this, right? So that's insert items, really good. If I want to, I can have multiple indices here, right? So I can insert octopus in multiple different places, or if I have 2 items here, octopus and squid, and I choose multi-line data to be turned off, then first octopus gets inserted, at index 3, and then second squid gets inserted at index 5, right? And since, okay, it gets tricky. You can see that squid is set to be index 6. That's because when we insert octopus, everything kind of scooches over, right? So it starts becoming a little bit weird with the numbering, I guess, or not counterintuitive, but a little bit harder to follow. So what you need to do is you need to just check the original list and just see, okay, I want in between cat and mouse, I want the octopus, and then in between the horse and number 5, I want the squid, right? And then it makes sense rather than trying to follow along what kind of numbers would you want them to have. Geometrically, this is, I use this much less compared to list item, but also sometimes quite useful when you need to insert a specific object into the list. Okay, so that's that. Oops, I'm grouping things too much. Give me a second. Measuring list length, I've already showed you that. In item indexes, not so useful. Sometimes useful, of course, but not as much. Dispatching, weaving, replacing numbers, all of those are quite, starts becoming a little bit tricky. Okay, let's do one last one before we move on. Dispatch. Dispatch is, out of all of these, is the most useful. So dispatch. I have a list, bam, and then I need a pattern. And right now the dispatch pattern is set to be true, false by default. You can see me hovering my mouse over it. Dispatch pattern, true, false. So it gives me two lists. Dispatch gives me two lists. If I check them, list A has 4 items in it. List B has 3 items in it. And let's try to figure out what the hell the pattern, how the hell does it work? Well, we have our cat, dog. Okay, I'll change cat to something else like pigeon. There we go. So we have our pigeon, dog, cat, mouse, horse, 5, 23. And here we have pigeon, cat. So this item. Oh, can I draw on top of these? Yes. We have our pigeon, right? We have our cat. We have our horse. And we have our 23, right? And then dog, mouse, 5, dog, mouse, 5. Most likely, that has something to do with the pattern of true, false. So imagine this. You have a list and you just go through it as true, false, true, false, true, false, true, false. And whatever lands on true goes to list A. Whatever lands on false goes to list B. So pigeon, true, list A. Dog, false, list B. Cat, true, list A. Mouse, false, list B, and so on, right? So it separates out, it dispatches according to some sort of a rule set. So what I can do is I can say / true, true, false, true, true, okay, sure, whatever. True, true, false, true, 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 false, true, true, right? That's what the pattern it's going to repeat. If I go for multi-line data, always needs to be a list, by the way. Connect that to dispatch pattern. Let's get rid of this nonsense here. Then I have true, true, pigeon, dog, false, cat, true, true, mouse, horse, right? Finishes the pattern, starts repeating it. True, true, 5, 23. And now if I had one more that is like Zaha, then we have false. Zaha lands on false, right? So that's dispatch. Showing it in action. Let's go back to our capped hole cylinders right here. And I can say, well, I could just do dispatch for this. Dispatch pattern. And then for list A, I can just say, oh, this is going to be the first time when we use a container, not for the sake of referencing. So I can use a brep container. And I can say, I only care about list A. So I just fetch that. Right? And if I hide all of it, like only every other entity gets dispatched because the pattern is true, false, right? And I can say true, false, false, false. By the way, a faster way, remember when I said 1 is true, 0 is false? I can just do 1, 0, 0, 0. Multi-line data, dispatch pattern, and now I get only every 4th element in the list, extracted, right? But I can do even crazier stuff with it because since this is true or false, I can start playing with logic. I have all of these distances here, right? All of these measurements that we've done. Let me remind you, line. Boop. You don't need to do this, by the way. the line from between this point, the anchoring or the attractor point, and all of the points on the curve. We have all of these distances. So those distances I can ask, yo, is this larger? Is this larger than, it's under math operators, larger than or smaller than, right? Is this larger than, let's say, it's a long wire, I know, but it is what it is. Whatever, 55. Is the distance larger than 55? And guess what I get from it? I get answers. Yes, it is. Yes, it is. Yes, it is. No, it isn't. No, it isn't. And then so on, right? So I get answers. And if I get those answers, I can use that larger than as a dispatch pattern, right? Because it's all true and false statements. So all of the entities that are further away than 55 millimeters from the attractor point are placed in list A, and all of the entities, or in this case cylinders, that are closer are placed in list B, right? So what I can do is I can then play with the range, right? And mess around with that. If you want the logic to be reversed, you can just use a tool that's called NOT, gate NOT, which literally takes true, makes it into false, takes false, makes it into true, flips it on its head, right? So now if I use gate NOT, it only will give me what's within the range of 60, let's say, millimeters, right? So that's one way of how you can dispatch objects, or how you can separate the lists into two parts, right? Okay, group that up. Give me just a second. For now, that's fine. Okay, a few more things, and then we move on. So we have ways of how we can remove data from the list, right? And in this case, I will not be showing it here with the dispatch or whatever. I will be showing it, or actually we should, I should. Okay, so let me just copy over this panel right here, and we continue with this list, right? So I guess 1, 2, 3, yeah, 4. I'll show you all 4 culling. Cull is remove. Have that in mind, right? Cull is remove. So cull index, I can just select this. It's literally like a list item, only reverse, right? So if I have this list and I want to remove something from it, I need to give it an index, and I can say I want to remove dog, which is index 1. I want to remove mouse, which is index 3. I want to remove both of the numbers, index 5 and 6, right? And I connect those indices here, and you can see it's complaining. Why? That's a test. Why is it complaining? I'll give you a second. You can do this. I talked about this like 50 times already. Multi-line data. Right click, multi-line data. Needs to be a list, or else it's poetry. Okay, so now we are removing index 1, dog, we remove index 3, mouse, and we're removing 5 and 23. And what we end up with is pigeon, cat, horse, saga, right? So that's easy. That's very straightforward. Then the next one is cull nth. Cull nth is, well, it takes a list and basically which every number should be culled. So in this case, cull frequency is set to 2, which means that every other object will be removed. So pigeon stays, dog gets removed. Cat stays, mouse gets removed. Horse stays, 5 gets removed, 23 stays, Zaga gets removed. That's cull frequency of 2. If I set cull frequency of 3, it's basically true, true, false, true, true, false, true, true. You know, every third item gets removed. So you can probably start seeing that you can mimic exactly the same behavior with dispatch of what you have with call nth. And this is a reoccurring theme in Grasshopper. There's always multiple ways of how you can do something, right? And you just find the one that works for you, or you find the one that you know how to how to do, right? So that's call nth. Boom, boom. Okay. Call pattern. That's going to be literally like dispatch, except that it does not provide you with list A and list B. It only provides you with list A, right? So call pattern and dispatch, I kind of want to group them up here. I won't even kind of talk about it as much, because if you think that you need to use call pattern, just use dispatch. Just keep that list B in there just for, you know, in case you need it in the later. And then the last one is random reduce. Well, that works exactly what how you might think it does. You connect the list and it asks, how many items would you like to remove from the list, right? So you could say, get rid of 5 items, please. And it gets randomly rid of 5 items. And you can change the seed, of course, you know, for this. So you can remove 5 random, you know, different random items from the list. A way of how you operate random reduce is usually not with a number slider, but rather by asking the question of, okay, how many list length, how many items are there in the list? And then multiplying that number by a value between 0 and 1. 0.500, right? What does this give you? This becomes percentage of how much do you remove, right? Imagine that this is a number 20. You know, there are 20 items in this list. There are not, but imagine, okay, actually, there are 8 numbers in this list. You don't need to imagine. 8 numbers. This gives you 8, you know, list length gives you 8. Number slider 0.5, 8 times 0.5 is 4. 50% of 8 is 4. 0.2 is 1.6. What happens when you try to remove 1.6 elements from the list? If I connect that to reduction, you can see that it actually, apologies, it actually rounds off the number into the closest integer. So 1.6 is 2. So it will remove 2. But by doing so, you're able to say how, you know, what's the percentage of all of the elements that you want to remove. And sometimes it's super useful, especially when you're dealing with paneling and you want to remove some of the panels. You just have this setup, you know, list length multiplied by a proportion, which becomes a percentage, and you just reduce the list that way. Okay, so that is that. I think with this, we're kind of done with the lists. There's weave as well, but weave I will cover a little bit later. Jitter, random. Sets, we don't touch sets just yet. And then data trees, those are very scary. We will talk about them later. And this became orange, that's fine. All it needs is just a curve and it's going to start working again. Okay. Sorry for just blabbing around. We move on to the next step, which is going to be learning about vectors and learning about planes and what those are. A little bit more geometrical, I guess. I'll see you there. All right, let's talk about vectors and planes. I'll start with vectors first of all. So in Grasshopper, in Rhino, honestly everywhere, vectors are used to define direction. And the way they are constructed, they basically have a direction at which they're pointing at, and they have a strength associated with that direction, right? So it's like a function of direction and strength. If we go to the vector tab here, in the top, right here under vector subtab, we will have most of the tools that are associated with creating or manipulating vectors. For example, if I were just to use vector xyz, vector xyz node, I have the x component, the y component, and the z component with which I can define, a direction for a vector. The problem with that is even if I were to, let's write something actually, let's do 5 and 0, and let's just use 0, 0, 5, right? So a vector that is pointing upwards, vertically and at the strength of 5, it is not shown to me in the Rhino viewport. And that's because by default vectors are not shown. So to actually see a vector, you need to create a tool or use a tool called vector display. There's also vector display X, but in this case, we will simply use a simple one, vector display. X, I think, is extended or something like that. Anyway, vector display asks us for two things actually, anchor and vector. Why does it, and we can connect vector to vector, sure. But the question is, why does it ask for an anchor? Well, that's because a direction, right, does not have a starting point preemptively kind of described, right? It's just a concept of a direction. So you need to say, you need to anchor that direction to somewhere, right, to be able to display it, or else it's just, how do you show north? Well, you need first of all to, select where that north arrow is going to be located, and then you show it, right? So that's exactly the same thing here. So for this, I can just simply construct point. I can construct a point, and thankfully by default, construct point component gives us a point at 0, 0, 0 coordinates. So I can just simply connect the vector. And now you can see a vector appear here, right? So now how does this work? Actually, I will disconnect that, copy paste. I will have 3 sliders going between 0 and 10. Like that, right? And I can just explain to you how do you construct the vector. So if I increase the x component, boop, 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 you can see that now in x direction, the vector goes by 5 units, in y direction, the vector goes by 0 units, and in z direction, the vector goes by 4 units, right? So we have a direction, and then if I do 9 here, then or 10 here, then we have a different kind of a direction. And of course it can go opposite, it can go into the negatives and so on, for sure it can. But basically with 3 numbers, you can define any direction in 360-degree globe, right? As long as you have X, Y, and Z component. And that is one of the kind of, not necessarily tricky parts, but one of the more hard parts for people to not get confused about, is because the point also corresponds to 3 a point also corresponds to 3 coordinates, x, y, z, right? And if I were to actually construct a point with the same coordinates, they would end up exactly at the end of the vector, as long as the vector is anchored to the 0, 0, 0 coordinate of the world, right? So that's that. And also vectors have, as I said before, they have a length, 11.87 in this case, right? So that's the complete basics, of how you construct a vector, right? Or rather what a vector is, I guess. Should I keep going to the right? I guess I should. We just keep going to the right. Construct vector. Okay. Now if I look at this, here we have the deconstruct vector node, which basically can take this vector that we have and it can explode it into X, Y, and Z components, right? So we can get these numbers separately. That's great. I mean, it's a no-brainer, so I'm not going to incorporate that too much. Okay, what does unit vector do? Unit vector, for example, here we describe the direction, right? And we have a pretty long vector, which is like 12, almost 12. Unit vector, if I connect it, And instead of this, let me just quickly, instead of this vector, I preview the unitized vector. You can see that it became much shorter. How short, you ask? Always 1 unit in length. In this case, my Rhino file is running in millimeters, so the units are set to be millimeters. So this vector, while keeping the direction, becomes 1 millimeter in length. This is very, very useful for when you need to then, then you can multiply this vector by 50, and then you know that you will have a direction that is set to, you have a direction that is set by these 3 numbers, for the vector, but you know for a fact that the length of your vector is 50, right? So that's one way of how it's useful. Other ways are just, unifying all of the vectors to have one uniform length of 1, or strength of 1, I guess. Another way, I'll delete those. Another way of how to introduce 50, the power 50 to a vector, is by using a command called, or node called amplitude, right here. This bad boy right here. Amplitude, vector connects to vector, and then here we describe the amplitude with 50. Connect that to the vector display, and we get exactly the same vector. So amplitude basically takes any direction and overwrites its length with, with the number that you give it here. Exactly the same thing as what we've done before with 2 nodes. Now we're doing it with 1 node, right? So I'm going to keep it as it is here. Add to group. There we go. Now moving on, you can of course construct vectors, simple vectors, such as unit X, unit Y, unit Z. I have an anecdotal thing. For first, I would say 3-4 years of me learning Grasshopper, I always thought that this is N, not Z. And I didn't understand why the hell, unit X and unit Y, that makes complete sense, because it's these are vectors that are aligning. I can show you. Vector display, construct point. They're very small, but these are vectors that are 1 unit in length and are aligning with X direction, Y direction, and then, here. And then I would freak out and I would not understand what the hell is an N direction. It's just a rotated Z. Anyway, but these are like the world axes that you can just get, right? And if you want to define a factor, such as 50, it's just a slider, or any number for that matter. So you can just give it factor, and thus you give it power. So for example, when you want to move something up for translation, you give it, this kind of a vector with a certain power associated with it. I'll show that, of course, in later stages, but just keep in mind. So we group those. Then to measure the angle between 2 vectors, I'm just going to borrow, or actually we can create a few. So let me make 3 points here, move 1 point up, like that. And I'll just get them in as 3 separate nodes, just for the sake of clarity. That's going to be the original point. Second point, origin point, sorry. Second point, third point, right? And now I will construct a vector between these points. So under vector, there should be vector 2pt, this one right here, vector between 2 points. I use that. And for my first vector, I use the origin point, which is this guy right here. It really doesn't matter which one you use, origin point. And for point B, I will use this one right here. And I get a vector, right? And if I use vector display, and I use my origin for the vector display, you can see that the vector that is created right here. And then I'm going to create another vector, vector 2pt, between the same origin point, but this time the third point that I have here referenced. And I'll use vector display again, anchoring to the origin and looking at the second vector. There we go, something like that. Technically, I could also do this and not use this. That would work as well, but I just want this to be kind of clean, as clean as possible, honestly. So we're doing this. So now we have two vectors, and clearly these two vectors, right, have an angle between them that can be measured at a specific surface, right, at a specific plane, if you will. So to measure the angle between the two vectors, you can do, you could do a cross product type of a thing and then use that, but we ain't about that life because that's a little bit more complex. We will just simply use the angle component here, angle, which will ask us for the two vectors. We do have those, vector A, vector B, and it is also going to ask us for a plane for a two-dimensional angle, right? Even though, if I remember correctly, apologies, give me a second. If I remember correctly, even if you don't present it with a plane, it's going to figure out the closest fit plane for the angle. So that's kind of nice. Anyway, so once we have the angle, it's in radians, right? The angle is in radians, so I can do degrees, conversion to degrees. So from radians to degrees. You can just hover your mouse and you will see angle in brackets in radians, right? So you convert it to degrees and we can take a look at the angle between the two vectors, which is 91. If I look at it, yeah, seems kind of accurate. That's really close to 90 degrees. This should, yeah, this increases the angle. This decreases the angle, right? So that works. Okay, what if instead of one origin point, like what if these two vectors are disconnected? So what if, let me just clear, and I'm going to hide the preview of everything else just so that it's not too complex. And I'm just going to make a copy like so. And let me really quickly redo the points, right? So I just deleted all of the point components and I'll rebuild it so that you don't get confused. Point A, point B for the first vector, set one point, that's going to be point A. Point B is going to be the one that's, let's say, looking up like that. Connect. And the vector display anchors itself always to point A. So we see the vector. And then two more. Point. Control C, Control V, point. Point A is going to be this one. Point B is going to be this one. Connect. And again, anchor. See? That it's definitely not a problem for it to measure the angle. Because all it needs to do is just move this, these 2 points together, and then it gets its angle from there. Very kind of useful. So that's kind of simple. That's kind of easy. And that's how it works, right? Okay. So that's measuring. Let me hide these. Let me group these, place them here. Internalize. Okay. Delete. There we go. I'm not touching upon the plane because we're not there yet. We're gonna get there, but not there just yet. Cross product and dot product, for now, I'm going to skip over these. These are just slightly more advanced, and I think you need to get a hang of, generally of how vectors work before you start moving into cross-dot products and so on. Instead, we will, one second, thinking. Yeah, instead I will show you like a few nicer things of how vectors can be used. So first one being, let's say we have a curve. There are two types of vectors on the curve. There are perpendicular vectors, or sorry, on a curve it's tangential vectors. On a surface there's perpendicular vectors. So first of all, I want to show what a tangent vector is. So for this curve, I will reference it in set one curve. And I'll just use evaluate curve component. Evaluate curve. And it's going to ask me to evaluate it at a certain parameter, right? The curve domain is basically, if it's not reparametrized, is going to be along the length of the curve. So I'm going to say that the parameter is, let's say, at 101 millimeters. Bam. Along the length. You can see I can easily move it, and I can even go beyond the curve here in this case, simply because it's how it's constructed. One thing that I would like to know is for evaluate curve is usually you don't use it with a regular parameter, but rather you right click here on the input of the curve and you choose reparameterized. What does that do? When you choose reparameterized, this little icon appears. And once this icon has appeared, then you're not dealing with millimeters, you're dealing with proportion. So now I can do 0.5, and that's going to be the middle of the curve. 0 is going to be the start of the curve, 1 is going to be the end of the curve. Clean and nice. So that's that. And the reason why I'm showing you evaluate curve is because it gives us the point, the tangent, and the angle. The angle we don't care about right now, point we don't care about right now too much, and the tangent is what we care about, because that's a vector, right? And I will just use vector display for the tangent, and the anchor is going to be the actual point, right? So I want to draw a vector from that point. And if I zoom, I can see a little angle, like vector sticking out here. It's too small, so I'm going to use the amplitude node, connect vector to it, vector here, and for the amplitude, I'll use like 50 or something like that. Bam. Now you have a proper arrow, showing it. Now if I drag the parameter slider, you can see that the angle changes. And the change of the angle is actually, it shows the tangent direction along any point of the curve that you want, right? So this is super useful for when you want to create something that is quite seamless and that connects seamlessly to a curved object. Really, really useful stuff. Alternatively, you could do, so this is like one. Let me group this, hide this. Alternatively, you can do, I'm just copy pasting it. I'm just going to delete a bunch of stuff. Just keep the curve. You can divide curve like that. Do the count of, let's say, 50 points. And along the tangents, you can increase the vector amplitude of the tangents to like 20-ish. And then vector display, get that kind of information along the whole curve. Again, right now it's pretty dry in terms of theory, but it's quite useful. It will become quite useful in the later stages. So just understand the tangential logic of the curve. Okay. Now, when it comes down to surface, let's internalize, and let's create a surface instead. Just 4-point surface really doesn't matter. 1, 2, 3, 4. flip F10. I'm just going to move it up. You might see the ISO curves. Anyway, all you care about is this kind of surface. By the way, if it looks funky, if it's all jagged and so on, in Rhino, you can just select it. Go to Properties, choose Custom Mesh, tick mark that, adjust, and then for the density, just choose like 1 or something. I think that should do the trick. That indeed did not do the trick. So let's test out smooth and slower, preview. No, that's pretty bad. 1 second. Density 1 and maximum edge to surface distance 0.001 millimeters. Hit OK. That should, okay, what the hell? Hello? Maximum angle 5, preview. Okay, that starts looking much better. Okay, 5, maybe 2. Yeah, that's not bad. That's not bad. So something like this, hit OK. And now your surface will be meshed properly, right? Will be shown properly. That's a usual issue that Rhino has when trying to display like curved geometry, is that simply the resolution at which it's meshing is pretty bad. Anyway, back here, I will reference in the surface as a surface component, set one surface, there we go. And this is going to be the first time when you will see what happens when you, well, actually you already saw this, but this is where I'm going to put attention on it. What happens when you reference in a surface in Rhino, and also I've just noticed that it's, anyway, it's going to crap the bed when it comes down to previewing the geometry, simply because there's 2 geometries in the same place. One from Rhino, one from the representation from Grasshopper. So usually what I do is I just, once I reference the geometry, I hide it in Rhino, and I only look at the geometry in Grasshopper. And you can see that the geometry in Grasshopper, even though we fixed it in Rhino, in Grasshopper it's still pretty crap. So I can go in here into this menu, and instead of low quality preset, I can choose high quality preset, which slightly helps out with the preview. Not too much though. I will not spend too much time making it pretty, because all we care about is just getting the geometry in here and creating a bunch of points on it. So I can do, just like I did evaluate curve here, I can do evaluate surface here, right? Bam. Which actually asks us for a point. It does not need a point, it needs 2 values. X and Y, right? X and Y value. So, or U and V value. So in this case, a point is not accurate. It's actually just 2 values, but the way of how we can construct it is by actually using either a point tool or a multidimensional slider. So that's one thing. I'll show you both variations of it. If I go for a point, or rather, sorry, construct point, like that, I can completely ignore the Z coordinate. I only care about the X and Y coordinate, and you can see since it's 0, 0, it already creates a point right here. I don't care about those. I care about the, about being able to freely navigate on the surface and find any point that I need. So I will create a slider of 0.5, just like here, a slider between 1 and 0, like that. And I will just simply connect that, connect one slider to X, connect the second slider, Ctrl+C, Ctrl+V, to Y. And now I should be able to, as I move this, I should be able to find any point. You can see it doesn't work. Why doesn't it work? Kinda does. But it really doesn't move that far. And that is because this needs to be reparameterized. Right now it's reading millimeters rather than proportion. So to reparameterize it, I just right click on the surface input here and choose reparameterize. And now that point that we are using can interpolate anywhere on the surface, right? Just like that. So that's one way with the construct point. Another way, I'm just disconnecting this, grouping this up, moving it to the side. Another way of how you can do it is if you go to parameters and you go to input, here you'll see multidimensional slider. If I select it, it looks like this. So basically it's a slider that generates 2 numbers, not 1. And I can use that, and then as I move this, I can move, you know, the point or the plane anywhere on the surface, right? And just to show you how it works here, you know, as I'm moving it, it generates a point at that particular coordinate. It generates a normal vector, that's the important one, at that particular coordinate, and it gives me the direction or the tangential direction at u direction and v direction. I'll show all 3 of these vectors for you just so that you kind of understand what's going on. And also it gives me a frame, which is a plane. I will touch on planes a little bit later. So now for the normal, I use exactly the same thing. Amplitude. I increase the strength of it because I know for a fact that the normal will be only 1 millimeter in length, and I'll give it an amplitude of 50. And I'll use vector display to actually show you the normal on a point, just like that. So what is a normal? That is a vector that is sticking out 90 degrees from any point on the surface. Oh, that's the wrong slider. See? It's always going to give us a perpendicular vector. This is super useful for when you have a bunch of elements on a surface and you want to move them as if you're offsetting them, right? When you want to move them away from the surface. Super useful. I will make the MD slider a little bit smaller, just so that it's not so much in the way. Okay, so that's that. That's the amplitude, and we group this up. There we go. And actually this needs to belong to the group. So that add to group, just like that. Now I'll just borrow the same surface in here. And I'll repeat the same thing as what we've done here with the divide curve, only that we will use for the surface, we will use divide surface tool. Divide surface will give us, you know, points along, not just points, also normals along the edge. Oh, apologies, I'm sorry. Hold that thought, go back in here. I showed you the normal. I didn't show you the u direction and the v direction. I need to show those as well. So that's the normal. The u direction is here, tangential along one way. V direction is here, tangential along the other way, right? So think of it x and y, u and v. Basically, x, y, z are global directions, while u, v, and w are local directions, right? So what was the best example? If I have a box, this box has its own x, well, actually that's x, y, and z directions, right? And currently they are aligning with the world's x, y, and z directions. But when I rotate the box like that, it still has its x, y, oops, and z directions, but now they are, you know, not aligned with world's x, y, and z, so they need a different name. And in computers and software, you just use u, v, and w then. So when you see u and v and w, you know that it's locked or attached to an object and it can rotate. When it's x, y, z, you know that it's global, that it's just from the origin of the world aligning with the world's coordinates or directions. Hope that makes sense. So now we're done with this. Now I promise we're done with this. And we move on to here, right? So I had the surface, I divide it up into points. I can increase the amount of points, 20 by 20, let's say, or maybe less, 13 by 9, sure. And I get a bunch of points, sure. And also I get a bunch of normals. The normals, just like here, I can use amplitude for the normals. I can use 50 for the amplitude, and I can use vector display. as an anchor. And you can see the, that the angle at which these normals are drawn, I guess. The directions of the surface at different points. What's the purpose? Well, for example, if I want to use CNR, circle normal, center normal radius, then I can say, and I want to place a circle that's aligning with the surface on these points, right? Then I can say, well, the centers of the circle should be the points, right? And let's say the radius is like 10 or something. 10 is a little bit too much. Let's say 8, right? All cool and all, but the circles are horizontal, right? If I were to hide everything, you'll see it better. The circles are in the correct place, but they are horizontal. This is where the normals kick in, right? Because then I can use the normals to align the circles to follow the curvature of the surface, right? Because suddenly the circles align themselves with the normals. So now if I hide that and hide that, you can see that this is becoming much, much cleaner, right? And now I have my my little circles. And then I can also use this information to, let's say, extrude these circles along what direction? Along the normal direction with a certain amplitude, because I need to give it a strength, right? Because if I just use the normal extrude like that, it's going to be locked to 1 unit, because that's the strength of these normals, 1. But then if I use the amplitude and I extrude, then they will be extruded by 50 units, right? And I can control the extrusion rate. Cool, huh? And that gives us the extrusion, right? So those are the, one of millions of useful things for why you need to know, understand the tangents and the normals. Okay. Group that. Internalize that. Internalize that. And hide that. So that's about it when it comes to vectors, right? Of course, there's much more to it, but most of it I think I have covered. Most of the bases I think I have covered, and vectors, let's say, will be beautiful pink color. That's, yeah, oh, great. Ooh, a little bit too much. I accidentally made this a default color. It is what it is. Right click, color, lighter pink, something like that. Okay. So that's vectors. Then when it comes to planes, it's quite a similar thing as vectors, except that it's like 2-dimensional, right? It's an object on which you either build things or on which you can move things around. So in Rhino, you are accustomed to the world XY plane. A plane has an origin, a plane has its X direction, Y direction, and it has a Z direction, right? And it follows a right-hand rule, which is basically, if you hover, or if you do this, thumb, this finger and this finger, right? If you do this and you have your, let me remember, oh no. Yeah. If you have your thumb and your Y, if thumb is X and Y is, sorry, if thumb is X and this finger is Y, then this finger is Z, and it shows that it's looking upwards. If it would be flipped and X is looking this way, Y is looking this way, then Z would be looking this way. Rhino, gang signs. Rhino is following the right-hand coordinate system rule. Programs such as Unreal Engine or Maya follow the left-hand coordinate system rule, which means that stuff that you export from Rhino into Unreal Engine will typically have its Y-axis flipped. and stuff will be mirrored, which is weird, but okay, I'm getting sidetracked. So a plane has an origin and two or three axes, right? X, Y, Z axis. So there are multiple ways of how you can define a plane. You don't need to define all three axes because two is enough for the third one to be calculated. And if I were to go to vector tab plane, here we have all of the different ways of how you can actually use the plane tool or create a plane. And why you would need to create a plane, that's going to be a completely another thing. I'll of course show you a quick example of where planes could be used, but for now let's just create one, right? So under plane there is this construct plane out of line, two lines. If you have a line and a point, you can create a plane, plane between 3 points, and so on. A bunch of different methods. So I will use the simplest one, construct plane, bam. And by default, it just creates a plane at origin 0, 0, 0 with x-axis aligned with x and y-axis aligned with y. If I were to, let's say, if I want a plane that is crooked, that's somewhere just floating, what would be the best idea for me to show you this? Let's say our origin is actually construct point. Boop. Our origin is actually 10 units along the x coordinate, 5 units along the y coordinate, and 11 units along the z coordinate, right? So the plane moves. That's the origin of the plane. And then for the x-axis, let's say I actually want to construct vector. That's only deconstruct. Okay. Let's go to vectors, vector x, y, z. Of course, it's not construct vector. Like that. Bam, that's our x-axis. And right now, since it's set to 0, 0, 0, it has no length. So this is just freaking out. It's not able to construct a plane. So for this plane to be actually constructed, I need my vector in x coordinate, let's say, to be let's say 5, right? So now it's, or actually it doesn't really matter if it's 5 or it's 55, or as long as it's not 0, right? So I just do 1 in x direction and 1 in y direction, right? So it's crooked like that. And you can see that even with me just giving it an x-axis, it rotates the y-axis by 90 degrees, and it interpolates where the y-axis is, and from it interpolates where the z-axis should be. And if I give it even the z component to this as well, like that, it's still going to, properly draw the x-axis, and then from it is going to figure out where the y-axis should go. So what happens if I also give it the same vector for the y-axis? Breaks, does not understand, right? But the moment I start denying some of the values for the z component or x component, it starts to correct itself and it starts to understand, try its best to align, right? This is like giving it, like locking it in so much is a bad idea, by the way. You should not. The best way is to actually have like a proper 3-point setup, and you know exactly that things are aligning properly for the construct plane to work. But for the sake of just training, this is, I think, good enough, so I'm going to keep it here. A much more convenient, I guess, way is when you use the, I personally enjoy using the plane between 3 points tool, right? Plane between 3 points, where it just asks me for 3 points. And if I just poop, 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 have these 3 points, point component, My vacuum cleaner just turned on. Wait, no. Okay, we're back. So where were we? Right. Creating a point component, right clicking, set multiple points, and just getting 1, 2, 3 in here. Then I will use list item to separate them out because this requires 3 inputs. List. This is first item on the list, second item on the list, third item on the list. Point A, point B, point C. Creates a plane for us. And you can see that, since this is the origin point and this is the X point, the X direction, that's pretty straightforward. But then how does the Y direction get interpolated? That's the question, right? If I move move the third point anywhere here, the Y direction is locked, right? Because it can only be 90 degrees from X, right? But if I move the plane or the point over here, the Y direction gets flipped, which is quite interesting. And you never see the Z direction, and I really want to show it to you. So what I'm going to do is, for this plane, I will create, where was I? I'm going to deconstruct this plane, deconstruct plane, bam. And I'm going to show you the Z axis. So Z axis, just like X, Y, and Z, Z is a vector, right? So I will use vector display on an origin with the axis, and it's very small. So of course I need amplitude as per usual. And for the amplitude, I'll use 50 or something. That's too much. And you can see that now, since X is looking that way, Y is looking that way, the Z is looking downwards. If I take this point and I move this over to the other side, the right hand rule, right? The coordinate system rule. Now the vector is looking upwards. The perpendicular vector is looking upwards. And the Z axis in this case is indeed the perpendicular vector. So that's also quite an important notion to have, is depending on where the Y vector is, or towards where does the Y vector look, the Z vector is going to look either up or down. That usually trips up students quite a bit at early stages of their learning. Okay, so that is the premise of creating a plane. And of course, as I mentioned before, there are multiple ways of how you can create planes. Some are trickier, others are easy. I kind of want to show you one example. For example, if you have a polyline, that's too many points. Let me do it again. 1, 2, 3, 4, 5, 6, 7. Let's say it like something like that. And that polyline is weird rotated, like so. And it's a little bit crooked. It's not, a little bit not planar, a little bit messy, right? Just slightly. Well, that's not slightly, but you get the idea, right? Just slightly crooked. Then to actually make a surface out of this, you can't use planar surface or anything like that in Rhino. So you kind of can clean it up in Grasshopper quite quickly. I will take this curve, reference it in, of course. Pop. I will get all of the points of the curve. So I need these control points of this polyline. So for that, I will use, you can either use explode, which gives you the vertices. That's cool and all, or you can use discontinuities. Discontinuity is basically where does the line change direction rapidly, right? So I prefer to use discontinuities. That gives me all of the points, right, along the curve. And then for these discontinuities, I will use a tool that's called plane fit, right here, plane fit. Fit a plane through a set of points. It does not tell me how many. It's just going to try and, do its best to fit the plane. Like that. Bam. A plane is now fit. And you can see that it's like in a weird spot. And I can Should I? Okay, I'll show you how you can move the plane into, the middle of this surface. It really doesn't matter where it is because a plane technically is infinite in size, just like a vector. It's just directions. So it does not have a size. I can even go one step further and show you. If you go to Display tab here, the top, Preview Plane Size, here you can change the plane size to whatever size you want. 200, sure, no problem. Now it's 200, right? And now, my little surface here or curve here kind of fits on the plane. But I tend to have them smaller so that they don't intersect too much, right? So that plane, even though it's located right here, it doesn't matter. It still has the same effect because it's just an infinite surface. With that being said, the representation of the plane can be moved. You can move it, right? And actually not just representation, you can, if you move the plane along its X and Y direction, wherever you want, right? The moving of the plane along its Z direction offsets it. And that's quite important. So I'll show you how to do that. And actually right now. So if I were to, let's build a little bit of a trickier system. First step, I want this plane to be in the middle. How do you get a middle point of the surface, right? Of this polyline? Well, you can use Polygon Center tool. Connect polyline there. And it gives you the vertex average, the area average, the edge average, and the area average. And I believe area average is, it can't calculate it because it's non-planar. Typically, I always use vertex average, the first output, which gives us a point, right? And then for this plane, I can use it to plane origin. Yeah, there we go. This plane origin tool. Plane origin, base plane, that's the plane that we have generated, origin point, the center point. Bam, that's it. Now this plane is represented on this center point, right? Easy as that. As you can see, I'm really quickly hiding things. It's just a habit. Once something works, you just hide everything to clean things up on the screen. Then for this plane, I want to be able to also move it along its z-axis, up or down, wherever I want, but along the z-axis, right? How do I do that? Well, I can take this center point that we have here, and I can move it, move it along some sort of a vector, right? And after it has moved, that will be the origin point of the plane, right? Right now, it's not good because it's being moved along vertical z-axis because that's the default movement of this move tool. So instead of using the vertical z-axis, I want the z-axis of this plane that we have created, right? I want this bad boy right here. So how do you get a z-axis of the plane? Well, that's the same way of how we got it here. We used deconstruct plane. I'm going to do the same thing here. Deconstruct plane. Bam, like that. Now we have the z-axis, and I'll use amplitude to define the strength of that z-axis. And I will actually, this time around, I'll create a proper slider between minus 20 ... 0 ... 20. Enter. Slider between minus 20 and 20, right? Connect that to amplitude and connect the resulting vector to the move. And now what you have is you have a plane that you can move up or down. Okay, why? Why? What's the purpose? Now, since we have a curve that is messy, right? And we have this plane origin, or this plane that is flat, and we want this curve to be flat, what we can do is we can project an object to the plane. So you can see here, the first one is project a curve onto a BREP. That doesn't work. A second one is project an object onto a plane. Excellent. That's what we want. I select it. Asks me for geometry. The geometry is our curve. Asks us for a plane. The plane is the, the new one that we have created, that we went through so much effort to create. Bam. And it just simply projects this non-flat curve onto a flat plane, making it a flat curve. And now I can use boundary surface to make it flat, right? Alternatively, I can also take the original curve and take the projected curve and merge them into one list. Let me make this bigger. Original curve, data 1, projected curve, data 2. Merge them into one list. You don't need to do this, merge them into one list, and then I can use loft to make a nice little loft between them. Okay. Sometimes when you make a bunch of nodes, when you use a bunch of nodes, when you use a bunch of functions, it messes up the address of the list. Don't worry about the address part. I will cover that in like an hour or so once we get into the data trees. Just understand that sometimes the list addresses, the names of the lists don't match up. And this is the case. In this case, that's the case. If I were to check with the panel what I get, you can see that I don't have one list. I actually have two lists. They are separated for some reason. And I have my referenced polyline curve right here as index 0, and my polyline curve that I have generated, that I have projected right here in this list as index 0, right? So there are two separate lists living in one merge. Why that happens? I understand why that happens. I don't understand why it wasn't coded out of the functionality, but it is what it is. A very easy fix. When you see this happen, and when you think that, well, clearly these two objects should just join up into one list, you can just right click on the result and you can choose to flatten. And that is just simply going to flatten it. Yeah, clearly flatten it. Makes sense, right? This is called like data tree manipulation, and we will get to that chapter as I said, in an hour or so. Before that, I don't want to dive too deep because it's, in my opinion, the hardest portion of learning Grasshopper. So that is going to be much later. For now, trust me, bro, it's going to be flattened here, and then suddenly the loft works, right? So now what I have is I have a crooked curve and a flat curve, and I am lofting between them. And with this amplitude, I can choose, what's the thickness, where do I, get the loft, as well as the surface here, I guess. The boundary surface and the loft, right? What's the offset, I guess. That's the how I should call it. So, of course, this is a much more complex version of what I wanted to show you. A much simpler version. Let me, this is complex. That's the original one. 1 second. And a much simpler version, I will just copy and paste this, and I'll delete a bunch of stuff. So you need the curve, you need discontinuities, and you need to fit the plane through the discontinuities. But then you don't really need a polygon center, you don't need to deconstruct it, you don't need the amplitude, neither you need to move it, because you already have the plane. All you need to do is just project it, and you don't need any of this, and you get your flattened curve, right? From here, from which you can create a boundary surface. Right? So you can create a surface from it. So this is just, to show you a few concepts, and the actually the real structure or the real definition is just here. It's much, much simpler, right? And that is how you internalize. That is how you can flatten out any you know, a little bit crooked curve, how you can clean things up. Hope that helps. Okay, delete those. So those are basically planes. Let me just check if there's anything else. Of course, you can rotate the plane along its z-axis. You can offset the plane. So instead of using this amplitude, you could use offset plane tool. Where is it? There it is. Offset plane. But then, you know, you still need to type in the offset distance. But all of this, boop, boop, boop. Yeah, all of these three nodes can be replaced by just simply taking the plane and then offsetting it by -5. And for now, that's it. For now, I don't really want to do too much. So I think we will stop with the planes here. Okay, one last thing. I promise. One last thing. If I have some sort of a surface, and I will talk much more about it a little bit later on, but actually, 1 second. Okay. Or actually, let's talk about it right now. I'm just changing my, there we go. I'm changing my notes so that I talk about it right now. Okay, intersections, right? Planes and intersections work quite well, and I will cover that a little bit right now. So, for example, let's say I have some sort of a shape. Boop. Circle, circle, oops. Circle, circle, and this is, let's say, smaller, and this is, let's say, squished, and this is, let's say, squished a different direction, and this is also rotated, and this is rotated a different direction and moved here. Whatever. Loft. Looks ugly, but that's fine. And capped, right? I have some sort of a weird ass looking shape, right? I can get it in here as a brep. Set one brep. You can just draw like 3 circles, loft between them, cap, and that's going to be exactly the same thing, right? I have it as a brep. I hide the original shape in Rhino. And then here, let's say I want to extract certain sections, you know, along the shape. I want to extract like ribs along the shape. How can I do that? Well, one way is to actually just create an XY plane. XY plane is the default plane right here. And move it up by series of numbers. So we move the XY plane up in Z direction, unit Z, by a series of numbers. So series, and I will say, well, first of all, let's check how it looks like. Okay, that's way too dense. So the step size is going to be like 20. Like that. It should start at a lower level. So it should start at minus, or I'll just use a panel for this. Panel minus 50 or something like that. Like that. Minus 50 was a little bit too much, but we'll adjust. And the amount of how many we use is going to be like, well, right now it's 10. Let's do like 20 just in case. Bam. Of course, it goes beyond now, but that's fine. So I have a bunch of planes, right? Then these planes, as well as this brep, can intersect. I can find intersections. So if I go to the intersect tab, under, is it mathematical? I think it's mathematical. Under mathematical, there should be brep plane intersection right here. I use it. Brep goes into the brep, plane goes into planes, go into plane, and it's complaining. Intersection failed. Of course. Intersection fails in places where plane does not hit the brep. And this is one of the instances where it actually works as expected, except that it's complaining really, really hard because it can't calculate any sections for these. So what I'm going to do is I'll reduce the count until it's happy with us. 15, 12, 11, okay, 11. After doing, after reducing, this is not complaining anymore, and I will hide all of the previous except the final one, and these are going to be the floor slabs, right? So I can, for these curves, I can offset them a little bit inwards, or actually, no, for this example, we stop with using it. We'll just use boundary surface, like that, extrude in Z direction. Or actually, we don't even need to use boundary surface, apologies. The curves can be extruded in Z direction by, let's say, 3 units. And then they can be capped. And we have ourselves floor slabs, you know, for that particular shape. And I can, since this is a parametric model, I can change the, I hate that it makes that sound. 1 second. Whoop. Like that. Maybe that's going to be a little bit better. Okay, so we can of course change the range of it, and now I can see that it's complaining again. Okay, fine. 21, not complaining anymore. Great. So this guy is complaining a lot. That's fine. So now for any shape that you have, you can create floor slabs easily. You know, generate floor slabs easily. Right? Of course, you know, in this case, the planes are horizontal because we're using XY plane, but you can use any kind of direction and make a slice, you know, of any geometry in any direction, because here under mathematical, plane can intersect with curves, with meshes, with B-reps. It can intersect with surfaces and so on. And also, of course, here you can do much more. You can intersect 2 pieces of geometry together and so on, right? If you're looking for Boolean operations such as Boolean union, Boolean difference, Boolean intersection, that is under shape. Here you will have your solid union, solid difference, solid intersection. So while in Rhino it's called Boolean union, difference, intersection, here it's called solid union, difference, intersection. Ask me why, I don't know. There's also mesh union, mesh difference, mesh split. That seems to work sometimes. Sometimes it does. Okay. So that is that with the planes, I believe. Just give me a second. I need to check. Yeah, for now that is it. Okay, we can move on to the next one. Okay, it's time to get on with the 3D geometry, or rather to start talking about geometry types and how you manipulate them in Grasshopper. So we will begin with meshes. Meshes is one of the 3 different types of geometry that you are able to operate with when working in Rhino, and as well, of course, when working in Grasshopper. So you have meshes, you have Nurbs-based geometry, B-reps, and you have sub-D geometry. In this chapter, I will cover meshes. So I guess we begin by me stating that meshes are the simplest form of 3D geometry representation, and everything that you see in let's say animations, for example, you know, just Pixar or whatever animations, or video games and so on, all of those geometries are meshes, simply because the geometry itself is very lightweight, and you can use meshes for multiple things. For you, two most important ones being, first, simulation. You can't really simulate Nurbs geometry that well because of the calculation times. Meshes are much easier to simulate, for instance, physics simulation. And the second one, complexity. When you need something to be super complex, for like a most basic example would be a clump of hair, right? If you need to generate a clump of hair, a bunch of pipes, if you will, if you were to do just a regular pipe tool, the computer would crash. So you need to optimize and use meshes for that. Meshes can be 3D printed when it comes down to, manufacturing them in some other ways, like CNC milling. There are certain limitations, but recently they have been kind of worked on, and now it seems to be a pretty solid type of geometry for manufacturing as well. Okay, so enough blah blah blah. Meshes consist of 3 major components. They have, or actually I'll write here, scribble. They have vertices, vertex. They have edges, and they have faces. And basically the edges, when it comes down to actually kind of working with the mesh or constructing a mesh, edges are just simply a byproduct of faces being constructed from vertices. What do I mean by that? Let's say you have, let's say you have 1, 2, 3, 4 points in your Rhino window, right? And I'm going to draw the same points in Grasshopper. Come on. Oh, with the drawing tool. 1, 2, 3, 4. 1, 2, 3, beautiful, 4. Okay, so I have these 4 points here, right? And those are vertices, right? And I can then define that a mesh should be created, a mesh face should be created between points 1, 2, 3, and 4. If I were to define 1, 3, 2, and 4, it would create, let's do a red color here. If I were to define 1, 3, 2, and 4, it would create a face like this, which is no go. But if I define it correctly, 1, 2, 3, 4, then it gives me a proper mesh face. A mesh face should be a triangle or a quad, a 4-pointed surface, right? It technically can be an n-gon, meaning a pentagon, a hexagon, a heptagon, an octagon, and so on. It can be that, but the topology of a mesh then gets a little bit fucky-wucky, and we don't want to deal with that. So at early stages of your learning, just think of mesh equals a collection of triangles and rectangles representing some sort of a 3-dimensional form, right? So let's create this from these 4 points. First thing that I need to do, and these are vertices, and this is a face, and this is, of course, an edge, right? So the first thing that I need to do is I need to reference in these 4 points. Point, right-click, set multiple points, 1, 2, 3, 4, enter. We have our points here. Oh, you might, at this stage, once you have a lot of points, it might become a little bit tricky to follow which one came first, which one came second, and so on. So you actually can number them, by the way. You can use a point list tool to get the points in here, and then for the size, this is just the size of the text, you can define, whatever, 10-ish, a little bit more, 12, And now you can see exactly, this is the first one, second one, third one, fourth one, 4 points. Okay, so now what do we do? Wait, I'm going to cross the wires, but in the long run, this is going to be a little bit cleaner. Now to construct this kind of a face, we need to use, we can go to the mesh tab, and here under primitive, we can choose the first item on the list, construct mesh, which asks us for vertices, so the points, easy, and immediately it gives you the face, right? well, a single mesh face. And why? Why does it happen? Well, that's because the faces input is already filled in with an instruction. So the instructions are as follows. Well, you can clearly see it now. Q and in brackets 0, 1, 2, 3, right? I can write it as well. Let's move this down. I can write it as well in the notepad or in the panel here. Q in brackets 0, 1, 2, 3. Connect, and then it creates a quad. Q means a quad. If I were to say T 0, 1, 2 without the 3, because T is triangle and it can only use 3 points, then it's going to create a triangle between these 3, right? Q creates a quad. 0, 1, 2, or actually if we do 0, 1, 2, then it's still going to create a triangle, honestly, but it's going to think that it's a quad, so don't do that. If you're specifying Q, then give it 4 points. But what we can do more is if I then add one more point in here, then I can clear values here. Clear values means that we remove the referenced points from here. Set multiple points, and then I can do 1, 2, 3, 4, 5, right? And now I have one more point here to play with. And what I can do is I can say, well, right click, multi-line data. First of all, this should be multi-line data. And then I can make another line here and say, actually, give me one more triangle in brackets, and in between 2, 3, 4, like that. And see how the shading became a little bit weird? That is because this mesh face is defined clockwise, while this mesh face is defined counterclockwise. So they don't like that. You need to choose either clockwise or counterclockwise. If I now change this from 2, 3, 4 to 2, 4, 3 clockwise, right? Now the shading is fine. It's displaying everything correctly. So this is another thing that really messes up people, is the clockwise versus counterclockwise. And for instance, now if I were to just move this point up and to the side like so, I can then build up a 3D shape from these points, right? Give me another triangle. We're doing clockwise, so 0, 4, 3. Bam, I get a triangle here. Give me another one. Or actually, we can build it up with a quad. Actually, 2 triangles, better. 1, 4, 0, and then one more triangle, 2, 4, 1. And that's it. Now we have ourselves a pyramid from, well, not necessarily a pyramid, because I can start messing around with these guys right here. But you get what I mean, right? We have a set of points. That's one list. And then the second list is a set of instructions on how those points should be connected into a mesh. And the nice thing is that also a mesh can come with colors, but we'll do that later. Let's not focus on the prettiness just yet. Okay, so that's that. Then when we have a mesh, we of course can deconstruct it. Deconstruct mesh. And we can deconstruct it back into vertices, faces, but this time also normals. So what are those normals? If I were to check, it gives me 5 normals, and I have 5. Actually, that's interesting. It gives me 5 normals, but those are probably not face normals. Those are probably vertex normals. Because I have 5 vertices, I also have 5 faces. Give me a second. If I delete one of the faces, it's still 5 normals. Okay, so it does give me Control Z to get back that face. So it's not a normal of the surface of the mesh, but rather a normal for the point of the mesh. So let's check those out. Vector display. Anchoring on the points, showing the vectors, much more strongly. Amplitude. Let's go for a 10. Let's go for 100. There we go. And those are the normal vectors that it gives us. What the hell are we looking at? There's no way. Oh. I'm sorry, give me a second. Thinking. That just feels like... No, it's weird. Okay, abort mission, abort mission. We don't use normals from here because they're yucky and weird unless the mesh is actually broken. Let's take a look. The mesh is actually broken. Unify mesh normals. Okay, so us creating the, us not aligning the mesh properly messed up the normals of the mesh, not aligning the instructions of the mesh properly, messed up the alignment of the mesh. Apologies for that. You can always use unify mesh normals, unify mesh right here, get the result in there, and then the normals start making a little bit more sense. Apologies for that. I forgot that it's not just clockwise or counterclockwise. You actually also need to align the, you know, what's the starting vertex here as well if you want a clean mesh. But this unify mesh node just makes sure that all of the points start from the correct sequence. Sorry, the instructions start in the correct sequence, and thus, you know, it cleans everything up. Anyway, back to where we were. This unify mesh cleaned it up. We get to deconstruct the mesh and we get to see the normals of the vertices. So it basically just catches the average normal of 3 faces that surround each vertice, except for vertex number 4, because vertex number 4 is surrounded by 4 faces and not 3. But it's still an average direction of all those 4 directions, right? So if you want to actually just get the direction of the surface, the normal direction of the surface, you can always go to analysis and use face normals tool. Face normals, we get the mesh in here, we get the centers, we get the normals, and I'll use the same Ctrl+C, Ctrl+V, the vector display and the normals right here. And then we get the face normals of the mesh. And again, that is going to be very useful in the future once you start creating stuff on the meshes and you will need to move that stuff along the mesh faces, right? So that's it for this portion. All right. So what else can you do with a mesh, right? If we go into the primitive, there's of course, you know, you can just construct a mesh plane, mesh sphere, and so on. Those are pretty simple, but I honestly, unless you of course need to, but I honestly would suggest if you need to construct primitives, then construct them in Rhino, because you have a little bit more control over it. And in Rhino, in the mesh tab, mesh tools tab, of course, you will mesh creation, you will have all of the possibilities here. And while we're at it, I'm going to internalize data here so that I can delete these points. And I'm just going to quickly create one mesh torus, like that, and one mesh sphere, like that. And I'm going to make them overlap, just like this. So you're probably used to meshes, or sorry, Nurbs geometry, Boolean difference, Boolean union in, you know, with Nurbs geometry. Meshes can do that as well. But in my experience, which might be, this is very anecdotal, so it might not be true, but simply from my experience in using meshes, Grasshopper's mesh Boolean, mesh difference works much better than Rhino's. Might be a tolerance, apologies, might be a tolerance thing, I'm not sure, but it just seems to work much better. So the way you use it is if you reference in mesh 1, set 1 mesh, bam, mesh 2. These are just empty mesh containers. Set 1 mesh, bam, you know, 1 and the second are now selected. Now I can hide them in Rhino. And then if I go to intersection, tab, shape, and here I have mesh difference, mesh union, and so on. So for instance, mesh difference, right? From mesh A, remove mesh B. Hide the inputs, and that's the output that you have. That seems to work quite nicely. Then we have, of course, mesh union, the first one, and the second one should be connected, hide the mesh difference, and these seem to be connecting also quite cleanly. This works only for closed meshes, of course, meshes that are watertight, that don't have any openings and are enclosed geometries, because then Rhino or Grasshopper can understand what's inside and what's outside. And also it tends to work only with meshes that have a low polygon count, right? Once you get into the millions, it doesn't really work that well. So then you need to use different kind of approaches that I will teach you later, right? So that's like mesh union, mesh difference, and last one, mesh intersection. Mesh A, mesh B, and we get the area that intersects between the two. Show selected. Oh, I have a bunch of hidden stuff here. And let's go for wireframe view. And you can see now as I move the sphere around, it trims out a portion of the shape. So that's neat. That's nice. Okay. So if you want to create some sort of a unique shape, usually, that is one way of how you can do it. Keep in mind, as I said before, low resolution works, high resolution doesn't work. So this is one thing that's like mesh operations or solid operations with a mesh. Another thing is, I already mentioned this, but if you have a network of curves, or actually, apologies, I believe that mesh pipe is only available if you have a plugin, and we will learn about plugins in the plugins chapter of this course. So for now, I skip over it. Sorry. Okay, what else? Okay, I think one more to show you. I will create, under primitive, I will create a mesh plane, which basically asks me for a boundary, which is a rectangle, right? So I can just draw any kind of a rectangle here, reference it in as a curve, set one curve, bam, that's my boundary. And it asks me, okay, well, how many divisions do you want in X and Y direction, right? So for now, it's 10 by 10. I believe it's 10 by 10. Yeah, 10 by 10 is fine. I will keep this as a default. I get my mesh. Then, remember we talked about that there are vertices. So I can extract the vertices of the mesh by simply using the deconstruct mesh tool, deconstruct mesh, which gives me the vertices as points. So these are points. It gives me faces, but it gives me faces not as surfaces, but rather as text. It gives me the instructions. And then it gives me colors that are none right now, and normals that are vectors. Right? Like this. So from deconstruct mesh, from these kind of components from which a mesh is built, I can only get the point component, right? I can only get the vertex. How do I get edges? As lines. And how do I get faces as surfaces? Good question. Under analysis, you can get mesh edges right here. Mesh edges, which extracts all of the naked edges, all of the interior edges, and all of the non-manifold edges. Let me guide you through it. Naked edges, curve, are all edges. You can see me, now it's highlighted green. They go along the perimeter. Naked edges are basically all edges that are not surrounded by faces, right? So this edge is only surrounded by a face on one side and the other side is empty. This edge, one side, other side is empty. This edge, this edge, this edge, this edge, this edge, this edge, right? These are naked edges. Interior edges are faces or edges that are curves that are surrounded by faces, right? From both sides. So taking this again, we have this one is surrounded on both ends. This one is surrounded on both sides. This one is surrounded on both sides. And this one, right? Those are all interior edges. And the non-manifold edges are bad. Always bad. A non-manifold edge is basically, if I were to, do I model? No, I'll draw. Let's say you have one mesh face right here. You have a second mesh face right here. And then you have a third mesh face right here, going up, right? So then this edge right here is sharing or is being surrounded by three faces. This is a non-manifold edge, which makes it so that the mesh cannot be, the front side and back side of the mesh cannot be calculated. The volume of the mesh, well, technically cannot be calculated. And also you can't offset the mesh without having it self-intersect. I can try to explain it right here in Rhino a little bit better. If I were to go to my mesh tools and I were to go for mesh creation and I just create one little mesh face here, and I will do another one, and then I will do one more. Okay, bear with me for a second, and I move this up. And it's very crooked, just like that. And we change to shaded view. This is what I drew, right? This edge right here is a non-manifold edge, right? So let me explain. Now the front faces of my mesh are colored in gray and the back faces are colored in red. So here it's fine. And usually you want, all of the gray to be on one side of the mesh and all of the red to be on the other side of the mesh. This face messes it up because suddenly we have a red color here that connects to the gray color. So back face connects to the front face. If I want to offset, and if I flip it, by the way, then here it's fine, but then, again, here it's bad. There's no arrangement where this works, right? If I were to offset this mesh, you can see how it's self-intersecting no matter what, right? Simply because it cannot, I offset it downwards and it makes something like this. Looks great, but then I look at the surface here and it's just a shit show. Apologies for my speech, but it's just bad, right? So it's all self-intersecting and all really, really messy. So you don't want that to happen. So never have non-manifold edges. Easy. If you see one, delete that face and rebuild the mesh with new faces. Attach new faces that don't produce non-manifold edges. Sorry for extending here, but this is important. So I wanted to spend a little bit more extra time. But with that being said, we have our naked edges, we have our interior edges, and you can use them in tandem as well. You can just, wait, can we, I'm struggling here a bit. Can we just merge? You can just merge interior and naked, and now you have, as a result, you have all of the mesh edges, right? Okay, and the last one is under how to get the faces themselves. So under analysis, there is this mesh explode, decompose a mesh into its faces. Bam. And now I have a separate mesh per each face. That is if you want to get, like a separate entity here. And then you can do like a weird thing where you take all of the faces here. 1 second. You take all of the faces here and you deconstruct them. Wait, do you, sorry, you don't deconstruct them. You use edges. Or actually, I'm jumping around. You do deconstruct them. Deconstruct mesh, because then you get 4 points per each face, and then for these points you can actually 4-point surface. 4-point surface. You can create a surface from 4 points, but for that you would need list item, because here they come as lists of 4 points. So here you would need to 1, 2, 3. Separate them out to point 1, point 2, point 3, point 4, corner A, corner B, corner C, corner D, and now you have a bunch of surfaces, right? If I were to bake this, these are now Nurbs surfaces. So there are ways of how you can convert a mesh back into Nurbs, but usually it's very, very heavy and you shouldn't do it unless you really know what you're doing. All right, so for now I'm going to have this deleted so that it's, you don't get the wrong idea. That's one way of how you can get faces. If you don't need the meshes themselves, if you just need the perimeter, you can always do face boundaries tool. You can always use face boundaries like that. And it gives you basically a bunch of polylines, right? Separate polylines, separate rectangles that you can work with. Okay, so those are mesh components. Let me group that. Let me internalize the curve. All right, what else is there? Of course, you can measure a mesh area, you can measure a mesh volume. Actually, I kind of want to show you this. I want to show you a few things. A brep, a Nurbs polysurface, can be easily converted into a mesh, very easily. A mesh cannot be easily converted back into a Nurbs polysurface simply because Nurbs has much more information than a mesh does. In the next chapter, I'm going to teach you about Nurbs. For now, it's just meshes. So when you are converting Nurbs into mesh, it's almost like a destructive process, right? Because you're getting rid of information and you're rebuilding everything out of triangles and quads, if you will. And I can showcase that quite easily if I just I'll grab this shape right here that we used. I will get it as a brep in here. Set one brep. Actually, I internalize, why not? And then delete it. Does it choke out? Okay, it's choked out here. 1 second. Internalize that. Okay, now I can delete it. Okay. I'm internalizing too much, it's going to freak out. But that's fine for now. Okay, so this brep, how do you convert it into a mesh? The easiest method is to just simply run it through the mesh component. And it automatically meshes it. Let me hide the brep, and you can see all of the quads and triangles that it created, that it made to create this mesh. Easy peasy. Not a lot of control though. You're just basically just praying that it's going to have enough resolution. A much higher degree of control is to actually use a mesh brep component, mesh brep, with custom settings. Custom settings, or settings custom, like that. By the way, I'm sorry, if you don't actually see the edges, you should, but if you don't see the edges, you can always go to display, preview mesh edges right here, right? Display, preview mesh edges shows you the edges of the mesh, shows you those lines there. So now the settings, the mesh brep settings. Let's move this to the side a bit, this right here. First one being stitch seams. We don't care about that. Okay, I'll just go for the important ones, okay? Basically the maximum distance and maximum angle. are the two important ones. Maximum distance is how close should the mesh be to the original surface. If I specify actually only 1 millimeter for the max distance, it's going to be very lenient with, you know, how it meshes this. But if I say 0.001 millimeter, it's going to make a much higher effort to be precise, right? So maximum distance is basically how you control the density of the mesh and how you control the precision of the mesh, right? That's step one. Maximum angle, it's basically what's the maximum angle that you can have between two faces. Usually, you know, if like 5 degrees or 2 degrees, it really depends. I'm sorry, but it really depends on what kind of a geometry you're dealing with. In this case, maximum angle, I'm choosing 1 degree, right? So you can see how dense the mesh just got. But if I were to bake this in, again, I use the insert key, and if I were to look at it in the Arctic view, you couldn't be able to tell the difference between a mesh and a Nurbs poly surface. The resolution of this would be immaculate, right? So those are basically the two main inputs that I use for meshing, a brep, and that gives me a much higher level of control than just simply running it through a mesh component. There is a third version, a third variation, I should say, which I will do, I think, something like this. It's called quad remesh. It's a new, well, not new anymore. It's was created in Rhino 7 for Rhino 7 quad remesh algorithm, which basically takes, it actually asks you to give it a mesh in the first place, but we'll just give it a brep, see if that works. Yeah, it worked out. And it does its best to remesh the geometry to be only made out of quads. And as you can see, it does a great job at it. Most of the time, it's pretty good. And then here, it does have its own settings, so we can quad remesh settings. We can get those. We can connect those. And in these settings, I would honestly suggest that you first just start with target count. This is how many faces you want. So if I say, well, try to do it in 50 faces. I mean, it tries, right? So it tries and it does it, but it's not a great output. But if you give it like enough, let's say 500 faces, you know, it's starting to get there. 5,000 faces. That's pretty good, right? So 5,000 faces with insurance that this is going to be a quad mesh. You can see that it's you are sacrificing certain things when you are quad remeshing, but it is what it is, right? You can't have it all. There are guides that you could use to sharpen this up, but for this particular course, I will not be showing those because time is of an essence. So those are 3 ways of how you can convert a brep into a mesh. I hope that those will help you. Actually, while we're still here, I will do one more thing with this. So under analysis, you have mesh area and mesh volume. So for anything that is closed, such as this mesh brep, you can calculate its volume, right? So I can go for analysis, mesh volume, connect that, and it gives me a number for the volume of the shape. But more importantly, it gives me a centroid. What's a centroid? It's a point. It's a point that is right in the middle of my mesh shape. You can also, by the way, calculate a volume of a brep in this exactly the same way, and it's going to give you the centroid in exactly the same place, right? A volumetric centroid. So sometimes for geometry, it's quite important to find the central point of the geometry, and that is how you do it, is you just use mesh volume. There are different ways you can get all of the vertices, and technically the average of the coordinates of all of the vertices is also centroid, but that is vertex average centroid rather than volumetric centroid. So those will not match up. So I'm not going to show you that. Instead, for now, volumetric centroid is how to get the center point of any closed, of course, shape. Add to group. There we go. 1 second. Yeah. Oh, mesh inclusion. Okay, this is going to be an interesting one. So for this mesh that we have here, let's create a grid of points around this mesh in X and Y and Z, a three-dimensional grid of points in X, Y, and Z direction, right? It's very easy, by the way. You just create a point, or actually, let's reference in the point. Boop. Point. Come on. Point, right click, set one point. There we go. Immediately, I'll internalize it. And we will just use box array for this. There's an array, linear array, which copies a thing along a line, right? There's rectangular array that copies a thing along two lines, so populates a surface with a thing, and box array, which basically copies a thing in 3 lines or populates a volume with it. So I'm going to use a box array, which asks me for, what do I want to array? That's my geometry, that's my point. It's going to ask me for what's the cell size. And cell size is basically, it asks me for a box that has X, Y, and Z size. So it's from it will know the step size in X, Y, and Z direction, right? So if I were to create a box, what's the easiest one? Let's do a domain box. Yeah, let's do a domain box. The base doesn't matter at all, but X, Y, or actually let's connect point to the base so that we create the box in here. And here I'm just going to write what's the X size, the Y size, and the Z size. So in X, let's say it's 10. In Y, let's say it's 5. And in Z, let's say it's also 10. Something like that. I create a box and then I use it as a cell, right? So immediately it knows, as it's copying in X, Y, and Z direction, this box array, it knows exactly by how much should it copy, what's the step size. And I can now control it fully, right? So that's nice. And then for the count, I'm just going to do 100 by 100 by 100 is 10,000. So let's do that. I'm going to create a number slider, 100, and I'm just going to use it for all 3 of these inputs, thus creating 10,000 points. That might have been a little bit too much. Let us reduce 50. Oh, the sound is back. Ew, go away. Okay, should be good. So 50 by 50 by 50, that seems okay. Or actually even less, 30 by 30 by 30. And then I can take that point and I can move it wherever I want to, completely engulf the structure, or not completely, but to intersect with the structure as much as I can, like that. Okay, so I have my point. I array it into this 3-dimensional array, right, of points. 27,000, wait. Oh crap, 100 by 100 by 100 was not 10,000. 100 by 100 is 10,000 and then 100 more. That's why it was crashing. Anyway, moving on. 30 by 30 by 30, 27,000 points. Yeah, makes sense. 27,000 points, and then we simply want to delete all of the points that are outside of this shape, right? So how do we do that? Well, we have our array of points, we have our mesh, and for the sake of clarity, I'm just going to create a mesh component here, and I'll connect our mesh brep to this mesh component so that I can just simply drag it out and hide this, and continue on the script here. It's just method for cleaning up the script, making it a little bit more readable. Okay, we have our mesh, we have our geometry. I need to delete all of the points that are outside of the mesh. What's the tool? The tool is called mesh inclusion. This one right here. Test a point for mesh inclusion. Bam. We have a point, or we have multiple points. We have a mesh. Immediately tells us if the point is inside or outside. So it gives us true or false statements. Scroll, scroll, scroll. Where was it? I know we did it. Where are you? True or false, true or false. Distance, remap numbers, cap holes, larger than, there we go. That was also true or false statements, and we used dispatch, right? We're gonna do exactly the same thing. Dispatch. What's the list? The list is going to be our points, right? So we're dispatching from our points. Actually, I should probably just have it here. We're dispatching from our points, and the matrix that we're using, or not the matrix, sorry, the filter that we're using is if it's inside or outside, the true or false statements generated by mesh inclusion. Bam. Now we separate the points into two lists, one that are inside, one that are outside. How do you know which one is which? Well, we just create a point component and we connect it to list A and we select it. And then the green ones are the ones that are in list A. They are inside. That's the one that we need. I will hide literally everything except the final node. Now I have a bunch of points here, right? And I could create, what do we do with these points? We could do Minecraft, right? Because the step size between the points, well, in this case, the step size is yucky. So let's do a proper 6 by 6 by 6 step size between these points. And then I can just create a box. Can I do a mesh box? I'm not sure if you have mesh box available without a plugin install. Just in case, I'll do a simple box. This might crash some of your computers. I'm sorry. Domain box. The points are the bases. And the XYZ size is the same thing as here. So it's going to be 6. 6, oops. My bad. 6 by 6 by 6. Congratulations, Minecraft. Insert. Wait for it to bake out. It's gonna take a little bit of time. Arctic view. That's how you voxelize. And for this, I would never use, and by the way, all of these are separate entities, separate boxes that you can simply, that was upside down. You can just move out and, you can work with them. I would never use a Nurbs polysurface for this, for the actual geometry, but since I don't know if you have mesh box component, mesh box, this bad boy right here, since I don't know, I don't know. I will not be using it for now. Okay, so that's the second iteration of this script. Let's think. Okay, analysis. There's a mesh closest point component. That's whatever. Under utilities, we have mesh surface, mesh from points, color faces, delete faces. I've noticed that some people try to use mesh join, this node right here, to instead of mesh solid union or whatever it's called. Mesh union instead of this one. So if you want two meshes to merge into one shape, you use mesh union. If you just want two meshes to join into one shape, that's such a bad example. 1 second. Let's create mesh tools, mesh creation, sphere. Sure, sphere. 2 spheres, right? Mesh. Right click, set multiple, pop, 2 of them. connect to mesh union, connect to mesh join, right? What's the difference between these two? Internalize, data, delete. Okay, let me bake out mesh union, move it here, further away, and let me bake out mesh join, move it here, right? The difference between mesh join and mesh union is if I, oh my god, clipping plane. If I clip through this, you're going to see it better. Mesh union actually unifies the shape into one shell. Mesh join actually is just able to join the two meshes together into one shape, but they are not unified, right? They are still like two different entities. And in Rhino, I can even, after I've baked it out, I can use split disjoint mesh, and it splits them back apart. While here, if I use split disjoint mesh, unable to split this mesh, there were no disjoint components. These have been completely unionized. That's the wrong word, but I'm sticking to it. So mesh union, mesh join, two completely different tools. Make sure that you use the correct one. Also, if, for instance, one of the meshes is open, or even if both of the meshes are open and I clear values, set multiple meshes, then mesh union should not, oops, my bad. Then mesh union should not work, but it does. What the hell? Okay. Well, that's an update and a half in Rhino 8. That's nice. So for simple openings, it still is able to union the two meshes together. That's cool. It used to not work. Never mind. That works. Okay. Still, mesh join, mesh union, two very, very different objects or tools. Apologies. Different tools. Where does this go? This can go here. Okay. Oh, what else? What else? What else? What else? There are ways of how you can create a mesh automatically from a set of points. So if I were to just create a bunch of points here. Come on. Imagine you get the landscape from a survey, and usually the landscape from a survey has a crap ton of, well, actually it has a crap ton of isocurves. Give me a sec. Okay, usually when you get a bunch of contour lines from the municipality or whatever, they come in a DWG format and they come in as polylines, just like that. And to be honest, usually not that clean. They don't have, proper amount of points, and they are kind of jagged and they break, but that doesn't really doesn't matter. What you can do is you can select these contour lines as long as you have already moved them, or they have been moved by the municipality workers or the surveyors to the correct altitude. You can get them in here, and you can, I'm just gonna use, probably I should do it here, curve, right click, set one curve, or set multiple curves, apologies. It really doesn't matter which one comes first or which one comes last, but just generally we just reference in all of the curves here. We get their discontinuities. Apologies. We get their discontinuities, and you can see that it doesn't catch all of the discontinuities. So for instance, here it's like missing the mark. It's not catching the points there. So to force points to be caught there, you need to adjust the level of the discontinuities. And you can see that if 1, it's curvature 1, or 2 is curvature 2, second grade, and 3 is curvature infinite. I think it's C is for curvature, I'm not sure. But either way, if you just change this from 1, right click, on the level, right click, and you use C infinite analytic, it will always give you all of the points for the discontinuities, except here for some reason. Hello, curvature, tangency. Okay, analytic, sure, whatever, right? It gives you all of the Even the slightest curvature gives you a point. So now what do we do with these points? Well, first of all, this is another one of those trust me bro moments, because we still haven't reached the data management or data tree chapter. I can't really explain it to you properly, but we need to push all of these points to be in one single list, because currently they are separated into separate lists that correspond to separate curves, even though they come out as one in one output, right? So what we do to force them into one list is we right click on the points output and we choose to flatten again, flatten. It gives us the small little arrow looking downwards. Once the data has been flattened and everything has been moved into one list, then we can proceed to create a mesh. And creating a mesh here is would be pretty tricky. You would need to, loft here, and then you loft here. But then what do you do when you have a closed curve and an open curve? You can't make a loft, so you would need to start exploding. And here it's making a little bit of a mess with the twisting. You get the drill. So instead of that, we go for triangulation, and we use Delaunay mesh. This bad boy right here. We get that in here. Asks us for only two things. Give me the points, give me the plane for where I should kind of fit the mesh onto. The plane is horizontal by default, XY. We don't need to change it. The points, well, we have the points. Bam. That's it. Makes a mesh for us. We have ourselves a landscape. There it is. If I were to bake this in, it's fine. It's kind of accurate. It generates a landscape according to, what kind of the accuracy of the contour lines that you gave it. The edges are usually a little bit messy, but that's fine. You can always trim those away. But the landscape seems to be okay. If you want to continue cleaning this up, I would strongly suggest using quad remesh. Like that. Remesh settings. Quad remesh settings. Like that. And giving it a proper quad count. So in this case, it's set to 1,000 quads, which seems to be quite good. And now if I bake this one in here, this looks much, much cleaner, much nicer. I can force it into, well, actually, let's not. Let's stop here, right? So that's how you clean up, and that's how you quickly construct a landscape from a set of curves. You're welcome. Should save up a little bit of time for you. Of course, since this is a mesh, there's still to make it into something that can be used for Boolean difference and so on operations. There's still a few steps, but the basics are indeed there. Okay. That's it. For now, that's it with the meshes. There's nothing else to specify. I think we are kind of done. I want to do something like this, I think, and then place this somewhere here. Yeah, that's going to be compact enough. I'm now going to spend a little bit of time naming all of these, and then we will continue on with the next chapter, which is going to be Nurbs. All right, so Nurbs. When it comes down to Nurbs-based geometry, well, as I mentioned before, in Grasshopper, it's called B-reps or surfaces, right? In Rhino, it's called poly surfaces or surfaces, same thing, Nurbs. It's basically a type of geometry that is infinite in its resolution. What do I mean by that? Well, we learned about meshes and that they are made out of these points, vertices, and those points are assembled into faces, and thus you get the shape of a mesh, which means that if I now really quickly just create any kind of a mesh, if I zoom into it, it has a finite resolution, meaning that just looking at it, from here, I can see the jaggedness of it. And of course, you can change the resolution of the mesh. So for example, if I say it should be 50 by 50, now it's much smoother, but still, if I zoom into it, I can see, you know, individual elements. So it's like, think in Photoshop, you have pixels, right? It's finite in its resolution. Nurbs is not finite. Nurbs is infinite, which means that it doesn't matter how close you zoom in, it's always going to be perfectly smooth. You know, a surface is going to be perfectly smooth. And I can showcase that by creating a sphere, or rather, I can't really showcase that, because if I create a sphere here in Rhino and I zoom into it, well, it's doing a pretty good job of displaying it, honestly. But remember our example, wait, maybe I'll do this instead. My example with the surface and the 2 control points, by the way, F10 to get the control points of the surface and pushing them up like that, and how jagged this is and how messed up this is. We can also do extract render mesh. You can use extract render mesh to actually get the shape that is being currently displayed, which is the render mesh. So what the hell? Why can we extract a render mesh from a Nurbs polysurface, or Nurbs surface in this case? That is because if geometry has infinite resolution, then the resources required to show that geometry are also infinite, right? Because you have infinite amount of points that you need to display, right? And that you need to calculate. So what happens is in Rhino, and honestly every other software as well, is that under the hood, the Nurbs surfaces, Nurbs polysurfaces are being meshed. A mesh is created from them and presented to you visually, right? So their visual representation is always a mesh. I think with an exception of the wireframe view, where the visual representation is just the boundary curves as well as the ISO lines. Right, so, and as I already showed you in previous chapters, you can control this mesh by just simply selecting the shape, going to properties, going to custom mesh, tick marking that, and saying that, yo, I want to adjust the mesh here, and just saying my density should be 1, and the maximum edge to surface distance should be 0.01 millimeters. Preview. Hello, preview. I think we had the same problem before, right? I think it was the angle. So let's go for 5. Why are you not doing anything? Hello? Every time I try to show something to you, it's always messy. Okay, smooth and slower, preview. That's better. Density, that's fine. Minimum edge length, maximum edge to surface distance is 0.001. Okay. Give me a second, I'll figure this out. Oh, sorry, I didn't need a second. You just go to adjust, and here the maximum angle, that was the culprit. I was not changing it. So here, if I changed it to just like 1 degree, you know, so between 2 polygons that are being created, the maximum angle between them can be 1 degree. Hit preview. Makes a much cleaner or much denser mesh where it needs to, clearly. We hit OK. And now the surface is presented to us in a much cleaner appearance, right? So that's the premise, that's the idea. Nurbs polysurfaces, or Nurbs surfaces, Nurbs geometry is infinite in resolution, and the only way to show it is by meshing it, right? To showcase it. But all of the calculations, when you're evaluating a point on the surface, when you're creating stuff along the surface, when you're using Boolean operations and so on, all of that is made with infinite resolution in mind. And the question is, well, how can you make infinite resolution calculations in the first place? Well, that's because while the mesh is calculated through points and the connectivity between the points, the Nurbs geometry, or BREP, or polysurface geometry, is calculated through f2x equals sinus x plus 15, and then all of that gets clamped in some sort of a range, thus you get a curve, right? A sinus curve. And then you have another function, f2x sinus y, you know, in another direction, right? So you have like two functions together and they're clamped into certain ranges, and then you interpolate a apologies, you then can interpolate any point within that range. So what I mean by this is you don't really need to understand this. It doesn't really matter, but it's basically a mathematical formula. And the mathematical formula, first of all, gets really heavy computation-wise. Second of all, it is infinite because you can insert any number to the x, right? There's infinite amount of numbers that you can insert to x to evaluate it, meaning that, you know, amount of points that you can generate on this surface is also infinite, right? So that's the idea. That's the premise. It's all mathematics. This makes it so that the geometry manipulation that you can do with Nurbs is much more accurate and much more precise than meshes, but also it's much slower and you can't do like simulations, for example. You need to mesh it to be able to simulate gravity or whatever. Well, gravity is fine, but tensile strain, for example. Anyway, moving forward, how do you create geometries, Nurbs geometries in Grasshopper? Well, first of all, my suggestion would be to create them in Rhino and then reference them in Grasshopper. But if you need to, there are ways. So in the surface tab right here, you'll find a primitive subtab where you'll be able to create spheres, cylinders, boxes, and stuff like that. There are some that are quite useful, others that are not so much. I don't know if I've ever used cone and cylinder for anything, but I sure have used a center box or a domain box. Even in these examples, we have already used the domain box for the array, right? So I guess we will begin by me showing, you know, those two and the differences between them. So under primitive, let's create a domain box. Let's start with a domain box because that's already familiar. There are four inputs. I can't count. There are 4 inputs. First one is the base plane, right? So here, the base plane by default is set to be world XY, but if I want to, I can create 1, 2, 3 points. You already know how to create a plane from 3 points. Point, right click, set multiple points. 1, 2, 3. List item to separate out those points. 1, 2, 3. Right? I zoom in to get multiple outputs. And then we, was it plane 3-point plane 3PT? Yeah, that's the one. You can kind of write what you want and it might guess. And usually it guesses quite well. So plane 3 points. Point A, point B, point C. We get ourselves a plane. And now if I just move this plane around, I'm able to rotate it, right? Properly. So X is always driving, the driving of X is always stronger than the driving of Y, right? So you can see that while the plane is always trying to look at the X, the point on the X direction, Y is just used to say if the plane is, you know, if the Y should be, in this case, going upwards or downwards, right? So we have our plane. If I now connect our freshly made plane into the base, bam, now our box is being created on the plane, right? So that's useful. That means we can have, and I'll show you later, but we can have a bunch of planes on top of a surface and we can just add a bunch of boxes flowing along the planes, which might end up with a really, really nice aesthetic. We'll see. We'll see. Right. So now we have our X, Y, and Z sizes. And notice that this is, if I hover my mouse, this is not a number. It's not expecting a number from you. It's expecting a domain. And what does that mean? Well, let me draw it for you. If you have a plane, it should be a bit, okay, you have a plane, right? And let's just say you have 1, 2, 3, 4. 1, 2, 3, 4. Minus 1. That's too close. Doesn't matter. Minus 2, minus 3, minus 4. Minus 1, minus 2, minus 3, minus 4. That's good enough. And then you want to place a rectangle in this plane. Position a rectangle in this plane while also defining the size of it. Well, you might say then, let's do blue maybe. And let's say I want a rectangle that is centered in this plane and is 4 by 4 in size. So that means the rectangle would go from minus 2, from minus 2, it would go until 2, right? So the gap between minus 2 and 2 is 4. And then it would go from minus 2 in y direction until 2 in also in y direction, right? So we end up with a square. Let's do maybe also blue, but darker. Mouse drawings, always fun. So we end up with a rectangle that is between minus 2 and 2, minus 2 and 2. We already know what it is. Well, it says here, it's a domain, right? So you define the box and the position of it as a domain. So here, if I hover my mouse over the x coordinate of it, it says minus 2 to 2, right? So the box along the x direction right here, this is 2 millimeters to the left and 2 millimeters to the right. Then in y direction is from minus 0.5 to 0.5, so it's half a millimeter here and half a millimeter here, right? So it's 1 millimeter in width and 4 millimeters in length. And then in z direction, it's 0 to 0.25, so it actually starts flush with the surface, with the plane, sorry, and it goes out by 1/4 of a millimeter, right? So that's our box. So now if I want to construct, or if I want to drive this box, if I want to define a proper size of the box that I want, I would just create a slider, a panel, // or type in panel. And I would then define, let's say in the x direction, it should go from minus 5 to 5. Like that. Bam, becomes longer. In y direction, it should go between, let's say, minus 1 until 10. Like that. So starts here, ends at 10, like so. And then in z direction, it should go from from minus 20 to 20. It should be centered. As long as these two numbers match up, it's going to be centered, right? And I end up with, well, that's too much, minus 2 to 2. I end up with a box, and I can control the position of the box any way I want, right? So that's the first way, the domain box. Then we have our center box tool, right? Right next to, under primitive, center box, this tool right here. So the center box tool is basically the same thing. You know, it asks you for a base, and I can, I'm just going to internalize this first of all. Internalize data, and I'm just going to copy paste the whole plane creation thing, and I'm just going to reuse it. I'm going to hide the box that I have just made, and in this case I'm going to attach the center box to my to my plane. So here we have x, y, z, but notice that this is actually, while here it's asking you for a domain. If I hover my mouse over it, domain of the box, right? Here, it's actually only asking for the size. So in this case, I don't need to give it a domain. I just need to tell it how much, how big the box should be. So if I say 2, bam, it's from, I think it's going to be from minus 2 to 2. 1 second, double checking. just so that I don't lie to you. Yeah. So it's basically like you need to think about this as radius of the box, right? So when I give it 2, it goes automatically from -2 to 2, meaning that the actual size is 4, right? If I give it 5 here to y, the actual size is 10 because -5 to 5. And in z, if I give it 10, it's -10 to 10, so it's going to be 20, right? So that's how it works, and the center box is also quite useful when you know for a fact that you will be the box that you will be making should be centered around a specific point, right? So that's another method, another way. Okay, time to hide things, delete those. Then, while we're at the topic of boxes, I think one is quite an important thing. If you have some geometry, right? And I'm just going to do some weird things, like 3 points. I'm just going to draw like a curve thing. That is going to be crooked. Whoop, like that. And the points are also crooked. And I'm going to also, just for the sake of argument, add a cylinder in here, right? Like a bunch of geometry, and the cylinder can be even higher. A bunch of geometry, right? I can reference it in just as geometry. So I can reference in the whole damn thing, set multiple, select all of them. I'll immediately or rather no, I won't internalize. So I have this referenced, and I can use bounding box to actually construct a box around this geometry. Really useful tool that honestly I use it quite a bit. So it's right here, bounding box, you can type it in. That is not it. Bounding box, bam, content goes in here. And it just finds the bounding box for every piece of geometry. But what if you want a unified box for all of these geometries all together? Well, you can right click on the bounding box node and select union box instead. So this per object node will change to union box. And now it's always going to generate a box around all of the geometry that I have, that I'm giving it here. And of course, the alignment of the box is going to be along the plane. And by default, the plane is world XY, but I can, let's borrow that crooked plane that we have made. I can just connect the crooked plane here, right? And now it's going to fit the bounding box, along that crooked plane. Honestly, typically you just use the world XY plane because you use bounding boxes to stack things, to measure things, and so on. So that's also quite a useful internalized data, quite a useful tool in my opinion. So that's bounding box. And that's it with boxes for now, right? Okay, under primitives, there's box 2 points, box from a rectangle. We don't, whatever. These are not as important in my opinion. Let's go for freeform. Let me explain a few tools here that you can do, that you can use. You have the 4-point surface, which is exactly what it says. If I have 1, 2, 3, 4 points, point, set multiple points. I have them set up here. And I will use this 4-point surface tool, bam. Basically just creates a surface from 4 corners, right? And actually it can create a surface from 3 corners, as long as you give it 3 corners. So I need to separate this out, of course. I can't just do this, it's going to freak out. So I need to separate this, list item. We're going to get used to this kind of a list item, like fetch separate data from the list type of a workflow. 1, 2, 3. Zoom in, 1, 2, 3. Click the plus sign, and then you just connect the corners. And you can see A, B, C, once those are connected, it makes a triangle. Once the 4th one is connected, it makes a rectangle, right? That's 4-point surface. Easy as that. No more comments on that. Internalize data. Delete. Okay, next, we have surface from points. Okay, this is going to be quite interesting. Should we do it now though? Give me a second, just thinking. Let's first do the simple ones and then we'll do the more complex ones, because this is a little bit more nuanced, a little bit more complex. So surface from points a little bit later. And I will show you one more trick with the landscape, wherever it is. We'll figure it out. We'll find the landscape. Yeah. So we'll continue on with the landscape script with the surface from points tool. So back to free form, we have the boundary surface tool, which I already showed you, but it's basically if you have any kind of shape that is closed and flat, it is going to be able to create a boundary surface. So if I put in the curve here, curve, right click, set one curve, it just creates a surface from a closed flat curve. The moment I take any of the control points and I move them up, it's going to freak out. But then what you can do is you can remember our projection. It was with the planes, so it was somewhere here. Vector, give me a second, plane fit. Yeah. So getting the discontinuities and fitting the plane. You can do that the same thing here with the curve that is not flat to force a boundary surface. So I can always, in this case, I know that it needs to be horizontal, right? So I can do XY plane, create an XY plane and use project. Project an object onto a plane, geometry, plane. Now it's projected flat. I connect that to my boundary surface, you know, and works perfectly fine. If I have, let's do 1, 2, 3, 4, 5, 6, something like that, explode it into 5 segments. So now all of this is exploded and I have it, curve, set multiple curves. So here I have 5 different line segments and I use boundary surface on those 5 segments. It still manages to make a surface. The moment you move either one of these segments even slightly away, it breaks because it can't close the shape, you know. So think of it as hatching, you know. Can it hatch? Can it fill? If it can fill, it's gonna work, right? So that's that. Okay, internalize, group, push here, delete, move on. So those are boundary surfaces. Control point loft, edge surface. Actually, edge surface is quite a useful little tool here. Perhaps I can, should we just keep going down or to the left? Maybe let's do something like this. Like that, and then here. So edge surface asks me for 4 curves. So what if let's do an experiment. 1 curve, 2, 3, 4. Really messy, right? Curve. Type in the curve, right click, set multiple curves, and just get them in here, no matter what's the sequence of selecting them. List item to separate them out. 1, 2, 3, and just connect first one, second one. Made a triangle. Well, not really. Made almost like a loft between the two. Okay, that seems to work quite nice. Third one. Something weird is starting to happen. It's starting to find between the two curves. It's starting to find the midpoint, right? The middle point between the two curves, and from it, here as well, midpoint, and from it, it's starting to draw the triangle. What happens if I give it the 4th one? Exactly the same thing, right? It's going to interpolate. If there are gaps between the lines, it's going to find the middle points, you know, of the gaps, and it's going to just try to guess that that's what you want to do. You know, that's, you want it to find a surface that fits between the 4 curves, right? So that is its aim, right? To do so. So edge surface, I mean, when nothing else works, you can use this to clean things up quite well. So keep that in mind. Internalize, group, hide, move to the side. Next. Okay, we have lofts, finally. So lofts are something that I use a lot. Specifically when you have a network of curves and you offset it and you need to loft it into frames. That's super useful when you need to do some free-form creation. That's also quite useful, and so on. So for now, I'm just going to make something very quickly. A little bit exaggerated wall type of a thing. Something like that. So it's 3 curves, right? Curve, set multiple, 1, 2, 3. Oh, by the way, it needs to be in the correct sequence or else the loft is going to be wonky. I'll show you. And then we use the loft tool. Loft, connect the curves to the curves input, and you know, it makes us a nice little loft. But if I were to, let me clear the values. If I were to be a little bit messy, set multiple curves. If I were to be a bit messy of how I selected, so this one, and then this one, right? Out of sequence, enter. The loft will look like this because that comes in first, that comes in second. So it just goes from here to here, and then that comes in third. So the way you loft really matters, the sequence of the inputs for the loft really matters. Clear. Set multiple, 1, 2, 3. A loft will only work with, like you can't loft a closed curve with an open curve. That will not work. They all need to be open or they all need to be closed for the loft to work. Then under options, there are loft options tool or node available. There is one. And you have a certain amount of options that you can choose from. So the first one being, is it a closed loft? If I were to just toggle, clearly, you know, this is going to be a Boolean, you know, yes or no, closed or not closed. If I say, true, then it closes off the loft into this more of a pipe looking thing, right? So the first one and the last curves also get lofted. So for now, I'm going to keep it open. Should I adjust the seam? Typically, you have this set to false. If a loft is starting to mess up, then you can do a toggle. You know, when it's kind of crooked and so on, you can do a toggle for it to try to adjust itself. But honestly, most of the time, I just have it set to false. Rebuild, you never rebuild unless you really know what you're doing, because then suddenly the loft that has been made will not fit to surfaces from which the curves were extracted. So it won't fit with its neighbors. So rebuilding is useful only when done in a vacuum or when you really know what you're doing. So in this case, we don't touch that. Refit, same thing. Type of the loft. You can see 0 is normal, 1 is loose, 2 is tight, 3 is straight, 5 is uniform. Where is 4? I don't know. So we just create a slider, 0, 5. A slider between 0 and 5. Connect that to type. So this is a normal type loft. I'll show it like so. This is loose. This is tight. This is straight. So you can see that it just generates separate lofts. It becomes a polysurface as well. 4 does not exist apparently, and 5 is, what's 5? I don't remember. Uniform loft. Where the hell did the developable, it doesn't matter. So usually you either do normal, loose, or straight. You don't really use the tight one, at least I don't. Tight or uniform. I don't even know what uniform does. Anyway, so in this case, we keep it as normal loft. Is that it? Yeah, for lofts, that is kind of it. We can group this, we can hide the preview of this, internalize data, delete. Moving on. There's network surfaces, ruled surfaces, extrusions, patching, piping, and so on. Piping I already showed you. At early stages, it's literally you just give it a curve, you give it a radius, and you cap it, and you get a nice little pipe. So that's very simple. I will not be repeating this. Revolution is very niche. 1 second. I think patching. No, patching is done usually in Rhino. You don't really do that much patching in Grasshopper, because it's not accurate enough. So if you wanted to patch, you do it in Rhino. Pipe. Okay, let's go for one more. Extrude. Let's go for extrude. Extrude points, curves, and surfaces along a vector, right? So here I have my loft, and I can connect it to the extrude tool, and then it asks me for a direction. And that's kind of an issue, right? Because if I give it a direction of, let's say, Z, with amplitude of, let's say that the amplitude is like 50, whatever, right? The extrusion looks really funky because it just extrudes upwards, right? Okay, so Z doesn't work, which means it should be X, right? X direction. Okay, let's give it X. And now it looks much better, but you'll notice that the thickness of the extrusion is not uniform, which means that if I bake this into Rhino and I run a clipping plane through this, just like that, and we just run it, you can see that the perpendicular thickness of this, like here, it's clearly much thinner than here. And that is because, you know, the direction needs to change to be perpendicular to the surface for us to have uniform thickness. Of course, if a surface is planar, then you can just simply extrude because that's the same. All of the normals are the same. So extrusion is great when you have flat stuff and you're just extruding it. But when you want to give thickness to a surface, right, you don't use extrude, you rather use offset. So under, I didn't see it here, so it's going to be here then. Oh no, it's not going to be here. No. Do I really need to? Okay, fine. Offset surface, you use this, and then we use Control-Alt-Click. Oh, it was under utilities. Utilities offset surface right here. Okay. You use it here. Loft connects to the offset tool, right? Offset surface tool. Let's hide it. Let's hide the extrusion. And then for the distance, we will just use the same slider 50. Bam. Oh my God. Really destroys itself. Let's see what happens. What happened? Oh, okay. So the drawback of using an offset is if that's the same thing. Remember with the pipes, and if the pipe radius is larger than the curvature radius of a curve, then the pipe self-intersects. That's exactly the same thing happens with the surface, right? If you offset it too much and it's can't make the corner, it starts self-intersecting. If I move this, you will see it better, you know? So here, it's all happy with you and it's all cool and everything works. And then at this particular point, it starts really, you know, breaking. And this is where it starts overlapping over itself, right? So of course, you know, when thickening things, there is a just geometric limitation to how much you can thicken things. And another problem is that when we are thickening this, you can see that this also generates just a surface. And the loft is just a surface as well. So this is not a solid. Extrude, this bad boy right here. Let me group this. Extrude gives us a solid. Oh, great. This gives me only the offsetted surface without a solid, which we need to actually, you know, we need to build up a surface. And I'll use this opportunity to do so. So how do we do that? Well, we need to get the perimeter of the original surface. We need to get the perimeter curves of the offsetted surface, and we need to loft between them. We need to create a loft between the two. Let's do it. Under analysis, there are two ways of how you can get the perimeter. There are brep edges and brep wireframe. Edges, just like with the mesh edges, gives you naked, interior, and non-manifold edges. I already covered this. I will not cover it again. Brep wireframe gives you all of the edges in one list. In this case, only the exterior edges are available or exist. So there are no edges inside of our surfaces, only around the perimeter. So this one would give us a proper, proper output, proper perimeter output. But we will not be using it. Instead, we will be using the cleanly brep edges tool with by extracting the naked edges, right? So now I will just use a panel to check what do I get from here. And what I get is 4 separate lines. And that kind of makes sense because this loft, is surrounded by 4 separate edges. But if I want to loft between the two curves, between the two perimeters, it's much, much nicer if both perimeters are simply polylines, a single polyline per perimeter. So what I can do is I can just, for these naked edges, I can use join curve or join curves, I guess, component right here. Connect it, connect that. And now I get a single, all of these separate segments were joined into a single perimeter curve. And the same thing, delete that. Exactly the same thing I will do for the offsetted surface. So I'm just borrowing those like that. Will this fit? Well, we're going to climb over a little bit into the, or we can just scooch it over. So I get the perimeter of the offsetted surface as well, right? So I have like these two perimeters. What do I do then? Well, I simply use loft. And the first perimeter comes in here, the second, with the shift key, the second perimeter comes in here and just produces a loft for me. So now what I have here, let me just move this to the side a little bit below. What I have here is my original loft, the back face. I have my offsetted surface, the front face, and I have my loft in between them. They're separate though, so I need to merge them into one list and then join all of the surfaces into one polysurface in that list. So first I will use merge tool, the merge tool, and I will just, the way I like to use the merge tool is I like to, take the loft, bring it to the thing that I want to connect. So first comes loft, that's data 1, then I bring it to offsetted surface, that's data 2, and then I bring it to my perimeter loft, that's data 3. And now I have all of them in one list, and we're already, yet again, I ask you to trust me, bro. The data tree does get messed up from the amount of functions that we're doing. So what I need to do is for the result, I need to right click, flatten. We're gonna get there. I promise. Data trees are coming. It's gonna be like 2 hours of a tutorial, but it's coming. So you just right click, you choose flatten, and now they exist in one list, 100%. And then we use brep join. Brep join tool, that as long as things align perfectly with each other, it's going to be able to join the shape into one. Group that, oops, including the brep. There we go. I'll just move it slightly back, just ever so slightly, just so that it kind of fits, okay? And I will hide literally everything except the final brep, this one. If I insert this, no, now all of this has a consistent thickness, right? So it's as if it was bent out of a sheet, right? Well, a very thick one, but now since it's a parametric model, you can just change. You can just change the thickness of the sheet to whatever you want, right? Also, please notice that this is our original surface and this is after we have offsetted it. Rhino or Grasshopper in this case tends to create a lot more ISO curves and uses up a lot more resources when it's offsetting a piece of geometry. You could use offset loose, but whatever. Okay, so that part is done and it's internalized. Great. So we have this done. I think all of this should be grouped up into a larger group just for the sake of clarity. Okay. A little bit of water. Give me a second. So now we are at this stage where we can start experimenting a little bit and we can start messing around with like different tools a little bit. I want to show you the landscape thing, first of all, of how, you know, at the mesh course part or mesh chapter, we have created this landscape right here, or rather this Delaunay mesh, right here from the contour lines. I will use that. So I'm just going to take the curve, take the discontinuities, and take the Delaunay mesh, like these three nodes. Curves, discontinuities, Delaunay mesh. By the way, for the curves, you can just do whatever. I can show you. Apologies, probably those of you who don't have the course files can't follow along that well. I'm sorry for that. You can just simply create a surface, rebuild it, 8 by 8, hit F10, move it around, you know, move some points around to make some topography happen. Go into the front view, select it, contour, use contour command, enter. Click anywhere, honestly, below the landscape, and then holding down the shift key or with the ortho turned on, give it a vertical direction. So click again. And then the distance between contours, I specified 10, but it depends on the size of the landscape that you're using. So in this case, I'm gonna be using 10, right? And then just simply delete the landscape itself, because, you know, this is an exercise for actually rebuilding it. Then we select all of these contours and we rebuild those to mimic what you get from the municipality. So let's say 20, the point count should be like 20, and more importantly, the degree should be 1. Hit preview, see if it's messing up too much. If it does, then increase the point count. For me, it seems to be okay. And voila, we have ourselves a little bit of a, you know, some contour lines. And honestly, I'll just use these for the next iteration. So in this case, I'm just going to be repeating curve, discontinuity, Delaunay mesh, what we've done so far. And discontinuity has this little flattening going on. That's the trust me bro thing. I'll guide you through it. So curve, set multiple curves, internalize data, delete the curves so that we don't need to think about them in Rhino. Discontinuity, level, infinity, right click on the level, choose C infinity, analytic model, gives you more points. Delaunay mesh, oh, that's the wrong one. Delaunay mesh. These points come in as a data tree. We don't need it. We need them to be in one list. Right click, flatten. Don't worry about it, as per usual. Connect points to points, and you get yourself, you know, a rebuilt landscape. And wherever it does not have like anywhere where to anchor itself, you know, it's not able to build certain parts of the landscape. Honestly, I personally sometimes just place a point by myself or add an additional curve in the corners just so that the Delaunay mesh stretches onto the corners. But in this case, I will not. Okay, so now as we have the Delaunay mesh, previously I showed you how to create, a clean mesh result from it with quad remesh. But in this case, I'm going to show you how to actually extract a portion of this as a Nurbs surface. A Nurbs surface means you can do a lot of much more complex things with it. So the step one is to actually make a rectangle above it. Top view, rectangle. And the rectangle should, like all corners of the rectangle, in this case, they should fit on top of the landscape. The rectangle can be crooked, by the way, so you can take certain corners and you can, fit them as you please. That is fine, that is allowed. But it does need to be a rectangle though. That's important. So something like that, right? I have my rectangle. Then I go in perspective and I move it up like that. I have it here. And if I reference it in as a curve, set one curve, I can then very easily convert it into a surface by using boundary surface tool, like that. And then I want to create a grid of points on top of the surface. So I'm going to divide surface. I'm going to use divide surface tool, right? Boundary surface goes into here, and I'm going to say, let's say 50 by 50 points, something like that. 50 by 50. Looks like a lot, but it's actually going to be fine. I will not internalize the curve just yet because I'll want to show you a few things that can go wrong, but for now that's fine. Okay, we have our mesh. We have a bunch of points flying above the mesh. I'm going to, and let's visually also see it here in the script. So the mesh goes below the points. I tend to do that. Like the geometry, what's above, I tend to push in the script as well. Above the geometry that's below. Maybe it's just me, I don't know. Anyway, now we can do project point. Project a point onto a collection of shapes. Great. We have a bunch of points and we do have a shape. Project point. Asks me for point direction, point to project, or sorry, asks me for a point to project. Those are our points that we have here, right? Asks me for a direction, and you can see that if I hover my mouse over it, it says 0, 0, -1. -1 meaning in Z direction it goes down. That's the default direction for projection, and in our case that is perfect. That's, we want to project the points downwards. What is the geometry that it should hit? Well, that's our mesh. And we just get all of the points on our mesh. That's cool. Let's hide the mesh. Let's hide the divide surface points. We get these bad boys right here. Now we will build a surface from these. How do you do that? Well, you go to freeform and you choose surface from points. This one right here. And it asks you for two things. It asks you to give it a bunch of points, and it asks you in this grid of points, how many do you have in the U direction? Remember UVW, XYZ? So in the X direction, in at least one of the directions. Okay, I have the points, but for the U direction, if I were to just use the slider, because this kind of controls how many divisions we do, if I just use the slider, it's going to freak out. And I can show you, right? If I just connect the slider, it's freaking out, simply because if I do like 3 by 3, for this divide surface, let me hide everything else. If I do 3 by 3 divisions, it's actually 4 by 4 points. Remember? Already talked about this. 1, 2, 3 segments, but 4 points. 1, 2, 3 segments, but 4 points, right? So it's always +1. Whatever number this is, it's always +1. So the U count is actually not 3, it's going to be 4. So I'm going to use addition for the U count. I'll take this slider value, connect that to A, like so. But then for B, I'm just going to type in //1 or panel 1, or you can use a slider, but like number 1, right? Connect that. And now technically this should work, but this is still complaining. And the reason why it's complaining is because all of these points, they come in as, again, a data tree, not as a single list. And I know that you're getting tired of me saying, trust me, bro, but every time before we get into the data trees, or should I? No, it's going to be like half an hour of me just explaining this. It needs to be a separate chapter. Trust me, bro. Right click, flatten. Push all of the points into one list. And now surface from points works. If I enable the preview of it, we get ourselves a really nice clean surface. There's a problem though. The problem is called the Lonely Mesh looks like this. And the surface is like way too smooth. Why is that? Well, that's because the resolution is way too small, right? We just give it like 4x4 points. If I now increase this value here, you can see that it fits the surface much more closely, right? But if I bake this, this is still a Nurbs surface, which makes it so that once this is baked, I can, duplicate border, and I'm gonna go fast, so sorry about this. Duplicate border, scale this down to 0, loft between the two borders, join them up, cap, make a sphere, or make a box, doesn't matter. Like that. Push it in, push it somewhere here. Boolean difference with the box. Scale the box down, or even not even that. Just take the 3 surfaces here, extract. Apologies. I'll do this differently. Get these edges in here. One more. Dupe edge, but give me one more here. Cell CRV, join it, offset it. Hello, offset? Please. Okay, there we go. Offset by, I don't know. This is not in scale, so like 2 or something. Loft between them, delete. Merge all coplanar faces. Extrude it up. So we have ourselves a retaining wall. Take the edges that are like a little bit too aggressive, push them down. Take the edges, push them down. They didn't get pushed down. Take the edges, push them down. Breaks here, we don't care, just an example, right? We have ourselves like a terrace or an area where we can start designing and building a thing, right? Something. So the reason why I'm showing all of this is because you can't do that with a mesh properly, right? Nurbs enables you to do Boolean operations and enables you to carve into things, merge things up, and then so on, right? So that's why we usually, the landscapes that we do is we convert them into surfaces, right? So that we can continue working on them. Okay, so that's it with this. I'll just, things that can break. If, oops, well, if you just close your Rhino, that's gonna break it. If I were to take this curve and take this, let's say, corner point and just move it further away, this breaks it. And what bricks is actually this project point, right? You can see here, there's a chunk of points here that miss the landscape, that just keep going and falling through, and they become null points, points that don't exist anymore. And since they are points that don't exist anymore, surface from points cannot comprehend the grid, cannot interpolate the grid anymore, and thus cannot make a surface. So it all breaks. That's why our rectangle that we have made needs to fit in the landscape that we have, right? It can't go beyond the landscape. My voice is going. Oh no, I need to keep recording. Oh. Okay, so that's the reason. internalize. Oh, that's already done. Delete. Okay, that's good. Poop. Get that one in here. Okay, a little bit of weather. Now let's do some analysis stuff, right? So there's two more things that I will show you, and then we will stop with the Nurbs, and then we'll continue. First thing is, if I were to create some sort of a surface here, and let's do the typical thing, right? Let's just take the 4-point surface tool in Rhino, boop, 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 flip, F10, grab 2 opposing points, move them up, saddle. Typical saddle shape, right? The reason why I use this is because it has both the convex and concave curvature. So it's concave here, or sorry, it's convex along this direction and it's concave along this direction. Very good for experimenting with curvature and how it works, right? And I'll reference it in as a surface. Keep in mind, you can also reference it in as a brep. You can also reference it in as a geometry. Remember? It also as data, I guess. Well, data, you can't reference data, but geometry, brep, surface. All 3 of these can hold this particular surface. So for this, in this case, I'll just use a surface, set 1 surface, bam, something like that. And let's do something a little bit, and I'm hiding it. Let's do something a little bit more uncontrolled. So let's use random populate. So let's just fill the surface up with points. Populate, geometry, populate geometry, populate generic geometry with points. Great, that's what we want. So surface connects to geometry, clearly. Count of points is how many points should it populate the geometry with. So let's go for 200. Bam. We can do more. For now, let's do 200. Later will increase. Then for the seed, you know, this is a pseudo-random population again, so you can play with the seed value. So like different types of distributions, you know, like that. It's easy. And if you have some pre-existing points in the collection, you can add them in here. We don't, so we don't care. Okay, so we have our 200 randomly placed points on our shape. What can we do with it? Well, we can use those points to analyze the surface at precisely that, what's the word? At precisely that area or that position, right? So there are a few things that you need to do because these are points. This is the surface, and you basically need to extract information from the surface with the points. And the analysis tool, which is, one second. Yeah, that's fine. The analysis tool is evaluate surface. Am I blind? There it is. Evaluate surface. That's the one that we're going to be using. Asks us for a surface. Great. Asks us for a point. Great. And you can see it's bad. It doesn't give us the, like it tries to produce planes for every point, but it's like all offset, all weird, all crooked and so on. What's going on? Well, these points don't belong to the surface. They're just points that were generated on the surface, but they're not connected to the surface. What you want are surface UV points. So to do that, you just simply need an in-between node here. So the points that you have, you want to use another analysis tool called surface closest point. brep closest point also might work, but we'll just use surface closest point here. That asks us for a surface, we have one. Asks us for the points, we have a bunch. And it basically just gives us the closest points as well as the UV points, right? Let's check the difference. If I use the closest points, it does that. If I give it the UV points, it does that. UV points are basically points that are located on top of the surface and that are associated with the surface, you know, within the coordinate system of the surface. The points are just points that float in the space, right? And they don't have a connection. So we use surface closest point to get that information out, and then suddenly we can actually, get all of this information. Frame, normal, U direction, V direction. So we do full analysis of the surface. As for the distance is concerned, it's actually going to be all zeros, right? Because we're generating the points on top of the surface in the first place. So it's all going to be zeros. But since even though the distance is zero, at the software level or behind the hood, the points are not associated with the surface, thus it doesn't matter if they're very close or they're 1,000,000 kilometers away. Surface closest point, that gives us the value that is associated with the surface, or the point value, right? So now we have a bunch of frames, right? And we can use our, let's start by using what we started with. So analysis, or sorry, primitive domain box. And let's do, the base should be the frame, which is basically a plane. So the boxes will be created on each plane. You will create one box. And all of the boxes, let's say, are going to be the same in size. So I'm going to just create a panel, and I'm going to say minus 10 to 10. Something like that for X. Then another panel minus 100 to 100 for Y. And another panel minus 5 to 5 for Z. And now we have a bunch of these, elongated boxes that are covering the surface, and they're overlapping, sure, that's not great, but they're covering the surface at a very, randomly, but since you're extracting the directions, the U direction and the V direction of the surface, they're kind of aligning, right? Because the planes are aligning with the U direction and the V direction of the surface, and since the surface is rectangular, they're kind of neat. So now, once this is, when this is working, I can hide the surface itself, and I can just keep increasing the populi geometry amount of points until I get something, 1,000, sure. Why not? I have this box thing right here. I can insert it, drag it over to the side, like that. Take a look at it in the Arctic view. Actually, let's hide the display settings, surface edges. There we go. And suddenly it starts becoming a little bit, kind of nice, kind of organic, flaky. Right, so that's one way. Of course, it's not controlled at all, and it's all very, very messy. But if you were to unify whole of this, it would honestly become a quite a nice CNC milling pattern. Right, so that's the surface analysis tool. And of course, you can get normals and so on, and you can. I wonder what would happen if I. Nope, that doesn't work. Or actually, what if we? Give me a second. If I go to vector plane normal, create a plane perpendicular to a vector, I have an origin, which is the point, and the z-axis is going to be the normal, like that. And if I use that plane now, yeah. That's just weird. No, now it's freaking out. Okay. Or you can do that. No, we don't do those. We stick to the tutorial. Okay, so that is evaluation of a surface in a nutshell. Let's do that. Internalize data, and we can keep going. Let me just check if there's things that I am missing. Of course, you can measure the area and the volume of a surface. I'm not going to touch upon that as much. Point in B rep, point in B reps. Perhaps that is going to be quite useful. So let me show you. These are still points, right? The UV points. These are still points, and I still have my surface. So what I can do, if I want to specifically state, that there should be just a few areas where the points should be created, I can create a bunch of spheres or I'll create just 1 or 2. Let's do 2. If it works with 2 or 3, it's going to work with 1,000,000. So let's say 2 spheres like that, right? I will reference them in as breps. Boop, boop. Okay, they're referencing as breps, and I basically want to say that these surface closest points that we have, only the ones that are inside of the spheres should stay. Everything else should be removed, right? So that, of course, will require this to be much longer. Actually, I'll break the group for now. I'll delete the group and we'll make one again. So these 2 spheres, under analysis, there are 2 tools, point in brep or point in breps. Point in brep means that you will be only checking with a single shape. Point in breps means that you will be checking with multiple shapes if the point is inside or outside of them. In this case, we have multiple, so we use point in breps like that. Asks me for a brep, that's easy. Asks me for points, that's also easy. I have those. And it gives us the answer of, false if it's outside and true if it's inside. And then I can use call pattern or dispatch. Remember, dispatch still gives you both lists. Call pattern removes list B, right? And only gives you list A. The pattern is, the answer to is it inside or outside? And the list are these points. And I can't, wait, what? Oh, that's weird. That's interesting. Yeah, okay, that works. Sorry, apologies for not talking. So, okay, UV point is this kind of a tricky thing because it has its own coordinate system that is associated with the surface, and because of that, it doesn't really work so well with point in breps. So what you want to do is when you're creating this pattern, the cull pattern for the, to cull out the points, you're not actually evaluating the UV points if they are inside or outside, you're evaluating the regular ones. And you can do so with either this population of points, or you can do so with, the closest points here. It doesn't really matter which ones. You can't use UV points though, because those work in a different coordinate system. Once that is done, you will see that the points are appearing in a weird place. That is fine. That is expected. But this call pattern then connects to evaluate surface like that. Let me hide it. And now under the domain box will be generating boxes only in places where the breps are, right? Are intersecting with the points. So that's kind of neat. That might be useful for you. One second. Yeah, something like that. Okay, I'll internalize this as well. Delete this. That's already internalized. Okay, we can now move on. Like that. Great. Okay, so those are surfaces. Then moving on, I already showed you cap holes. Offset surface has been shown. Retrim, copy trim, divide surface shown. Well, divide surface has been shown. Surface frames and iso trim. Okay, let's grab that loft that we had somewhere here. Where was it? Loft. Hello. Yeah, there it is. This loft, copy paste, drag it over here. So I have my 3 curves and I have my loft here, right? Make sure that the type of the loft is set to 0, so that is normal, a normal loft. Let's say you want to make paneling out of this. How do you do it? Well, many ways, of course. One of the ways is by using iso trim. Iso trim is a way of how you can take a surface that is continuous and divide it up into segments. into split segments and then work with those segments individually. And I'll show you a very, very quick and simple example of how to do that. It only works if you give it a single surface or if you start managing the data tree quite well. But I strongly suggest that at first, if you're doing this kind of methodology, you should use just a single surface as an input, or in this case, just a single loft. So here under utilities, I'll use iso trim, extract an isoparametric subset of a surface. A mouthful of words, but the way it works is quite simple actually. Asks you for a surface, we do have that, and then asks you for a domain, which is a little bit tricky because this is a two-dimensional thing. So up until now, all of the domains that we were talking about were one-dimensional domains, right? A single line. An iso surface is a two-dimensional domain, or a surface is a two-dimensional thing, right? It has u and v directions, which means that this domain actually would need to use under math domain this domain squared thing. And I can show you a pretty simple example of it. If I were to construct domain squared, it basically just asks me for two domains, right? And then I can use construct domain for domain u and construct domain for domain v and connect that as my 2D domain in here, right? Don't forget to, if you don't want to deal with millimeters, you should use the loft output should be reparametrized. Remember, when you have this, the surface input should be reparametrized. When you have, one second, I'm thinking how to explain it. So everything inside of Grasshopper in terms of surfaces is calculated through the units, right? So you have a certain length along the u direction, some certain length along the v direction in units. So any point that is given on the surface, for instance, if this is the start, this point is probably like 100 millimeters in the u direction and 85 millimeters in v direction on the surface, right? Easy peasy. But visually, for us, it's much easier if we say that this is like 10% of the way, of the full length, and this is like 5% or 20% of the full width, right? Giving the point. And reparameterize does exactly that and converts from unit-based system to a proportion-based system, and that's why we sometimes use it. So I can use reparameterize here. Time to explain things. Drawing time. So maybe somewhere here. Yeah, somewhere here. If I have a surface, right? That surface has a point here that is 0, 0. Another point here that is 1, 0, right? In x direction or in u direction, it's 1, 100%, but in v direction, it's still at 0%. Then we have this little point here that is 1, 1, and this point here that is 0, beautiful 0, 1, right? So we have this kind of a surface. And then let's do an exercise where we extract this patch from this surface, right? I just want to extract this particular patch. How do I do that? Well, I need to figure out the domain along this axis between 0 and 1, right? And the domain along this axis. So I need to figure out this as well as this range, right? And in this case, it might be, let's say 0. That's such a bad color. 0.25 and 0.75, right? And here 0.4 and 0.6 or something like that, right? So there's a domain here that is between 0.4 and 0.6, 0.4 to 0.6, and the domain along this direction, 0.25, 0.75. And then it just understands that, okay, that's the rectangle that you need, right? That's all it needs. So here, if I give it 0.4, because we first deal with the X direction, 0.4, you can see it being trimmed up to 0.6. Trimmed down to here. Then I give it 0.25. Here. Come on, give me. And 0.75 here. It gives me exactly that patch, right? So those dashed lines are, the lines that would go here. Like that. I'll give you a little bit better look here. And I can now mess around with the sliders to get any patch on the surface in any shape or form that I want. Okay, so that's one way of how to use isotrim. Let me move it to below here and group it. And I'll show you another way, or not another way, but that division of the paneling that I was talking about. We're gonna do it now. Isotrim. In this case, we don't need to reparameterize anything because it's not going to be us who will be putting in the variables. It's going to be automated by Grasshopper. So under surface, I still need the domain right here, but now I can do, I can do divide domain squared, this bad boy right here. Divide domain squared, which basically asks me for 3 things, and then it gives me the segments. I'll show you first, before I connect those into the isotrim, I'll show you the segments in the panel, and then connect the panel into the isotrim. So basically this is like a window for us into the data that's going to be being put into the isotrim. And before I do so, data here, that's how it looks like, right? For this, basically in U direction, that's the domain, in V direction, that's the domain, right? That's what I was talking about. All right, so now, first of all, what's the domain? Well, that's actually our loft, because it will take the surface and it will measure it. It will, say that, okay, I understand. The length of this in U direction is from here until here, in like 5,432 millimeters, and the V direction measurement is from here to here, like 2,000 whatever millimeters, right? So the domain is easy. You just connect the surface into the domain. What the hell? Oh, it's not happy with us that we're parsing it through the panel. Okay, that's fine. That's fine. We can just connect the segments straight here. It's going to be happy. And you can see that immediately it works. And it divides everything into panels, simply because the U count and the V count are already set to be a particular, like unit, not unit. Like there's a number there for divisions, 10 by 10, right? So it gives us 100 panels. But if I do, let's do something simpler, 3 by 3. 3 by 3, hide the loft. You can see 1, 2, 3 panels by 3 panels. And here you'll see 9 of these 2-dimensional domains, right? So here, the first panel goes from 0 millimeters to 69, nice, millimeters in U direction, and from 0 to 187 in V direction. That's the first one. Then the second one is going to be this one, because the second one is going to be this one, right? Because in the U direction, it goes exactly the same amount, but then in the V direction, it starts from where the last one ended, 187, and it will continue until 374, until here, and so on, right? So it builds up this domain. And now you can, by just changing the panel slider, you can increase the amount of panels. Let's do 10. We don't need more, just for me to explain, the logic of this. So now all of these surfaces are separate entities, separate surfaces. which means that we can we can work with them, and we can extract stuff, and we can offset them separately, and we can work with them as if they were like separate panels. For example, what's a good one? Like technically I could, that would be kind of crappy. I'm sorry for, I haven't prepared, I prepared only until the ISO trim, and now I want to show you more, and that's not what I prepared in my head, so I need to think. But if we were to just simply get, let's say, the edges, don't really want the edges, sorry. Let's just scale it. Scale all of these surfaces like that along their center points. So to get the center point of a surface, you can just use area measurement. Remember when I showed you the volumetric measurement? Area measurement does exactly the same thing. It gives you an area centroid. And then for the factor, I can just give it 0.995. So 99.5%, maybe a little bit less, 0.942, something like that. I can hide the original ISO trim. And now I have my scaled panels, right? Like separated scaled panels. Of course, offsetting would be a better idea than scaling, because they're kind of messy along the length. Like the gaps don't match up along the length and the width. You would need to be a little bit more elegant with or more precise with the script, but for now it's fine. And then that geometry that we have, we can use exactly the same thing as what we've done here with the offset surface. And I'll show it to you one more time just to kind of lock it in. So every panel gets offsetted by a distance of, I'll just go for 10. That was way too much. 1, that's good enough. Distance of 1. And then I will loft between the edges. Brep edge. There we go, brep edges of this scaled surface and this offsetted surface. That will be joined up like that, and will be merged into one list. And now we just pray that it's not messy. It doesn't seem to be messy. Yep, joins up nicely. And then we would do the brep join and so on, but I'll skip over it. So we have ourselves a perimeter right here, and we have ourselves the front face, or sorry, the back face, and we have ourselves the front face, you know. So we are creating a three-dimensional paneling system. It's a simple grid, but you know, also it's very fast to make. Okay, so that's that about ISO trim. Hopefully the squared domain is not has not scared you too much. And I think this is where we stop with the beginner level introduction with the surfaces. Let me just double check if I'm not missing anything. That's fine. That's good. That's fine. That's good. And then under intersection, of course, you can intersect B-reps with planes, and I already showed you that. But also you can do solid, what's the word? Tools, like not tools, operations. So Boolean operations. Perhaps I should show it here. If I just have a sphere and I have a cylinder like that, something like this, sphere and a cylinder. That's brep 1, or rather set multiple breps. Bam bam, easy. 2 breps. Under intersection shape, I have the possibility to do solid union, solid difference, solid intersection, like these three. There's also split and so on, or trim solid, but for now, let's just use the typical ones. These three: union, difference, intersection. Right? So solid union is simply like Boolean union. Let me hide that, hide this. It's a Boolean union that merges the two shapes together. So you can see that the sphere connects perfectly now to the cylinder, and before it was like so, right? It was just sticking into the cylinder. So solid union merges things together, great for 3D printing. Then you have solid difference, which actually requires us to split these apart. List item into a sphere and a cylinder. And then you can choose what are you carving with what. So the first input is what is it that you're carving? That's going to be the sphere. The second input is what you're carving with. That's going to be the cylinder. If I hide this, you can see the sphere, is being carved by the cylinder. And the last one is going to be the solid intersection, which also requires me to give it a list item. I'm just going to reuse the one that I have just made. I'm going to intersect my sphere with the cylinder. And then it gives me this in-between shape, right? A shape that overlaps, where the cylinder and the sphere overlap. It gives me that. So those are the three Boolean operations that you can use. Last time I thought that it's only going to work with the shapes being closed with the meshes. It actually worked without the shapes being closed. So now I will not make that statement. It might actually work. Okay. I think that's it, honestly. I think we have survived. We have survived the Nurbs. We can move on to the next one, the sub-D portion. Okay, we learned about meshes, we learned about Nurbs geometries. Now it's time to learn about sub-Ds and what you can do with them in Grasshopper, what they're used for. So those of you who are not familiar with sub-D, the logic of sub-D geometry in general, first of all, it's a pretty fresh type of geometry that came in, well, it was at late stages of Rhino 6 and then really was kind of coming out in Rhino 7, right? So it's pretty recent. And sub-D it exists somewhere in between meshes and Nurbs. Meshes with their finite geometry, that is finite resolution geometry that is quite fast, and Nurbs with their infinite resolution of geometry that is quite slow, but unlocks more possibilities for, evaluation and so on. Sub-D is somewhere in between. So you operate with sub-D geometry as if you're operating with a mesh, meaning you're pushing and pulling on vertices, you're working with edges, vertices, and faces, right? Just like with a mesh. But the output that it generates can be very easily translated into Nurbs. Okay, let me give you a quick little example here in Rhino, first of all. Right, if I go to mesh tools and I create a mesh, well, let's do the donut thing. I create a mesh donut. This is, actually that's fine. No, let's do less resolution. I think by default it's 10 by 10. Something like that, mesh donut, right? And then I go to sub-D tools and I also create a sub-D donut. Well, it's a torus, but sure. I'll still call it a donut, right? And then we go to just standard tools, I guess. And here we create a Nurbs donut, torus. Like that. Clearly, sub-D looks much more than a Nurbs version of the torus rather than a mesh version of a torus. But the moment I press the tab button, now it looks much closer to a mesh than the torus, than the Nurbs torus, right? So tab button switches between the smooth preview mode and jagged or control point preview mode. How is it called actually? Flat, smooth and flat preview modes, right? So tab button does that. So now let's say I want both of these to be, convert it into a Nurbs surface. So of course, Nurbs is already Nurbs surface, so that's easy. I just copy it over. Then if I were to select a mesh, I'll just copy it over first. I can type in to Nurbs, delete input objects, yes. And mesh options don't really matter. Trim triangulated faces, sure. You know, I hit enter, enter, and now I have here my Nurbs poly surface, right? Which is actually pretty bad. Every polygon was just simply converted into a surface, right? So it was a direct conversion. Here with the sub-D torus, if I select this and I convert it to Nurbs, delete input objects, yes, enter. That's the geometry that I get from sub-D, right? Much, much closer to a torus, and also, I believe I can't explode this. Yeah, I can't explode this because this is a single surface, right? So, of course, there are limitations to sub-D geometry. One of the limitations is that sharpening up an edge really messes things up. So when you try to, actually, let's do it this way. Introduce a crease. Why not? You know, when I do something like this to it, and I then try to convert it into Nurbs. Actually, this might work. We'll see. Into Nurbs polysurface, to Nurbs. Yeah, okay. That's exactly what I thought. Then, of course, it's unable to produce a single surface, and then it starts dividing things up into patches, acting a little bit more similar to what we observed when we meshed, when we converted a mesh into a Nurbs polysurface, right? But then the moment that it has clean topology, so when the polygon flow is clean, it immediately jumps into creating a clean surface, right? So it's like a very interesting, in my opinion, very cool in-between type of geometry that I really like using recently. If you want to learn more about Grasshopper, about sub-D, in terms of 3D modeling, I will put like a link in either in the video description or somewhere. I'll list the link to a set of videos that I have made somewhere. So just scroll down, you'll find them. Anyway, moving on. So sub-D, right? So the first thing that we want to find is where the hell sub-D exists, right? Where is it? So if I go to to surface, under the surface tab here, we have the sub-D subtab, and it's only these elements, by the way, only these. We don't have more, but these are enough to create a pretty cool, pretty interesting, to operate with sub-D in a pretty interesting way, simply because most of the tools for manipulating sub-D comes from actually mesh tools, you know, moving vertices around and so on. So the way I like to work with sub-D is, first of all, I get some sort of a mesh in here. So for example, yeah, let's do sub-D from mesh. So first let's create a mesh tools, mesh creation. I'm just going to do something very simple. Let's go for a sphere maybe this time, because a sphere in the top has triangles, so that's going to showcase that sub-D also works with triangles. A little bit smaller though, something like that. And I'll reference in this mesh, right? Set one mesh, bam. Now to convert this mesh into sub-D, all you need to do is just literally use sub-D from mesh tool, like that, which asks you for a mesh. Well, we have it. Let me hide it. Asks me for a mesh, asks me for where are the creases, if there are any, so you can already pre-crease it. I would strongly suggest that you don't crease things, instead you apply different kind of methodology for it, but it's up on you. It's basically sharpening of the edges. If there are any corners, that should be stay sharp, and if the geometry should be interpolated or smoothed out. You always should smooth out the geometry. Interpolating usually is a bad idea. Anyway, by the end of it, you get a sub-D that you then can convert to Nurbs. Am I blind? Okay. Oh, wait, there's no two Nurbs tool here in Grasshopper. Either I'm losing my mind or there's no two Nurbs tool in Grasshopper, which is fine. I can just simply insert it here and then run the two Nurbs tool in Rhino, so it's fine. Also, technically, you could do a C# script or a Python script that would do this. So you can see that it's mostly building it up quite well, except that it's making a little bit of a hiccup here in the top, simply because the way a mesh sphere is made is through the, it has poles. It has the North Pole and the South Pole, right? So it is unable to solve those. But if I were to, for example, use a mesh box, with X count set to 1, Y count set to 1, Z count set to 1. And let's go for 100, or let's go for 50 by 50 by 50, a cube, right? And I use that as my mesh, set one mesh, hide. Then we also get a sphere. This is a quad sphere, which we can bake out, right? Quad remesh, or not quad remesh, sorry, two Nurbs. And this one, even though, it's also not a single surface, but it is made out of elements that are symmetrical, right? That the same element just stacked 8 times, right? So topologically, this is a cleaner sphere than this. Just keep that in mind if you need to convert spheres for some reason. Either way, for now, I'm going to keep this, this mesh, right? I'll internalize data, and then we can move on to other stages. So this is how you construct a subd, and to convert back from subd into a mesh, you can just use this mesh from subd tool, right? So subd goes in here, and then you can give it a density slider. So you can see that by now the density slider is 2, apologies. If I were to use a density slider of 0, it would just be subdividing the initial mesh one time. So every rectangle would be subdivided into 4 rectangles. Hopefully you can see it, right? 1, 2, 3, 4 correspond to this single rectangle right here. And then subdivision 1, or sorry, 0 and 1 apparently is the same thing. Apologies. 0 and 1 is the same thing. Subdivision 2, then you have 16 patches for one rectangle, and then 3, 4, 5, and then 6 does not calculate. It's kind of preventing you from going for large numbers because it's afraid that you will crash your computer. Anyway, so that's how you can generate a pretty clean mesh. Okay, so with that out of the way, what we can do is now I can show you a few different workflows for where subd can be used and where it's useful. So let me just group this up. I'll convert this to, let's say, gray for subd. Subd is going to, let's say subd is going to be green color. For now, it's going to be our default grouping color, right? So also internalize. Oh yeah, it's already done. So let's look at the tools that we have, right? The workflow that I like to use is take a subd that already exists in Rhino, do something with it in Grasshopper, and then get it back in Rhino modified. So, okay, example. Quick little example. Let's say it's not going to be quick, but I'll try to do it as fast as possible. Let's say I go to my subd tools, and here I'm just going to create something really fast. So I'm going to probably grab like a subd box. 2 by 2 by 2 is fine for the divisions, something like that. And let's then manipulate it a little bit. So maybe it goes like so. Maybe it's extruded here a little bit. These things tilt. Actually, since I'm modeling, I'm just going to do that. Let's say these things are tilting. Okay. Now I'm blanking when I need to actually make a design. I'm blanking out, and I have no idea what I'm designing. Usually I tend to do like spaceshipy or ship-like elements. In this case, it's going to be like a pistol or something. Anyway, we'll figure it out once we cross that bridge once we get there, right? So let's actually extrude here better. Control Shift, by the way, to manipulate the geometry, the sub-geometry, sub-elements of the geometry. Let's go for something like that, sure, why not? And then I'm just going to hit it with sharpening here. So this whole part, actually, we shouldn't. No, we shouldn't. We should keep this as clean as possible. Sorry for talking with myself. Like that. Could shrink a little bit. Yeah, that's not bad. Could go back a bit. Yeah, I guess we're making a car or something. A little bit of a non-symmetrical car, but it is what it is. And this, sure, let's extrude it a bit more. Whatever, it's something, you know, a building, if you will. A building on a chicken foot. So this shape, I will just get it into Grasshopper as sub-D shape. So now, by the way, I have covered points, I have covered curves, I have covered B-reps, surfaces, meshes, and sub-D. So when it comes down to data types, we're going to be done after this. Yay! So I get the sub-D in here, set1 sub-D. And the first thing that I want to do to be able to manipulate it is I want to convert it into a mesh. And not just any mesh, but actually I want to extract the control polygon. So I'm not going to use the mesh from sub-D tool because it smooths it out. Rather, I want the sharp version of it. So I'm going to go to sub-D control polygon. I extract that. And thus I get this, you know, control polygon mesh, right? So with this mesh, I can deconstruct it. Actually, sorry, apologies. I don't deconstruct it. I just go to mesh analysis and I'll just use face boundaries to get all of the separate objects of the mesh, all of the separate boundaries of the mesh. And then for each of the boundaries, I'm going to scale them. Yeah, I could offset or scale, so I'm going to choose to offset them. Oh, sorry, I'm going to choose to scale them, because it's just simply faster and easier to show. So every boundary gets scaled around its polygon center. That is another one. Polygon center with a factor of like, I don't know, 90. Doesn't really matter, 0.500. I'm just going to give it a slider and then I'll adjust the slider accordingly, you know, by how much I need. So now we have our boundaries and we have the scaled boundaries. And what I want to do is I want to loft them, right? I want to create a loft, and then from that loft, I want to make a mesh again. And loft is technically a yucky way of doing this, but it's the fastest in terms of amount of nodes required. So we're doing that. Unless we use plugins, but we don't. So for the boundaries and the geometry, I want to put them in the same structure, in the same list. Oops. Like that. Is it going to be another trust me bro type of situation? Yeah, it definitely will. Because right now I have 140 curves all in one list. So loft will just shit the bed. Honestly, loft will not work. Well, it's going to work, but it's going to loft through 140 curves. We don't want that. Actually, I can show you. I think it won't crash. I'm going to just save here. Don't do this, by the way. I'm going to do this for you. And I'm just going to loft. Nah, it just doesn't even work. Loft could not be constructed. Okay. Anyway, so that doesn't work because all of the curves are in one list. So what I want to do is I want the curves to be separated and grouped up 2 by 2 by 2. You know, all of them should be paired. This is going to be weird. I'm going to right click on the boundaries and yeah, trust me bro type of a situation. Boundaries output, right click, graphed. We used to use flatten. Flatten puts everything in one list. Graphed separates everything into separate lists. So we use graphed. And now if I were to use loft, Again, graph is this little arrow that goes up, you right click and you choose graph. Now if I use loft, now it just works. I really hated that I can't explain it to you properly right now, but it is what it is. So now we have these openings, right? We have these openings. And for these openings, I can also, from the loft, I need to convert the loft back into a mesh, right? And I can use, I don't remember if you have this. I hope you do. There's a simple mesh tool. Let me just check. Well, technically it exists under the mesh tab, so you might have it. So simple mesh tool actually, converts everything quite neatly into a mesh. But since I'm not, I don't remember if you have this. Just in case, I'm going to show you a more manual approach. Because, if we look at any of these lofts, it's basically made out of 1, 2, 3, 4. Out of 4 surfaces, subsurfaces, right? That are all quads, they all form rectangles, right? So that means I could just use deconstruct brep. It's in the top, deconstruct brep, brep. I get the faces, and for the faces, for each face, I get the the face boundaries, not face boundaries, sorry, brep edges. Or I could just deconstruct brep again for each face, right? So now when I deconstruct it twice, now I get 4 points for each of the surface, and I can use those to construct a mesh. And since construct mesh, by default, it uses 4 points to construct a single surface of a mesh, it's going to make it. So basically it's the same, like these 3 nodes and this node are exactly the same. You could, mentally you could draw an equal sign between them. I will do that for you. Equals, right? So which one should we use? Let's use this one because I'm 100% sure that this one will work for everyone, right? So now we have a bunch of separate mesh faces that are just like floating about. We need to join them all up. So I'm going to, first of all, flatten the list, right? Notice this dashed line, right? Everywhere where ever since we graphed it, there was a dashed line. This means that we have multiple lists going through here. And it's basically lists of lists of lists. I'll explain that in the future. I keep promising that. So construct mesh, the mesh output, we need to flatten that to pull everything back into one single list, because then we will be able to mesh join them all up into one big mesh, right? So now if I were to look at the mesh join, this is one single mesh, and I can use two Nurbs two subd, subd from mesh, subd from mesh, fine, surface primitive, subd from mesh, yeah, I don't know why it didn't give it to me. And now I get this kind of a cute little behavior, I guess. But now, since this is a parametric model, I can change the size of the holes for it, right? So I can control how much it opens up, which is nice. And of course, the factor for the size. Remember when we use the point to read how far away, for instance, any of these center points is from any given point? For instance, here, point, right click, set one point. For instance, here or wherever, doesn't matter, here. I can measure distance between this point and all of the center points here. I get the distances, and I can remap those numbers, those distance numbers, to be between 0.1 and 0.9, something like that, with the source domain being, 1 second, need to think. Oh, we just need to know the maximum and minimum distance. So by using bounds, we can do that. Literally the same thing as what I was doing when I was explaining the remap numbers node, right? Except that here, again, everything comes in as a list of lists. We want, for the bounds calculation to work, we want everything to be in one list, so the numbers needs to be flattened, like that. And then we connect it to source. And then, of course, the mapped numbers need to go into the factor. And now, wherever I move this point, it closes off. So I can control that, which is nice. So that's a little kind of bonus thing for you. Okay, internalize that. Okay, back in here, we have our subd from mesh, which, if I bake out, hit tab, looks like that. To give it thickness, you can, before you create a subd from mesh, you can offset mesh. You can use offset mesh tool. Missed it. Mesh connects to mesh. Distance, you give it distance, let's say 2 or whatever. And make sure that create solid, that this is toggled to true. By default, it is true, so you're fine. And then you just connect the offsetted version to the subd from mesh. And it just breaks. Okay. No. No, please. Is it the distance? No, it's not. Ooh, that's interesting. So why does it break then? Do we need to unify? Cleaning up of a mesh usually consists of unify mesh tool and another one, mesh clean tool. So let's see if just unify mesh will work. Yeah, okay, that was enough. Unify mesh just works, cleans it up well enough so that we have ourselves a decent offset. Insert. We made cheese. Yay. The thickness is too much in here. But you get what I mean. And then this subd can be to Nurbs, converted to Nurbs for further Boolean union, Boolean difference, and so on, right? Because as long as it's Nurbs and as long as it's closed, you can just create some sort of a sphere looking thing, Boolean difference from it with the sphere, and it just all works perfectly fine. Right. So that's a very basic kind of, very basic concept of how you can manipulate a subd and what you can do. So you convert it into mesh, you do what you want with the mesh, and then you convert it back into subd, right? That's the premise. That's how it works. Internalize data, hide all of this, we move on. One of my favorite tools, or two of my favorite tools. First one is subd fuse tool. So for example, let's say have some sort of a Nurbs geometry. Let's do 2 boxes actually. Let's go for it. Box here, like that, and box here like that. Nothing special, just 2 boxes. Let's reference them in. Brep. Set multiple breps, brep. Okay. Step 1, we need these breps to become meshes so that they can become subds. Directly translating breps into subds, not the best idea. I mean, it should technically work. If we just do subd from mesh and we connect brep to mesh, it should work, but I think it's going to be very, very complainy. Yeah, it's not the best, They should be a little bit different. slightly different. So what we do is for these breps, we first use quad remesh. Boop. Right. And actually, is that a good idea? Nah, maybe not. Sorry. I'm just thinking. Actually, yeah. whatever, quad remesh, and we give it a pretty generous amount of polygons. In this case, it's too many, but actually, no, it's too many. Let's quad remesh settings. Let's change that to like 500 each, not more. Yeah, that seems a little bit better. So that's our remeshed boxes. You can see that they're starting to lose shape a little bit. You could use guides for the quad remesh. I wonder if that would work. 1 second. If I just give it the wireframe, will it lock into the wireframe? Nah, it doesn't. Okay, so we don't use that. Never mind. We don't use that. We just use a little bit weird quad remesh, and then we convert them mesh to subd, or subd from mesh. Bam, and they get a little bit, smoothed out. Subd tends to smooth things out, unless you introduce creases to it, but that is a little bit more advanced in Grasshopper, so we skip over it. So now with these two subds, if you want to merge them together, subds don't really have Boolean operations, but they do have one thing that might help, which is subd fuse. If I select that, there's subd A and subd B. In this case, we have two subds here, which I'm just going to use list item. It can only fuse two things together. It can't fuse 5, right? So you would need to fuse two things and then add one more with multiple of these subd fuses if you have more than two elements. Subd A goes here, subd B goes here, and voila. It just managed to fuse the two objects together. And of course, there's multiple options here. There's fuse, and then there's intersection. So an overlap between the two. There is A minus B, so you can Boolean difference. There's B minus A, you can Boolean difference the other way. Great. And then there's smoothing. So how many iterations of smoothing should it do after the fuse has finished, right? So this is like 0 smoothing iterations. It's pretty sharp. The transition is pretty sharp. And this is like 100 smoothing iterations. So it's really, really smooth. If I insert this and I look at it here, and I not quad remesh, to Nurbs, again, this is a pretty damn clean Nurbs poly surface that you can use. That's a nice transition here. So when it comes down to shell creation, architectural shell creation of these kind of smooth buildings, there's nothing better than using subd. It's a great tool. Okay, that's another one. Then the last bit that I will show you with subd is curves or networks of curves. Got it. Got there. What should we do? I know everyone likes Voronoi, so I'll show you one quick Voronoi example. So if a Voronoi is a way of how you can tessellate a surface by giving it a point distribution. So let's go to the top view and let's just simply create a rectangle. Any size you want. Maybe this is a little bit too big, but doesn't matter really. Rectangle, reference that one in. Curve. Set one curve. Now we populate this rectangle in 2 dimensions, right? So we used to use populate geometry that populates a surface of a geometry. Since a rectangle does not have a surface, we need to use populate 2D, and it's not a 3-dimensional object, so we can't use populate 3D. Populate 2D. Our rectangle is the region. Count is how many points. Let's keep it at 100. If I need to, I'll adjust it later. And we have our point distribution, right? Point calculation. Yeah, we have our point cloud. So these points, then I can go to mesh, triangulation, Voronoi. There we go. Planar Voronoi diagram for a collection of points. That's great. That's what we want. And we just connect this population of points to the points input. And we get a very organic shape that all of the students love. And it's, I don't know, it's fine, I guess. It's just overused. So don't use it too much. And of course, with Voronoi, you can also define the radius of these points. So you can do, If it's 5, nothing touches. As you increase it, bigger slider. There we go. As you increase it, things start touching. And that's basically how Voronoi kind of works, right? So it's a lovely algorithm that is, unfortunately, since it's so lovely, it has been used to hell. And you can also apply a boundary. So we can use the same rectangle as a boundary for the Voronoi, and thus we end up with a bunch of cells here, right? A bunch of Voronoi cells. So then the question is, how do you make this into some form of a network? You know, how do you, for example, how do you make it into a dome? Well, first of all, you need to transfer these cells from here onto a dome. But before you do so, all of the cells right now are enclosed polyline curves. So if I were to bake these out, you'll see that, you know, this is every cell is a curve on its own, like that. And you don't want it. You want it to be a network, meaning that all of the curves should not be duplicate. Because, for instance, here, this curve is duplicate because this cell and this cell share it, right? So there's 2 curves here. You don't want that. You want them to be single cells. So what you do is you explode all of them. Explode. You get all of the segments. You force them into one list. Right-click, flatten. Right? And then you remove duplicates. Remove duplicate lines. With a certain tolerance. 0.01 seems to be probably okay. We'll see. If it's not going to work, we'll need to increase the tolerance. For now, I think it's going to work. So now all of these, if I were to insert, if I were to bake, this is a single line. Actually, let me hide this as well. That's a single line, that's a single line, and so on, right? That's a very small line. Oh no. I can really see a problem, a problem happening right there. We'll see. We'll see. So for now we have this Voronoi pattern. And what I can do, oops, shouldn't have deleted that. There we go. And now what we can do to actually make a network out of it, a 3-dimensional network, is, you know about pipe. So technically I could pipe this, right? And it looks good as long as you don't zoom in. The moment you zoom in, you notice that, oh crap, all of the pipes are actually like separate objects that don't really work together. They're just kind of intersecting, right? So pipes are bad for that. They're not good for seamless connections. And thankfully, alternative to that is multi-pipe. Multi-pipe. This bad boy right here. It's under surface, sub-D, multi-pipe. You can take the lines and you can connect that to curves. Hide the pipe for now. And see, now it makes a very, very clean connection. And I'm just looking through it all, and it seems to be working just well. Yep, everything works just fine. And I'll find a very, very small connection. I think it was here. Yeah, it was it? Yeah, it was here. And even here, it seems to be working quite well. Now let's increase the radius of them. That's the, I believe, the node size or size points. I never remember. I think it's node size. Let's just make 5. Like something ridiculously thick. And it still seems to be, I mean, it's starting to mess up a little bit, but it seems to be doing quite well, right? So let's reduce it to like 3. And in most cases, except here, 3 seems to be quite good. The further like steps or iterations that I would do is I would actually bake this out, and then any areas that I need to fix, for example, you know, this is weird. I would just take this point, move it over here, take this point, move it over here, tab. Perhaps they could move a little bit closer here, something like that. Yeah, something like that. And you just straighten it out manually. And there's, of course, many areas where, that fails, but don't be afraid of manual labor, is what I'm saying. Okay, then we have, let's make this a little bit smaller. Then we have a bunch of different settings here that I'm not going to cover as much, but I guess the most important one is the amount of segments. Amount of segments along this division. So if I do like 5 segments, bam, you can see that it adds 5 divisions. So by doing so, you can create more, or not more, but like better resolution. And I'm like looking at this and it seems like that's the gap size. Spacing, okay. So this is the spacing between the edges. So what's the resolution basically for the polygons? You can get a more uniform distribution when you apply the segments this way. Then we have our strut size, was it? I think, 1 second. Yeah, okay. So if you're decreasing the strut size, you can see that now the middle portion becomes thinner, and the nodes become thinner. And if you increase it beyond 1, then it's going to have the opposite effect of these becoming thicker, right? It looks like a balloon. 1 is, everything is kind of evened out. So you can have that control over it as well. Okay, that's enough with the multipipe. That seems to work quite well and quite nicely. And of course, you can apply multipipe to any kind of a geometry. If we have, just give me a second. Oops. Let me just move this over here. Internalize data. Have this grouped. Okay. So for example, if I were to, let's do our, where's our B-rep? No, those are the 2 faces. I'm just gonna find one here. That's curve, surface. Okay, can we use this? Yeah. I'm just going to borrow this, Control C, Control V. The surface tool from where we used to use the surface, right? This saddle-like shape. The surface tool I will convert into a mesh by using quad remesh. Actually, we can just use surface mesh or mesh surface tool. As long as it's like a quad surface, it's very easy to mesh it. You just give it U and V count. So I'm just going to say 25 by 25. Easy. We get a grid. And then from this mesh, I can get wires. B-rep, or sorry, that's not mesh edges. Mesh edges. I merge the naked edges and the interior edges. As you can see, I'm trying not to repeat too much stuff that I already said. And then these edges, I can use multipipe to pipe them up. Multipipe. Like that. Curves. Let's give it like a 3, I don't know, for the size. Sure. 4. Just so that it's visible better, right? And we get ourselves a pretty clean insert. A pretty clean lattice structure, which, this is the flat preview tab. This is the smooth preview. Okay. So that's, you can basically, as long as you have a network of curves, you can use multipipe on that. I think that's it. That's it with sub-D. You can extract vertices, you can extract edges, and that's it. It's a small one. Okay, so sub-D is finished. Let's move on. Okay, next chapter. Let's look into the transforms and different ways of how we can move, rotate, scale, orient, mirror, and so on geometry. I'm just going to cover the basics of it, and a deeper ones you can figure out yourselves, I guess. So the first thing is we need a test subject of sorts, and I'm just going to create a sphere here in Grasshopper. Sphere with a radius of, let's go for 5. There we go. There's our little sphere. And the things that we can do with the sphere, we can move it. I already showed you move quite a few times. Sphere connects to the geometry input, and for the motion, we need to give it a vector. So in this case, I'm going to move it along the x, unit x, by 20, right? We get to move the sphere by 20 units. And you might think, well, it's not moving it, it's copying it. Well, actually it is moving it. It's just that we see the previous version of the sphere here, right? That's also something that students kind of mentally, at least for first day, they kind of struggle with it, and then they figure it out that all of the iterations, of previous geometry generation, they stay, So move is, you could think of copy, but it's not really copy. It's like now when you apply move, the sphere appears here, right? What if you want to make a bunch of copies of it? Well, you can move along the x, or let's go for y this time, along the y vector. But instead of using a single number, you can use series of numbers, a list of numbers, right? And the step size is, let's say, 5. And the count is, let's say, 25. So a list of numbers produces a list of spheres, right? So that's creating multiple spheres that move. Of course, under array, you can already see there's a linear array here that we can apply if I just use the geometry of the sphere, and in the polar array plane, that's interesting. Oh, that's polar array, my bad, sorry. Array, linear array, there we go. Geometry goes here, direction x, but this time, let's say, well, actually, it should be like negative. So we can use negative value here. And whatever value you plug into the negative node, it's going to be minus. So it's going to go backwards in x direction, and we will just give it like 5. Bam. So the linear array works this way. Right? And of course, the count controls. The count is the same thing as in series. How many spheres should you array? Personally, I usually use the move rather than array. I don't know why. I'm just used to it more. Both of these are exactly the same. Okay, then we have for the array. Let's continue here. We have the rectangular array. Geometry, but geometry requires us to give it a cell, and a cell for a rectangular array is a rectangle. So I can create a rectangle. This one, create a rectangle on a plane. And for the size, I will just give it, let's go for 5 by 5. 5 by 5. More, 10 by 10. So that's the rectangle, and it just moves according to the rectangle size. And then we can define how many there are in x count and how many there are in y count, right? So you can array your spheres that way. That's the rectangular array. Then, moving on, we have our, actually, let's finish up with the array, because I already showed you the box array quite early on. I will not be repeating that, but there is the polar array, which might be quite interesting. So polar array revolves around a central axis, or rather a central plane. And in this case, polar array, if I just connect the sphere here to the polar array, you will see that it does not really do anything. And the reason for that is because the sphere is just simply because by default, the the plane around which the array happens is world XY plane, and the sphere is built on world XY plane. It just kind of rotates around its own circle, around its own center point, so you can't see it. But if we first move the sphere like that, and then we use polar array on the moved geometry, well, that's a different kind of a situation here. So then we can apply the count. Let's say 22. Right? And you can change the angle. In this case, the angle comes in as radians, but you can right click and you can choose degrees, and then you can use like normal people measurements for the degrees, 360, 180, and so on, right? So you can control that. Okay, that's one more thing. Okay, so those are the arrays. There's a kaleidoscope, but we don't, let's not. Then, 1 second. Project, I've already shown you project. I can show you again. Project basically takes any kind of a geometry and projects it onto any kind of a plane. So in this case, the plane is world XY, but if I were to just, let me just create one plane. Plane from 3PT, plane 3PT, yeah, list item. Something like that, pump, pump, pump. We get ourselves like a crooked plane, bam. And then if I move one point around, my geometry, that sphere, it's basically as if it's a shadow, gets projected onto the plane, right? So spheres are fine. I mean, it makes a very weird type of a geometry. Usually you project like curves and points rather than three-dimensional shapes, three-dimensional geometries. But it still works, so we keep it. Internalize. Bam. Group. Okay. So that's project. There's also project along, where you can define a direction for projection onto a plane. So you can project it at a weird angle onto a plane, but we will not be using that because it's a little bit more advanced and you don't really need it that often. Scale. If we have a sphere, we need a center point for scaling. And to get a center point of any closed shape, let's do it like that. To get a center point of any closed shape, you just simply need to get its volumetric centroid. To get any center point of a flat shape, you just get its area centroid. And to get the center point of any polygon, you get its polygon center, like that. In this case, it's a closed shape, so we get a volumetric centroid. Get that in here, and the factor is percentage, so 0.5 is half the size, like so. And then, you can play with it. Of course, you can scale it up as well, so factor 2 makes it bigger. So that's scaling. There is, of course, non-uniform scaling, scale NU. Same geometry. The plane is basically, for non-uniform scaling, you need to define what's the plane along which you're going to be scaling. So I'm just going to use a simple XY, world XY plane, and then I can define 3 different scaling factors. Let's say along the X direction, it needs to scale by 5, along the Y direction, 0.5, and along Z direction, it stays as 1. Something like that, and I just make a weird looking squished banana thing, right? That's non-uniform scaling. Stretch. Think of it as stretch. Okay. What else? What else? What else? Box mapping, huh? Nah, I'm going to show you a different thing. It's going to be cooler. It's going to be under morph. But for now, let's just see. Array and affine is done. Euclidean transforms. Move is done. Rotate is not done. Okay, and mirror is not done. So mirroring is pretty straightforward. For this, I need a separate type of geometry. So I'm just going to make some sort of a box. Somewhere off the XY axis. And you can see that the mirror plane by default is set to YZ, not XY. So that's why this plane right here is vertical. If I add a B-rep in here, it just mirrors along that plane. And of course, I can then take those 3 points. So I can just borrow this plane between 3 points and use that for mirroring, right? And now suddenly that plane, or rather the 3 points that generate that plane, starts working as a mirror surface, right? So if I were to move this around, wait, now it's the y-axis, huh? Oh, it's internalized. My bad. 1 second. There we go. Right. Now I can use this as a mirror. So that's cool. Mirror is a nice tool to use. Let me just internalize. That's already internalized. Group this up. Then for Euclidean transforms, I'm just going to show you one rotation, or rather, yeah, I'm just going to show you one rotate and one orient node. So orient is, what's a good example? 1 second. First, let's do rotation, right? That's going to be easier. So if we have this B-rep here, right, and I want to rotate it, I have all of these possibilities for rotation, right? The one that I'm going to show you is going to be rotate 3D, this one, because this one is the most flexible one. So rotate 3D asks me for geometry. That's fine, I have one. Asks me for an angle. We always right click on the angle and we choose degrees rather than radians because we're not nerds. And we create a slider 0.180.360 between 0 and 360. That's our angle. And you can see that now it does work, it does rotate, but it rotates around this particular point right here. And that is the center of rotation, right? The center of rotation by default is set to 0, 0, 0 point. If I want the center of rotation of it to be in the middle of this box, I just do a volumetric centroid. So I measure the volume, connect that. And now the box can rotate around its original owner, I guess, or whatever you call it. Let me delete that. And then for the axis, that is currently vertical, Z axis, but I can very easily just, if I convert it to any vector, then I can define the direction, around which it rotates. So right now it's rotating around the X axis rather than Z. So if I look at it here, that's the axis around which it rotates, and so on. So rotate is pretty simple, pretty straightforward. We're blasting through these, aren't we? Okay, a little bit of water. I'm getting tired. I'll need to take a break after this one. Orient, okay. That's gonna be a little bit trickier to show, but we'll manage. So for example, what would be a cool thing to show you? Let's grab that surface that we keep using. Was it this one? Yeah, this one. Surface. Control C, Control V, and then of course drag it over. There we go. So I'm going to use this surface here. And I'm going to use, under the surface tools, utilities, I'm going to use surface frames tool. Surface frames, bam. And I'm just going to give it a count of 25 by 25. So 450 something frames? 6 76 frames. Okay, because it becomes 26 by 26. I forgot. Anyway, we get a bunch of planes in here arranged as a grid. And then if we want to populate elements onto these planes, what I can do is I can create any kind of an element. Let's make something, let's do sub-D this time around. Sub-D, cone, whatever. Weird sub-D cone looking thing. Tab, sure, spiky boy, right? And I'm placing it currently, like, I'm trying to be smart about it and place it on world XY plane, just so that it's easier for me to navigate it. But perhaps just for the sake of this example, I should move it away from world XY plane just to, you know, explain to you the origin plane logic. So anyway, what I want is I want this to exist on top of every one of these, right? Every one of these planes. This cone needs to exist. So first of all, I reference it in as sub-D. Set1 sub-D. Bam. Then I will use under transform, under morph, I will use, no, that's not morph, sorry, Euclidean transform, orientation, orient. And the geometry that I'm going to orient is going to be my sub-D geometry. And the source plane from which I move it needs to be located at the bottom of this shape. So what I'm going to do is I'll go for standard and I'll just create 1, 2, 3 points at the bottom of my shape, right? So 0, 0, 0 point, X direction, Y direction. I will reference them in, set multiple, origin, X, Y, and I will 3PT, plane 3 points. Ah yes, list item, I keep forgetting. List item, like that. And I just make a plane on the bottom of the surface. So now it doesn't matter how this is rotated, as long as the points rotate together with it, the plane will match up, right? So that's great. So then from this plane, that's the source plane, my target plane is going to be every single plane that we have here under the frames. So I just literally connect surface frames to my target for the orient. Takes a while, but here it is. Gives me the orient planes, and you can see that it's whatchamacallit, it goes in, it doesn't go out. So I need to fix that, and the way I fix that is by either flipping over this shape here, or simply by moving this point from this position to the opposite side of the shape, and then these will be looking outwards. Maybe there's too many of them. Let's do like 15. Something like this, and just scale this up a little bit, make them a bit bigger, and there we go. We have ourselves a spiky boy. Insert that, you know, kind of organic, kind of petal shape like. So that's one thing. That's the orient. That's how orient works. Hope this is easy to internalize data. I hope it's easy to follow along. Okay, all of these are internalized. I think I can delete these. Yeah, perfect. Now let's do some a little bit more complex things with the morph. So in terms of morph, I'm going to show you one second. One tool. Yep, I'm going to show you one tool with morph, and from it you'll need to build it up yourselves. So, or rather two tools, I guess, surface box and box morph, these two working in tandem. So for example, I create a surface, any kind of a surface, doesn't matter. Rebuild it. I rebuild it with 4x4 points with degree of 3x3. hit F10, and I will just simply move up all of the points except the corner ones. And thus I create this dome shape, right? Easy. We have this dome shape. I will reference it in as a surface. Set one surface. There we go. Hide it. And then for it, under morph, I will create a surface box on it. So it asks me for a surface and it will ask me for a domain. We already did this. If I go back in here, isotrim also asked us for a domain, and we use divide domain squared to get a grid of domains. As you can see, things are starting to repeat themselves, which is nice. So I will use divide domain squared for the surface as well. U count, V count, let's go for 15 by 15, something like that. And for the height of the boxes, so these have thickness, right? So for the height of the boxes, I will use like, I don't know, I start with 50 and I adjust. 50 is probably going to be too much. Actually, not that bad. Just slightly less, 44. Okay. So we have ourselves a bunch of twisted boxes that are following our shell, right? Very nice. Now we need to insert geometry into those boxes. So a way of how I kind of want to tackle this is by just here creating some sort of a rectangle. Let's say 50 by 50. Just the size of the rectangle doesn't matter. It's all going to be proportion based, right? 50 by 50. And from this, I'm going to create a tile that is going to be added into every single one of these boxes. So I'm going to say offset this. Should I offset? No, let's make something a little bit different. Let's just do like a weird thing with like a weird trapezoid pyramid thing. So if I just make a planar surface out of this, delete, and I extrude it, oops, up a little bit, and I move this or copy this up and I scale this down a bit, and copy this again and scale this down a bit. I end up with this pattern, I guess. Boolean union, something very simple, and something very, very quick. And maybe this one can be a little bit taller. Sure, I guess, right? So something super, super simple. And then I said weird, and then I end up doing 3 boxes, but I'm tired. That's my excuse. Brep, right click, set one brep actually, because I used Boolean union to join them up. And now I want to convert, not convert, but to get this into every single one of these. How? How do? Well, if you use morph, box morph, that's the answer. So you need to, first of all, you define the geometry, right? That's my tile. Then you need to give it a reference box. And that is going to be a bounding box. A box into which this fits perfectly, touching the corners of the box. Just in case union box, there we go. And we connect that to the reference. And then for the target, we will use all of those twisted boxes here. Bam. Give it a second. And we end up with this. And I think this is the first time where I'm going to actually use, I'm disabling the preview of everything, where I'm actually going to use a custom preview just to be able to show it to you in Arctic View properly. So I'm going to use custom preview node right here, which automatically draws it in pink. It is what it is. And then we go for the Arctic View. And we can see our little waffle structure here actually work. And it's kind of clean on the outside. It's nice on the inside. If I take this and I just rotate it 180 degrees, then it's clean on the outside and it's waffly on the inside, right? So that's how it works. I'll delete the custom preview just so that it's not in the way for now. Okay, so that's the premise. You know, you have your surface boxes and you populate them with any kind of geometry. Since box morph accepts geometry rather than brep or a mesh, this can be a mesh, this can be a sub-D, this can be a Nurbs polysurface. So whatever, right? So that's how you apply box morph in this little example here. Okay. Yep, those are the two that I wanted to show. And then for utilities, these are way too... No. I guess grouping and ungrouping is kind of useful, but... okay, I can show you. So, is there like a reason? No, at this stage of your learning, there is no reason for you to use group ungroup. So we will not do that. We will say that this, in terms of transformations or translation, that's all you need. That's all you need for now, right? So on to the next chapter. Okay, let's talk about text this time. It's actually pretty interesting because you use text in Grasshopper or manipulate the text in Grasshopper quite a bit. And it's, I guess at early stages you don't really manipulate it that much, but basically for every drawing that you get from the municipality and so on, and you know, any kind of data that gets imported, usually there's CAD text that you need to work with. So I'll begin by showing you a distinction between what a text entity is and text is, right? If here in Rhino, I just simply write a text, which, sure, maple R question mark, you know, maple tree, and I'll just draw a circle here. Doesn't really matter. So this might be one type of a data that would come in from any kind of CAD drawing where the R is undefined and you would be measuring the R and typing it in. But you can kind of automate it with a little system, and I'll use that as an opportunity to actually show you about how you operate with text. So the first thing is, how do you get this into Grasshopper? Well, there are two containers for text. One is called text, like this, hexagon. The other one is called text entity, like this, text entity. Which one is which? Well, the text, if I right click on it, you can see there's no set input objects, right? You can only set the text, and I can write cat here, commit changes, and then if I look at it, it says cat, right? So this is something that you can only set up in Grasshopper. So to get it, get some text from Rhino, you need to use text entity node, which is located right here. You right click on it, you set one text entity, you select your object, right? Now you have your referenced text entity right here that says maple R question mark. So what's a text entity? Well, first of all, it does have words in it, right? And characters and letters and so on. For sure it does. But also it has much more information. It has the font information, the text size information, alignment information, and then so on, right? So it has a bunch of data. What you care about is mostly just the text, right? The text itself. So what you want to do is you want to extract this maple R question mark from this. The way you do it is you go to the Rhino tab, you go to the annotations tab, and here you'll find the text entity object or node, which you take, and you connect your text entity to the text entity input right here. Then the output that you get, well, there are a few. First one is, or second one, first one doesn't matter. The second one is a plane. So it shows you where does the text start from. That's sometimes useful. But more importantly, you get the text output here, which is raw text, which we like. So what can you do with this raw text? Well, first of all, if we go to our vector, to our set text subtab, all of the operations with the text are available here. And the main ones are these four, honestly. And those are the ones that I will be showcasing. So the first one is characters. You can split it into separate characters. like that. And the result, if I look at it, bam, we get our, every separate character gets placed into its own little list. You can also use text split tool that takes this text and splits it with a specific symbol, right? At a specific symbol. So in this case, I'll use the space bar, right? So I'll just write dash dash panel space bar. It looks like the panel is empty. It's not, because it has a space bar in it. And then if I look at the result, it's going to be 2 lines, maple and r equals question mark. Then what I can do with this is I can call index, remove a certain item from the list, and I can remove index 1. Just like that. And I'm left with just maple, right? Of course, it won't update here because we're only operating with the text, but that's fine. We're learning things, right? Then to this maple, I want to add the radius, the r of the circle, right? So how do I do that? Well, I first need to get the circle in here. Curve. Set one curve. Bam. Then I want to get the, actually, is there like a radius tool? No, there's not. Okay, fine. We get the center point area, centroid of the curve. We get the, let's say, a start point. End point. Either start or the end point of the curve. It really doesn't matter because in a circle, the start and the end are exactly the same point. So it doesn't matter which one you choose. And we will just measure the distance between them. Let's say start point and the centroid. We get a distance. And that's some sort of a value. 38.465595. This is too much, too many digits after the comma. I only want 2 digits after the comma, for the precision. So the way I personally like to do it is I like to multiply this by 100. Multiply this by 100. So that I get 3846, right? Then I convert this into an integer number, which integer can only be full numbers, meaning there's no more digits after the comma. And then I divide it by 100. It looks clunky here because I'm using panels, but it's actually pretty decent. And then what I get is 38.47, right? So initially what we're doing is we're just choosing how many digits after the comma we want. If I convert, if I change this to, let's say maximum is 1,000, and change this to 1,000, then we're gonna have 3 digits after the comma. 100 gives us 2, and 10 gives us 1, right? Okay, so now we have our radius number. That's cool. I want to also get that r equals before this radius number. So I'm just going to create a panel and I'm going to write r equals, that's it, right? This text right here. Okay, and now I want to join them up. Text join. It's under here, text join. Oh yeah, and I forgot, I need to get them into one list. So merge r equals and 38. Looks like that. Text to join. Joining, if I keep this empty, then it's not going to add anything in between them. And if I look at the result, I have my r equals 38.47. Okay, great. I have my maple and I have my r equals 38.47. So now I can merge these into one list. And I can join. Text join again. You need to flatten this, sorry. You need to right click, flatten for them to actually be in one list. The moment I saw the dashed line here, I know that this merge is shitting the bed and we need to right click, flatten for it to actually work. Then if I look at the result here, it's going to be, okay, it's upside down. What the hell? Okay, fine. We need to flatten here and here instead of here. So you flatten the inputs, not the output, and then it's gonna say maple equals 38.47. So the joining symbol should be the spacebar. Panel, spacebar. Connect that one in here, and now we get our nice little space. So that's, you know, some text operations there. Of course, there's a much faster way and, you know, easier of how to do this, but it's this is very pedagogically because I show you like everything step by step. Out of all of these, there's also text length option, which when you have a lot of texts that are very similar, it's very useful to filter out the ones that you need. So if I look at that, text length in this case will give me amount of characters that there are. I can also get the text length by breaking the characters and measuring the list length right here. That's going to be 10 as well. So basically that's a shortcut for this. Okay. So now when I have my maple r equals 38.47, how do I place this where, you know, in this position? Well, I used text tag 3D, not just regular text tag. I use text tag 3D, which asks me for a location. The location is going to be the plane, the original plane for our text entity, like that. The text to display will be our maple r38.47. And the size, color, and justification, I mean, technically you could get the text size, font size and color, but instead of doing that, I will just create my own. So size, let's say 15. That's a little bit too much. 11. Color, whatever, and justification. It says bottom left, but it should actually be top left, right? Top left. Okay. And now if I hide this, it's also here. Bam. Hide that. Now I get my maple with the correct radius, and if I scale this, you know, the radius updates. So to get this in, I just bake it, default, okay. And I have myself my, you know, parametric way of how I can override the existing text. In this case, you know, it's oversimplified system, but in most cases, I mean, that's how you do it. That's how you work with it. So for now, I'm just going to keep it as it is. And that kind of concludes the text part. It's honestly not that difficult. It just builds up when you need to, you know, separate out precisely the element number 5 in the text line or stuff like that. But I believe with list item, you know, separating this into characters and then using list item to get item number 4 or item index 4, which is the letter E. At this point, you should be able to kind of extrapolate on that and understand how that works. Next chapter. Okay, custom previews, custom representation of geometries that you create in Grasshopper and are shown in your Rhino viewport, but are not baked. That's an important distinction, right? So how can you showcase things not in the, in this way, in this color, right? Specifically, when you're looking at it in the Arctic view, doesn't look that great. So for this example, or for this portion of the course, I will be using the same geometry that we have created in our transforms chapter. The last one, that was the box morph, right? So this dome shape right here. And the easiest method of how to actually create a shading system for this dome, or this is actually not a single dome, it's an array of elements, right? Shaped like a dome. You can just use custom preview node, custom preview. This bad boy right here, which is located under display tab, under preview, there's the custom preview node. And if you just simply connect it like so, then automatically it's being shaded in this pink, hot pink color, or bubble pink, I don't remember. Yeah, I don't remember what's the name of the color, but pinkish color. If I go to Arctic view, you can clearly see it. Right now there's two pieces of geometry overlapping each other because box morph has not been hidden. I'm going to hide it. And now you can see this pink shiny color in the Arctic viewport. Right. If I then want to control the color of it, just the color, I would use a tool called swatch, color swatch, which basically does not give us, I can connect it to material input here. It does not give us any control over the shininess or reflectivity or anything like that of the material, but it gives us full control over the color. So if I click on the color here, I can then find, any color that I want. I can also control the alpha value, which is the transparency with the swatch material, right? So I can make it a little bit more transparent here. So that's the color swatch. A more advanced version of this. Oh, by the way, one more thing. If I hide the custom preview right here. That's interesting. Okay, sure. If I hide custom preview, it hides. It used to still show up, and you would need to right click and untick the render portion, but for some reason it's kind of hiding, which is weird. I don't know. So hiding custom preview hides the actual geometry now in Rhino 8, which is fine. We just get used to it. It's okay, so never mind. If I want to enhance this material, I wouldn't use a color swatch. I would actually create, under preview, I would create a material here. Bam. And the color swatch would go into the diffuse input, like so. And the material would connect to the material here. So what's the difference? Well, now I have the possibility to change the specular color, the emission, the transparency, and the shine through the use of the create material node. So the specular, if I hover my mouse over it, you can see, color the specular highlight. Right now it's set to white. If I use my color swatch, connect that to specular, and I change it to something that is not white, in the Arctic view, I guess that does not show up. I guess we would need to change it to ray traced for it to show up. Let's see if it shows in the rendered view. No, also doesn't care. Okay. Let's jump for ray traced, see if that helps. I'm about to give up. I think it does. It's hard to say. I personally use V-Ray for rendering purposes, so the specular color I don't, I don't mess with. Generally speaking, I create V-Ray materials instead. Emission color, that is set to black. If I set it to white, then suddenly this starts producing light, right? Again, if I go for ray traced, well, now you can't really see anything, but that geometry is indeed producing light in ray traced mode, right? That's emission. Transparency, that is definitely not a color. That is a percentage, so 0.5 would be 50% transparent, opaque, and so on. Right. once you're very close to 0% transparency, it starts behaving weird, so be careful with that, you know. You want to be either transparent or completely non-transparent. You shouldn't be very close to being transparent. And the last one is shine. You can, if you hover your mouse, you can see what kind of inputs you can have. 0 is non shine, 1 is low shine, 100 is max shine. So if I just create a slider saying 100, connect that to shine, now my object is all shiny. I will just really quickly check if the specular will react to it now. Red. Really? Nothing? Ray traced? Okay, still absolutely zero reaction from the specular. I guess, well, there's something here. I don't know. Let's not play with it too much. But you get the idea, right? You can construct any kind of a material with different types of shininess attached to it. Okay, let's go one step further. Let's apply a different material for every different tile. For that, I will be using a tool called Gradient. Under Preview, no it's not, I'm lying. Under Color, that is going to, I'm lying again. Where the hell? Okay, Gradient. Is that going to be under Input? Yeah, okay, that was under Params Input. Gradient is located there. This basically generates a set of colors, right? So how can we generate a range of colors for this entity? Well, I can say that, well, 0, 1. Okay, I can say that I just want a range, like to create a range of colors that would coincide with the amount of elements that we have. So the first thing that I do is I measure the list length, because I need to know how many elements I have. And I get 225, and that becomes my upper limit. Bam, like that. So basically, element 0, number 0 is going to be green. Element number 225 is going to be red. And then for the parameter, I will just create series of numbers. And I'm going to count them 225 times. So imagine this, it's basically going to, since this is at 0, green is at 0, red is at 225, is going to just go first element, green, second element, you know, which is number 1, also kind of green, element number 120, somewhere in the middle, yellow, and so on, right? So this basically generates a bunch of colors for each element individually, and if I connect that to the diffuse color, I can, you know, see the pretty colors, right? And of course, you know, since it's counting like so, this is element 1, element 2, element 3, element 4, element 5, you know, the rainbow kind of appears here. By the way, if you don't like the colors, you can right click on them, hit presets, and you can find, you know, a color theme that works for you. You can also push and pull on these little sliders to adjust the color distribution. Okay, so that's one thing. Another thing that I would like to show you is once you get those colors, you can actually shuffle them around. And the tool that does that is called Jitter. Jitter. It takes a list and it shuffles it, you know, inside. It just literally jitters the list. So the values that you get randomized. And you can specify by how much do they get randomized. So my jitter value, if that is 0.5, that's going to steer towards a certain angle, I guess. And the bigger the number, the more random it is. The smaller the number, the closer it is going to be to the original, right? So you can kind of have it randomized, which is kind of nice. Okay, so that's one way. Another way is you can control the gradient. Let me group this up. You can control the gradient by simply measuring hotspots. What are hotspots? By measuring the distances between attractor points and these elements. So let me show you an example. Let's say I have these two points here. one here in the top, actually both in the top, just floating about in space like that. This one's here a little bit closer, these 2 points. And I have a bunch of elements, right? So what I can do is I can first of all reference in the points, right click, set multiple. So now these 2 are referenced in. And for these elements, I can say, okay, give me the volume centroid of these elements. And it's going to give me the center points for each of these guys. By the way, notice that this takes almost 100 milliseconds, which is pretty long. So what I can do is I can convert them into a mesh, I believe. That was stupid. That takes 1.4 seconds. Never mind. We don't do that. We're okay with 100 milliseconds. So basically from these 2 points, I will find the closest point for these centroids, or either from each of these centroids, I will find the closest point out of these 2 points. So I'll just measure closest point. I'll use the closest point tool. So from these centroids, I try to search for the closest point in the cloud. I will draw a line just so that it's kind of easier for you to see what kind of a measurements it's making. From here to here. See? Let me turn on the color display so that it's a little bit less. Yeah, there we go. So it's making these measurements and it finds which ones are closer, right? So those measurements that I get are here. Those distances are here. And I can remap them. Remap these distances from the biggest and smallest one. So I need bounds, as what we always do. We need to find the smallest and the largest distance, and we need to create the domain from them, like so. And I remap them into a target domain, which is going to be by default 0 to 1, which is great. So now my remapped numbers are always going to be between 0 and 1. So now what I can do is I can create a gradient again. Create a gradient, and I can say my lower limit is 0. That's good. My upper limit is 1. That's good, because all of these numbers are between 0 and 1. My parameters are these mapped numbers. And then according to, if it's close, it's going to be green. If it's far away, it's going to be red, right? So we color it that way. And I'll just use custom preview again, custom preview node, hide this one and use this one for the geometry, the box morphed geometry, and connect the gradient to my material. Bam. Voila. Now I have hotspots. Right? And let me change the preset to something like this, and maybe make it a little bit more tolerant. There we go. And now this measures, how close things are getting to it. In this case, these 2 points, and colors it. You can of course color a slope this way. I have like tutorials for that as well on the YouTube channel. You can just roof slope Grasshopper and you'll find it. And you can color a bunch of different things this way, right? So that's the custom preview in a nutshell. Let's see if there's anything else that I want to show you. I already showed you the vector display node multiple times when I was talking about the vector. Point list node also showed you when I was talking about points. Nothing here, nothing here. We did the text tag 3D, nothing here. And you can construct a color from red, green, blue, like from 3 numbers, but that's very simplistic. Okay, I think that's kind of it, honestly. Internalize data here. Okay, that's an easy chapter. Let's move on. So there is one thing that I skipped over, and now we're coming back to it because now we have enough knowledge to actually work with it, and it's called fields. We had points, we had vectors, and under the vector tab, we had planes, and we also have fields. So here, if I were to describe what a field is, it's basically a data type that was introduced in Grasshopper 0.9, I believe, and it's a data type that deals with forces in space, right? So imagine it's basically you have a space that is filled with forces going at the different directions. Think of wind, for example, and then if you say, I want to know exactly the force at this particular point in space, this right there, in this particular point in space, and it's going to say, well, the wind force, for example, let's say wind or magnetic force, doesn't matter, at this point in space is going to the left, and it's at the strength of 5 or something like that. And then you say, okay, what about this point in space? And it goes, well, this point in space is actually going to the right. It's at the strength of 3. So those are fields. It's basically a space filled with forces, and you only can see them when you evaluate that space at a given point, or a grid of points, if you will. We'll do that as well. So here under fields, we're going to look at most of these. And the easiest way to create a field is actually to create some point charges, some points that introduce a charge, introduce a force in the field. So I'm just going to place one, let's go for 1 point. Why not? YOLO, 1 point, right? Just this little guy right here, right? And I'm just going to reference it in as a point. Right click, set 1 point. There we go. And then in the field tab, I'm going to apply a point charge for it. Point charge requires me to give it a point. We've got that. Notice how the icon immediately changes. Can I make it bigger? No, I can't. Okay, so the icon immediately changes. So it's a force that is pushing out from the point. That's what the icon shows. Then the charge, since it's a positive, it is indeed pushing out. If I had a negative charge, -1, it would be pushing in. See, it's changing. And then you can mess around with it. For now, I'm going to keep the charge set to 1 for this particular point. Then decay is how fast does the power, the strength of this pushing fall off the further we are away from the point. And bounds is when do we stop calculating, right? How far does it reach? How far does the calculation reach? In this case, we're doing it unbound. Okay, so that generates a field. As you can clearly see, there's nothing that we can really see. That's because a field, just like a vector, needs to be evaluated. So how do we evaluate it? Well, let's start with 2D stuff, right? Let's just simply create a rectangle. Do we do random? Let's do random. Let's create a rectangle, reference it in as a curve. Set 1 curve. Populate. 2D. That's going to be our region. And for now, I'm going to keep the count set to the default value of 100, right? We have all of these points. And I will use these 100 points to evaluate this particular field. Actually, I'll show you here. Evaluate field right here. Evaluate a field at a point. Bam. We've got the field here. We've got the point here, or points here. And what we get from that is a tensor and a strength, right? A tensor and a strength. So this is going to be a very weak field because the charge is 1 and it's decaying very fast. But I believe if we just look at the tensors, which are, by the way, tensors are vectors. For the sake of argument, just put an equal sign in your head for it. Tensor equals vector. So if I do vector display right here, I anchor, the vector that I show is here, and I anchor it to my 100 points, like so. You can see that it generates a bunch of vectors that are pushing away. And let's do a little bit of amplitude shenanigans for the vectors. Let's increase the amplitude to 500 is going to be an overkill, 5. Or is it? Wait, is it so small? Okay, 500. I think I did a very big rectangle. Yeah, I did a very big rectangle. Let's make it smaller. Boop. There we go. And now let's shrink it a little bit. Apologies, the rectangle was way too big. So now you can clearly see that, you know, this point is pushing all of these other points away. So it's generating, sorry, it's generating this kind of a push effect. Okay, what if we want to have 2 points, right? Bam. And I just, instead of 1, clear values, I give it set multiple points. I give it 2 points. Well, that seems weird. There's like one vector that is looking to the left and all other are kind of reacting to this, and this one, you know, only this point is reacting to this vector. So that clearly something is wrong with it. Wait, my voice is gone. Clearly something is wrong. And the thing that is wrong is that 2 points actually generate 2 fields. If I look at it with a panel, it's 2 fields here. So what I want to do, I want to merge them into one. And I can do this by using the merge fields tool right here. Bam. That merges like that. And now I have 2 vectors interacting with each other. And the interesting bit, of course, happens when they meet. Right there. You know, how does the direction change? Let me increase the count for this. So I'm going to say 200 points. Bam. Let's go for more. 500 points. And you can clearly see like a direction of them pushing one another away. And it's like a magnetic field. It does have that kind of a behavior, right? So merge fields when you use more than 1 point or more than one of anything here. Because you can also do, for example, here we have these 2 points. So I can draw a polyline through them, which literally is just going to create a single line segment, right? Like so. And then I can use line segment, sorry, not line segment, field line charge node here, and use that. And then this becomes a line charge that affects the grid, right? So then you can have like 2 line charges here and so on. So maybe I will do so. Let's say 1 here, 1 there. Why not? And this one is a little bit pushed in. These 2 lines. So I can disconnect that and just grab a curve component. Right click, set multiple curves, connect those as lines, right? So, you know, stuff gets kind of squeezed in here. That's fine. And then for the points, we can just literally connect them to the field and holding the shift key, connect that to the merge fields as well. So suddenly the points have an influence, the lines have an influence, everything has an influence over the field. So we can construct a pretty intense, pretty intense structure this way in terms of, the directionality. So visualization of it via vectors is great and all, and of course you can then use the vectors for different things. So for example, you could use the vector to just create a line. So instead of vector display, I can do line SDL, start direction length, to construct a line, right? And I can use the vector, well, the tensor in this case, for the start. Sorry, apologies. Direction. Tensor is actually direction. The start is the points from which they should start, like so. And then I can control the length with, this number slider that I had here for the amplitude, right? So now I have a bunch of sticks, then I can then extrude up and so on, right? To construct some geometry. I will not be doing that in for this particular portion of the course. So we're stuck with the with the arrows. All right, so that's like a 2-dimensional field and how you operate it. We start with that. Then continuing on, if you were to work with a 3-dimensional thing, a 3-dimensional geometry, that absolutely can happen, or rather you absolutely can do that. So let me just really quickly internalize data here, internalize data here. Hide these guys. And let's create some fancy three-dimensional, like weird stuff. Why not? A quick little, oh, forgot one. Internalize. Forgot this one. So, for example, if I were to, let's do a completely parametric model. So first, let's create a box in which everything is going to be calculated. Let's do a center box. Center box, and I'll say it should be a cube of 100 by 100 by 100. That. Once we have this box here, then we need to populate it with a bunch of points, just like we did with the rectangle, right? So I'm going to use this, in this case, populate 3D, because box is three-dimensional, right? Populate 3D, like that. And I'm just simply going to grab the box and put it in the region, right? So it gives me 100 points. For now, I'm going to keep it as 100, but then keep in mind, I will be adding a slider to this later on. So that's done with the points. Now we need to create some charges in here for the box. We could populate 3D again, but I think maybe for you it would be more nice to learn how to create a point at any given place in the box. So I'm going to be using point charges rather than line charges. Let's hide the populate 3D for now and just look at the box. If I type in evaluate box tool, evaluate box, it basically gives me U, V, and W parameters for box evaluation. And if I just connect it here, it gives me the center point of the box because U, V, and W are all set to be 0.5. So if I were to just create a slider of 0.5, here, here, and here, just Control C, Control V, copy pasting, connect it. Now I can control a position of a point inside of a box with this slider. You can see me, moving it along the U direction, moving it along V direction, and moving it along W direction. So what I can do is now I can create, or I can get a point anywhere proportionally on this box. And I'll do so with 2 points for now. Evaluate box again, and just give it different numbers. Right? Something like this. Okay, so now as we have these 2 points, I will give them point charges for both of them. So holding down the shift key, I'll give them both the same charge of 1. If I want to give 2 points that come in here 2 different charges, I would need to create in the panel, I would need to create 2 numbers, 1 and 5, for example, and I would need to give it remove the multi-line data option from the panel. Right? Now these are 2 charges. First point has charge of 5, second point has a charge of 1. I don't want to do that, so I'm going to keep it as 1 for both. The decay goes beyond, just simply goes to 2, that's fine, and then the field is generated here. Rather, 2 fields are generated, right? Don't forget to merge the fields together so that the points actually influence one another, like that. And now as we have our population of points and we have our field right here, I can actually, evaluate the field. But instead of doing that, this time around, I'm going to use the field line tool because I want to show it to you. Field line, field goes in here, points go in here. And it just shows me how would a point travel within that, this kind of a field. And let me just increase the populate 3D count, how many points there are, to something closer to like 600. And you can clearly see that the 2 points that are pushing the field away. And if I move, let's actually see them. There we go. If I move one of these guys over to here and the other one over to here, I'm just positioning them into the opposite sides. you can see, them really literally just kind of hit each other like that, right? So we produce some pretty interesting field line results. Of course, these are just random points populated in space, so not really architectural, but could be used for some interesting patterns. With that being said, you can, of course, increase the amount of steps. Right now it's set to 1,000 steps. If you do 2,000 steps, the curves just grow further. So you can control the, how far they grow, and you can also change the accuracy if the calculation of this takes too long. You can, of course, also use the box to introduce the point charge bound, so that anything that goes beyond the box gets trimmed away, or rather the forces become zero, thus the field line stops moving, stops growing beyond the boundaries of the box. I have removed the bounds in this case. So those are point charges. For the evaluate box, let's actually group this up, hide it, call it a day, and then make a copy of this whole thing. Delete the group and delete the evaluate box. Let's make some, and delete the point charges as well, but keep the populate 3D as well as the field line and the merge fields tool. A different way of how you can just create a bunch of points in the box is by using the same technique, populate 3D with a very low count, 3, for example. And don't forget to also change the seed, 666, whatever. Change the seed so that the randomness of this and randomness of this don't overlap, right? And then I just add the center box into the region, and we populate these 3 points. And now we could use point charge again, but in this case, I'm going to use the spin force charge, and that's going to be the last thing that we do. Spin force charge asks us for, actually it asks us for a plane, which is interesting. If we just give it points, it's going to force the points to be horizontal in their spin, which is absolutely fine. Later we can change the planes for them, make them a little bit fancier, but for now that's okay. Then the strength, radius, well, we can increase the radius of these guys to like 50 or so. Bam. That's basically the radius of the spin, and let's just connect it. I just want to see how it looks like. Voila. We got ourselves this kind of a spin force, right? There's clearly something that we can do with this as well. With that being said, I believe that it would be for a spin force. Let's group this and save this. But for a spin force, copy paste, I actually like to be very methodical or very precise with the position of the planes where that are being used for the spinny boys to be oriented along, right? So what are the planes? So instead of using a random populate 3D, I'm actually going to, for this center box here, I'm going to be creating little rectangles like so. And I'm just going to do like 3 of them. 1, 2, 3. For now, they can just be, okay, I even missed them completely. They can be just here, that's fine. 3 rectangles. And I'll reference them in here as curves. And the nice thing about flat rectangles is that if I were to just say is planar, test curve for planarity, if I use this node right here, the output that it gives me is not just the answer that they are indeed flat, that they are planar, but also it gives me their planes that I can use as planes for the spinny force things, right? And now I can start breaking them apart. But before we do so, let's look at the fields. Right now it's just a mess, right? Because everything is also spinning in the same direction, right? So it's not, there's no counter force. Everything is just going clockwise or counterclockwise. I'm not sure. Seems like it's going counterclockwise. So, but if I rotate one of these, You can see the influence that this has. Rotate another. Rotate the third one. Like that. And now we're starting to get somewhere. It's starting to become quite a bit more interesting. We're starting to build up a structure here. Well, not a structure, that's far-fetched, isn't it? But something interesting, something with which we can start designing. Look at that funky little spiral there. Okay, so now let's reduce, and this is it. This is how you operate with fields and how you can generate, insane amounts of complexity really quickly. Let's reduce the complexity to something like 250. And to make this structural, you can actually make this structural, by the way. All you would need to do, I will show you one more trick, one more step for this. I would take these curves, I would divide them up. Divide these curves. Actually, I would probably divide them. Sorry. I wonder if you have rebuild curve. Let me check. Well, it says that you should have it. Nah, let's do a simpler method. So I will divide length for the curves, and I'll divide them every 10 units in length, right? So I get these points, right? And then with these points, I can then do proximity check. So I basically can say that every point should find at least 2 or 3 neighbors. A tool that does that is called Proximity 3D, and it's located under, I believe that was Mesh, triangulation, nope, yes, Proximity 3D, this bad boy right here. Bam. We grab the points, we connect them in here. And you can see that right now, it seems like the points only see other points that were on the curve. And that's due to the data tree. Next chapter, data trees, by the way. That's due to the data trees, and that, this is a separate list, this is a separate list, this is a separate list. So they can't see anything else. So to force them to see something else, we can right click and flatten. Bam. And now we're starting to get a little bit of a structure in here, right? Neat, huh? So now with this structure kind of working, I can check the links. I need to flatten this again, by the way. Check the links. I have 13,600 of them, and I can remove all of the duplicates, because if this point is able to connect to this point, that means this point is able to connect to this point. So there's like 2 lines there. So if I remove duplicates, remove duplicate lines, bam, now we're left with 8,000 of them rather than 13, I believe. Yeah, 13,600, much better. And with 8,000 of them left, I believe YOLO, multipipe will work. Let's just see. Actually, let's save first. Save that. And internalize something. Internalize that. There we go, save it again. And now we do this, because this is going to be heavy. I know it. Come on. Oh, 4 seconds, didn't crash. Still calculating. Oh, there we go. That works quite well. It is a little bit spiky in certain places, though. It does break, unfortunately. We were so close to glory. So close, yet so far. Unfortunate. Maybe we can reduce the spikiness. Actually, I wonder. I wonder why. Just give me a second. Oh, it's because of how many lines connect at a very sharp angle. Okay, gotcha. So we can't use multipipe. Instead, I will use a mesh pipe tool. You might not, you probably will not have it. But, okay, so don't do it, just see how I do it, I guess. Because unfortunately you don't have it, and we are not there yet with the creation of plugins, or not creation, but downloading of plugins. So if I connect curves, are there parameters? Oh, there are too many parameters here. Okay, I'm just all over the place. I'm tired and I want to go home. Let's stop. Multipipe reaches its limit with this. It's unable to fix it, which is absolutely fine. That's okay. I believe if we were to say that the group proximity is actually set to 3 rather than 5, that should be better. No, it's still very yucky, very messy, so can't expect that to work. So you would need to just use a regular mesh pipe or to use a cocoon shape. Actually, one thing that I could show you before we end here in this this chapter, if I bake this into Rhino, I probably should have selected, okay, undo, delete those. If we bake this into Rhino, I believe that we can use shrink wrap for this structure to make it sound. So as long as you have Rhino 8, shrink wrap. Oh, it doesn't want these guys to be shrink wrapped. Okay, never mind. Then I probably should just give up. You would need to mesh pipe it and then shrink wrap it for it to be a 3D printable structure. There are multiple ways of how you can do it, but we're probably, I would guess, at like a 6-hour mark, something like that with the video. I'm really not sure for how long I have been recording. So we should stop and we just move on to the next chapter. That's how you get a bunch of curves that look structural, that are actually structural, and that would hold themselves up. That's it. Next chapter. We move on. It's time. It's time to talk about data trees, the nastiest and hardest to understand thing in whole Grasshopper. If you grasp data trees and data tree structures and how to operate with data trees, then you're basically able to do anything you want in Grasshopper, but it takes a while. And the concept of a data tree is quite simple, really. It's a list of lists, potentially of lists, of lists, of lists, right? A data tree can be not just a list of lists, but those lists can have other lists inside of them and so on, right? And operating with that becomes quite tricky. So I guess we begin by me kind of showing you the use cases, or rather not the use cases, but the most basic data tree that we could create. If I go here, and first I'll do a synthetic example, right? I'm just going to create a panel and I'm going to make a list. My favorite: cat, dog, mouse, horse, chicken. I'm going to make another panel: A, B, C, D. Only 4 letters. 5 animals, 4 letters. I'm going to make another list. 1, 2, 3. Right click on the first one, multi-line data. Second one, multi-line data. Third one, multi-line data. These are 3 separate lists, exactly the same as what, for example, series generates. The series node generates, right? These lists, as you can see, have indices, numbers, where the item is located in the list, and also the lists themselves have their address. Think of it as, yeah, the address of the list. So since these exist in a vacuum, by themselves, all of their addresses are 0, 0, 0. For some reason, the address of this list is 0, 0. That makes no sense. Why are these zeros and this is 0? Well, not comma, but the weird icon here, I forget the name, 0. So why are there 2 zeros here? Well, that's because some of the nodes, when you use them, add an additional 0 to the address. Ask me why. I don't know. I really don't know. But you do that, and that messes things up. Because remember how from time to time I would flatten things when I use merge? I'm trying to find an example of that. Well, actually, let's just try to merge these two lists. Merge. Oops, wrong. Let's try to merge these two lists into one list. First comes 1, 2, 3, and then comes these 1, 2, 3, 4, 5, and so on. And then we look at the merge output. Bam. It didn't merge into one list. It actually merged into two, even though this is 0 and this is like 0, 0, which is literally the same, but they don't merge. And this drives me crazy because they should, right? So when I did right click, flatten, I eliminate that information, that 0, 0 information, and I just push everything into one list on purpose, right? So I'll come back to the flatten in just a second, but that's why I did it, right? So that trust me bro moment, that was why why I was doing it. Because things wouldn't merge into one list and I couldn't operate with everything. I couldn't join, for example, all of the geometry into one piece of geometry because it was still in separate lists. Anyway, moving back here, one way of how you can actually eliminate the 0, 0, this problem, is by right-clicking on the output of series and choosing to simplify. Simplify the data in this parameter by removing all redundant path indices, I guess? No, path elements. Redundant. This 0 is redundant. If you're not sure what redundant means, Google that word. Quite a useful word. Redundant. I click on simplify. Are you kidding me? I was really... Okay. Do I simplify this then? Okay, it doesn't work. So this is not redundant then. How is this not redundant? Okay, I just flattened this, whatever. Flattening kills it. I'm not sure why simplify didn't work, and I did the whole speech and so on. I'll find another example where I can actually show you simplify at work. Simplify should have removed that additional 0 from the address. It didn't. So what I did is I used flatten. Flatten all data in this parameter into a single list, and that just killed the address, simplified the address automatically. So that works. For some reason, simplify didn't. Okay, god damn it. We move on. I guess I can keep this in here just as an example. Let me group this up, but let me yoink back the 1, 2, 3, this list right here. So for now, let's make a data tree. So if I use merge on these three guys, merge, that's not going to be a data tree. That's going to be us making just a longer list, and I can show you how that looks like. Bam. Cat, dog, mouse, horse, chicken, ABC, D, 1, 2, 3. Right? Just takes D1, reads the whole thing, then attaches D2, then attaches D3. Right? And just creates a single list. You can see only one address, a single list that, just has all of this. To actually work with these three lists, and let me delete that. To work with these three lists as a data tree, we need to use a command or tool that's called entwine. Entwine. Flatten and combine a collection of data streams into a data tree, I should say, right? And even here it says branch 0, branch 1, branch 2, and so on. So I connect this list to be my branch 0, this list to be my branch 1, and this list to be my branch 2. And it tends to flatten by default, which is great. Basically, anything that comes into branch 0, it will make sure that, you're running the flatten tool preemptively, just to make sure that all of it comes in as one list, because it's going to mess things up if you don't, right? We have our entwine, and if I look at the result of it, you will see that I have my cat, dog, mouse, horse, chicken list with this address right here, 00, ABCD list with 01 address right here, 123 list with 02 address right here, right? So I have these three lists in one output, and you can see that the line has changed from double line right here, a thickened line, into a dashed line. That means multiple lists are going through this line, a data tree. A way of how I can also display the data tree for you is by going to Param tab, Utilities, and choosing Param Viewer right here. And we're going to get to the interesting bit in just a second. Maybe something like that. And then the Param Viewer, if I just connect my result to it, is going to say, well, there is a data tree with 3 branches, each branch corresponding to the 3 lists that we have connected, 00, 01, and 02. If I double click, and by the way, it also says here N5, meaning that there's 5 elements in the first branch, 4 elements in the second branch, and 3 elements in the third branch, exactly as expected. If I double click on this, it actually shows me the data tree, the data structure, right? With these 3 branches located here, right? Branching out. And here are those addresses, right? Here are those, these rings are basically those addresses, right? And since at this ring, nothing branches out further, right? Nothing really happens. The branch just keeps going, continuing. That means that these points, they do literally nothing. They don't matter. And if I double click on this again, and I see the address, the same thing is here, right? 0, 0, 0, those don't matter, those don't do anything. Only 0, 1, and 2 really matter. So what I could do, please work this time, if I right click and I choose to simplify, oh thank God, if I choose to simplify the result, it removes those zeros, right? And we're then only left with the address of 0, 1, and 2. Branch 0, branch 1, branch 2. Double click that, now this is how it looks like. Only one of these rings, right? And there's 5 elements here, 5 elements here, the animals, 4 elements here, the letters, and 3 elements here, the numbers. If I right click on this and I untick the simplify, you can see that then, the additional complexities here, that is not needed. That's the redundant zeros. Okay, so that's, just keep in mind that sometimes Grasshopper tends to generate crap that you need to just use simplify to get rid of when dealing with data trees. So that's the first thing. And sometimes you don't even need the data tree, then you flatten it into one list. Oh, I can show you what happens. Data with 3 branches, and 5, 4, 3, right click, flatten, data with 1 branches, data with 1 branch, and 12. Everything pushed into one list, right? Forced into one list with 1 element, or rather with 1 branch. So that's the flatten. Okay, what does graft do? If we have flatten, we have simplify, we have graft, and we have reverse. I guess first I can show you what reverse does. If I click on reverse, every list inside of every branch, the data gets reversed. Back, so we now start with chicken, then it's horse, mouse, dog, cat, D, C, B, A, 3, 2, 1. If I unreverse it, now it's normal, cat, dog, mouse, horse, chicken, A, B, C, D, 1, 2, 3, right? So that's the logic of reversing. And then we have our graft. So this is the last one. Sometimes, especially when you're dealing with some specific geometry, and I'll show you an example of that quite soon, but when you're dealing with specific geometry and you want to isolate it and you want to work with it individually, like separately, you want to separate that geometry into one list, right? Into its own list, into its own data branch. I will show you first a much simpler example of this. If I just have this list, which is text, right? And I look at it, because you can't do anything with the panel, you can't graft the panel. So I'm looking at it, And here, and actually I'm also, sorry. I'm also going to look at it through the data structure. Oops, that's wrong. Through the data structure. Data, how is it called? The param viewer, I think. Yeah, through the param viewer. Data with one branch. Yeah, that's the single list. 5 items in the list. Double click on that. That's our list. Perfect. Now I right click on this and I choose to graft it. Bam. 5 items. Or 5 elements, right? 5 branches with one element in each list. So what it does, what graft does, is basically a reverse flatten. While flatten takes any kind of a complex data structure and just goes, okay, which one is the first? You're going to be the first item in the list. You're going to be the second item in the list, and just builds a single list from any kind of complex data structure. So simplifies it to hell. What this does, it takes any kind of a list or any kind of a data structure for that matter, and takes every individual element in that list and goes, okay, you are your own data branch now. You are your own list of one element now. Now you are your own list of one element. You are your own list of one element, right? That's what it does. And with a single list, the data tree looks like this, right? Just branches out. Also, I can simplify it, right? Again, because there's a bunch of zeros that are unnecessary. So if I simplify, bam, the zeros are gone. And, you know, the data tree looks like this. Easy. Hopefully. Then here, to showcase it here, if I right click, because here we have we already have a data structure, data tree structure with these 1, 2, 3 elements. And this is data with 3 branches. If I right click and I choose to graft it, there's 12 branches now with some fancy addresses as well. Because remember, it's still simplified. I need some space here, something like that. Yeah, that's going to be fine. So it's still simplified, right? So now there's like 2 numbers for the address, and you can see that it's 00, 01, 02, 03, 04, and then it's, okay, so once it counted 5, then it jumps to 10, 11, 12, 13, it counted 4, and then it jumps to 20, 21, 22, it counts 3. It's just exactly the same thing as here, 5, 4, 3, right? And then you can see also here that it's always one element in each data branch. If I double click this, then this is our data tree, right? So this chunk right here, clearly you have like 3 main branches, right? For the list 1, list 2, list 3, but then you produce sub branches because you're taking every element in the list and you're saying now you're your own branch, you're your own branch. So you're making smaller branches. So this is a more complex data tree, right? Which has, okay, there we go. Which has exactly the same amount of elements, but now they have been placed into separate branches. Okay, enough theory, because I guess without really showing it in practice, you know, doesn't really help. So let's go for some practical stuff. Example number 1. We have, let's say, a rectangle, something like that. Reference it in as a curve. Set one curve. I immediately internalize. I'm not going to change anything about it. And we make a surface out of it. By the way, you can just use surface tool as long as it's a rectangle and it's flat. Surface node. That will just make a surface through it. Boundary surface would also work, right? But anyway, it's a surface. Then we use divide. Divide surface. This is the simplest one that I can show you. And I'm just going to reduce the count. So in U direction, the divisions are going to be 3. So it's going to be producing 4 points. And in V direction, let's say it's going to be 5. So it's going to be producing 6 points. So 4 and 6 points. Let's check them out. In a panel, now let's go for the param viewer this time around. Param viewer. Okay. Data with 4 branches. These points are not in the single list. They are in separate lists actually, right? Oh, and ew. What the hell? Why does it have so much? Right click, simplify. Okay. I don't know. I don't know why it keeps adding those damn zeros. That's bane of my existence. If someone from McNeil is watching this course at probably like hour number 9, please answer me in the comments. If you answer properly, I will pin your comment and I will apologize. If there is no answer, then this is a bad tool, bad design, and this shouldn't exist. Okay. Rant over. Moving on. So 0, 1, 2, 3. Those are the indices or addresses of the branches, right? And now if I simplify it, it's quite straightforward. Every single one of these 4 branches has 6 points in it, right? This is branch number 1. This is branch number 2, branch number 3, branch number 4. Think about it as columns and rows. There are columns, and in each column there are points, right? So let me draw that for you. Sure. Let's do 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. Change this to red. And we have these points here, right? 1, 2, rather, we have, according, what the? Close. Sketch attributes could not be set. We don't know why though. Okay. Cancel that. Please don't crash. Save us. Scary. Scary moment. I'm going to let it save. Oh, it's a little bit crashy. Anyway, so for every row, we have 5 or 6, sorry, we have 6 points, right? So in every row we have those 6 points, which I'm trying to draw, but it doesn't work. And all of these, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Come on, 4, 5, 6. I'm rushing. I'm rushing. I'm lightning fast. Okay. And all of these, if I were to draw the indices or write the indices of them, this would be 0. This would be also 0, also 0, also 0, right? And if I were to look at it with a panel, zero index, 0 index, 0 index, 0 index. So those zeros are these points right here. And I can actually fetch them for you to show it in the Rhino viewport with list item. List item, list. By default, the index that it's fetching for us, extracting for us, is indeed 0. So the items that are currently highlighted, the green ones, are the points, at index 0. And I can even show it to you better if I guess if I hide the surface. No, I'll show the curve. So I can show that better, like so. And I can also, if I also hide the curve, I can do polyline through them. Actually, I can't. Okay. This is going to be also a learning experience a little bit. Since there is still a data tree here, after I fetch them, they're still in separate branches, right? So the data tree is exactly the same, right? For the list item. If I connect it here, it's still 4 branches, but now it's 1 element in each branch. And what that does to any kind of a mathematics or any kind of a function that I'm trying to do with it is that it won't work. The points don't see each other because they're in separate lists, right? So they don't exist to each other. So if I do a polyline, it's just going to complain and going to say insufficient points for a polyline, right? And it says that because, well, it goes to this list and it goes, yo, you're just giving me 1 point. I can't do anything. It goes then to that second list, goes again, 1 point. What do you mean? I can't do anything. And so on, right? It can't draw a line at one point. So what do we do? You already know. I'll give you a hint. Trust me, bro. Exactly. Right click, flatten. They're now pushed all into one list. The item from the first list, the item from the first branch was pushed to the top of the list. Then item from the second branch came. Then item from the third branch came, and so on, and everything just collapses into one list. And now polyline goes, oh, okay, 4 points, no problem. Say no more, I've got you, bro. And it just draws the line here. If I were to, so that's list item with index, when I use index 0. If I use index 1, for example, then it just goes through the next, next row of elements, next row of point index 1, right? And catches those. So the question is, or actually I should delete that one. The question is, if we are able to draw a polyline there, give me a second, I need to clean this up a little bit, get a little bit of room in here so that it's not too cramped. So that is going to be its own example. I'm just going to place it here real quick. And then we will continue on. Okay, you go here. We continue on maybe like so, something like that. Then the next question is, okay, what would happen if I were to flatten this output here, right? How would it read? How would it draw, right? Because here it's like, let me show you. Here it's like 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. If I flatten all of this, this becomes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So technically, if I were to flatten this, the polyline through these points would make a zigzag, right? And that's exactly what it's going to do. So if let's go to our set tree, and instead of using flatten here, because I want to keep this logic here available for you to see, I'm going to actually use a node that does the flattening for me. And the node is going to be called flatten somewhere here. No, it has to be, right? Yeah, there we go. Flatten tree. Flatten tree node. Ignore the path. Okay, it's basically what kind of name for the list would you like to give once you flatten the tree. Keep it as default. You honestly almost never need to change the path. But after we have flattened the tree, that's exactly, by the way, as right-clicking and choosing flatten here. Exactly the same thing. And I draw a polyline through it. Let me hide this polyline though, so that it's not in the way. Bam. That is exactly, well, okay, it was inverted. But besides the, so this was the 0. Besides that, it draws the polyline exactly as I said it would, right? As this zigzag. So that's the logic. That's the logic of data trees and operations with them. You might think, okay, so what? What do I do with it? What's the reason? There is a next example. I'm just kind of thinking about where to start with the next example, the reason for it. Okay, let's do a quick paneling thing for me to explain it to you. So this gets grouped up somehow. Sure, a little bit bigger group, but that's fine. This gets grouped up, and let's make why is this? Oh, okay, it's still here like that. Is this internalized? Yes, it is. That's great. So let's make some sort of a paneling structure. For that, I want to make a loft, I guess. But we did a regular loft before. Let's do a loft from circles. So just draw one circle, another one, a little bit thicker boy, another one, a little bit thinner, one more, and I think one more. Yeah, why not? 5 circles, something like that. gonna be looking like a bong. Loft. Ew. Don't like it. How do we make it nice? I think by tilting the big one. Oh, that's too much of a tilt. If we tilt the big one, actually let's start lofting here. So let's just reference in the curves and then we will learn how to make it nice. That's another nice thing about lofting in Grasshopper is that then you can just adjust the curves and you get, you know, the nice loft that you want. So I just reference in all of these curves in here and then I just use a loft through them. And now I'm just going to be adjusting those curves so that they look nice. I think for the loft options, I kind of want to use loft options. I want to use a different type of a loft that would be, instead of a normal, right click on this, choose loose. Yeah, that's nicer. Loose loft tends to be a little bit more elegant when it comes down to this kind of stuff. I'm just going to minimize the size of these. Bottle. Sure, it's gonna be a bottle. And then this maybe can be rotated and moved away in a weird way. Maybe we scale it a bit here and we scale this a bit more here so that there's like a nice crease here. Something like that, why not? Yeah, whatever. A bottle looking facade thing. For this example, that's gonna be fine. Internalize that, delete the curves. Don't need the curves anymore. So this loft, right? I will divide it up into segments, into elements. And I will use, let's get a refresher. Let's use ISO trim for this. ISO trim, which asks us for a surface. We do have it, we have a loft, and asks us for the domain. So for that, I would need to use divide domain squared. Divide domain, wait, is that squared? No, my bad. Divide domain, it needs to be squared. It needs to be a two-dimensional thing or else you're just going to be out of luck. Divide domain squared, the loft is our domain, the segments go into the ISO trim, and for the U count and the V count, we can mess around. So we can say, okay, I'm thinking, how much? Let's go for like 15 by 15. Don't need more. Something like that. Okay. We have all of these 225 surfaces, right? And now for these 225 surfaces, I want to create like I want to operate with them separately and I want to get their edges, right? I want to offset, oh, actually I can draw. So for every surface, I want to extract their edges. I want to offset them inwards. And I want to make a loft between them, like that. This is going to be, I'm trying to make it as simple of an example as possible. Beautiful drawing, by the way. Wait, I need to sign this. There we go. The date, 2024. You're welcome, NFT. So that offset, to do it, I actually need to just, for every surface, right? I need to get brep edges. Brep edges. And you will notice what happens when we do that. Brep edges. And if I look at it, here, this is actually like something that happens under the hood and you need to be very mindful of it happening. So you constantly check what kind of data tree do you have. Here, if I check with the param viewer, one branch, 225 elements in the branch. Great. If I check with the panel, easy. One list, you know, in that branch, a bunch of surfaces. Great. That's what I want to see. After I extract the edges, really thinks that, okay, you definitely don't want to place all of the edges in one list. Why would you? You want, for every surface, you want to place those edges that belong to that surface into their own list. That makes sense, right? So now, after I get the brep edges, and I extract the naked edges, which is the perimeter, it gives me 225 branches. Let's look at the data tree. It's going to be gnarly. Like that, right? So for this is like every surface. And inside of every branch, there is 4 elements. Edge 1, edge 2, edge 3, edge 4, right? Those are the 4 elements. If I look at it in the with the panel curve, well, it doesn't matter what kind of curve, but curve, right? 4 curves in each one of these. Again, with the addresses though, really messy. Right click, simplify. Ah, nice. Right click, even here it's nicer. I will keep talking about it until it's not a thing anymore, or until I understand the use for it. Okay, so with these curves here, now I am able to actually join them into like a closed loop, right? So if I join curves, bam, they are now joined into a single closed curve. Easy. So now what I end up having is this same 225 branches because of the 225, I'm gonna get there, 225 surfaces, but now it's only 1 element in each branch because 4 elements were joined into 1, right? So now it's closed curve. Okay, we move on. The address, right click, simplify. No, go away. Okay, 225, right? So now after this, I'm going to make on purpose, I'm going to make an error so that you can see. And before I do so, I will reduce this to like 5 instead of 15 by 15. So it's only 25 branches because if I make it, if I were to make it with 15 by 15, it would just crash my computer, the next thing that I'm gonna do. But here I'm going to say, well, actually, now we're done, right? We have 1 element in each branch. We can just right click and flatten this. We can just push everything into 1 list. We don't need to really think about it in the future, right? Because now all I have here are separate curves, right? Like all of these, let me hide this. Actually, the ISO trim is messing us up. So these, if I were to actually even bake this in, these are like separate perimeters here that are just in 1 list, right? Just chilling in 1 list after we flatten this. Simplify, by the way, does nothing at this point if you're flattening it. Okay, we have them in 1 list, but now remember my beautiful drawing? I want to offset it. Sure, that's gonna work. I can offset. I think we need to use offset loose though. Offset curve loose. Curve to offset. Those are going to be our curves. It's going to be a little bit yucky. Distance to offset by. That's going to be negative. A negative distance of, I don't know, like 10. I have no idea how big this thing is. You also, so just guess. You can guess do an informed guess by checking the grid, by the way. That's 1 unit, right? So 10 is going to be way too much. Not that bad. Not that bad, honestly. But you can see that the offset in this case is really fucky-wucky. So I might not use the offset. I might use something else. One last ditched effort is... Nah. It's too messy. This is a beginner level course. I'm not going to start solving this. Instead, we just scale. It's not going to be as nice, but at least it's gonna work with less amount of nodes. Okay, so geometry. The curves are the geometry that we scale. The center point is curve center, or sorry, polygon center. Polygon center. This bad boy right here. Ooh, cannot convert input curve to polyline. That's fine. If it can't do that, that's okay. We can just simply, okay, there are 2 ways of how we can do it. We can either get an area of these surfaces, because these surfaces are basically the same thing. So if we just extract the centroid, those are the center points. So that's one way. Another way is for these curves that we have here, we could technically explode them, get the vertices of the exploded curves, and then average them out. Average out the vertices, and we would get, oh, ew, what the hell? 1 second. Recursive explosion. Why are there 5 vertices? 1 second. I think the start and end points are duplicated, so we remove duplicate points and then we use the average. Yeah, now the arithmetic mean is much closer to the actual centroid, but as you can see, it treats it as if this geometry is flat while it indeed isn't. So this method worse. This method from isotrim, from surface, area, centroid, much better. We just get that. That becomes our center point for scaling, and you can see how clean the scale is. I love it. So for the factor, somewhere between 0 and 0.1 dot dot 0.5 dot dot 0.999 or 0.99, that's fine. Enter. Connect that to the factor, increase it to something that looks nice, something like that. Great. We have ourselves a little bit of a chain kind of situation. And you can see the scaling is crappy because since, you know, for instance, this element is stretched, it's of course going to scale more in the horizontal than in the vertical. Offset tends to keep it clean, but that's too much work. Okay, so after scaling, we now have our geometry here, which is also all in one list. And now we have a little bit of a problem. How the hell do I loft between these curves and these curves? If I just merge these two things like so, that ain't gonna work, right? That's just gonna be a long ass list. Oh, actually not even, oh my God, not even a long ass list because the addresses are not matching up anymore. So I need to simplify this for this to work. It doesn't. Flatten this. Okay, then it does. Anyway, the point is, merge will not work because what we want for this to work is we want pairs of curves, right? We want the outer one and the inner one to be in their own list, and then they get lofted. And then it moves on to the next list of 2 curves, they get lofted, you know, for every panel. In this case, this doesn't work. So the reason why this doesn't work is because we're operating with everything as if it's a single list, right? We can't in this case. Everything needs to be separated out. And that's where I made the mistake here. We actually shouldn't do this, but actually I can show you. If I unflatten this, what the hell? What's going on? And that is where most of the Grasshopper crashes happen. Hope you're with me so far. Let me get some water and I'll explain. Delicious. So notice how this is a dashed line. By the way, the amount of curves that are generated is literally a square root or the squared number of amount of segments that we have or amount of surfaces that we have. So it's 25 times 25, 625, right? How do I know? I know this because that's how data tree mismatch behaves. Data with 25 branches, 25 elements in each branch, 25 times 25, right? Why? Well, there's a dashed line coming in here, meaning that the curves that come in are coming in as separate, like every curve for each branch, like that. Closed curve, closed curve, closed curve, you know, so every segment is its own little branch. But the center points that come in They come in as one list, right? So what happens? Scale node takes the first curve and it goes like, okay, I need to scale this first curve by 94%, by 68%, by whatever amount of percent, right? I need to scale it down by 92%. Okay, what's the center point? Show me the center point. And what it gets, instead of getting one center point, it gets 25 of them, a whole list of them. And it goes, no problem. Okay, so this curve, the closed curve at 0 index, the first curve, gets scaled around this point. Then it gets scaled around this point, then around this point, around this point, and it gets scaled 25 times. And then it's like, yay, I'm done. Okay, next one. Okay, I have my second closed curve, right, from here. I need to scale it again by 92%. And again, I scale it along 25 different points. And it just does so for 25 curves. It scales them by 25 points. Thus, 25 times 25. Or by the end of it, you get data with 25 branches, each branch for every curve that you have here. It keeps the data tree structure. But then the problem is that, it gives you 25 curves in each branch because of 25 center points. Fix how? How fix? Problem, fix how? Fix by right-clicking the centroid here and forcing it also into a data tree, its own data tree, right? And notice how, even though it's all fucky-wucky and all messed up with the addresses, here it's like cleaned up, 0, 1, 2, 3, 4. Here it's 0, 0, 0, 0, 0, 1, 0, 0, 2. Somewhere under the hood, scale actually cleans it up for you and actually, manages to match these guys up because clearly it works, right? And clearly then you can see it's 25 branches, one element in each branch, everything works out. So even though it's doing a crappy job here, it's actually cleaning it up and then pushing a messed up address here, again, with a bunch of zeros. So I will simplify it here so that it does not, we're helping the scale by simplifying the data. Okay, so now these match up and it goes, okay, for the first curve, I will use the first, or, I will use this element. For the second curve, I'll use this element, third curve, this element, fourth curve, this element, and so on, right? So that's how it operates. That's how it works. I should probably keep at least one of these, or I'll keep actually both of these for you, but I will of course make them smaller so that they fit a little bit better. Something like that, maybe. Okay. So that's for now kind of working. And if I were to check the merge now, right here, it says data with 25 branches, 2 items in each branch, because we take the original curve, the outside perimeter, we take the scaled curve, the inside of the perimeter, and we merge them into one list. So basically what it does, it takes it takes item index 1 from here. It takes item index 1 from here, from the scale. It pushes them into one list. Item index, sorry, apologies. Again, it takes item index 0 from here, item index 0 from here, pushes them into one list. Item index 1 pushes them into the second list, and so on, right? So you end up with 25 lists of 2 elements in each list with closed curve, right? The big boy, the small boy. Big boy, small boy, big boy, small boy. Time to loft. Easy. Just works. Just like that. Right? Easy peasy. Then it's time to... These lofts need to be joined up into one brep, right? Into one boundary representation. Currently they are still in separate branches. And now if I use brep join, they will not join, right? Because they're in separate branches. The breps that I get will still be open breps. No bueno. So what I do is I use, I right click on the loft and I choose flatten. And then breps are indeed, the lofts come in as one list, like so, and they are joined into one brep here, one polysurface. And then you can offset the polysurface or do whatever you want with it. I wonder if we can do offset surface. That's just offset surface. I wonder if that's gonna work. Nope. Should I show you how to offset a brep? It's kind of gnarly. Well, we have plenty of time, right? I can show you. Okay, this is going to be the last thing about the data trees. Of course, there are multiple things that you can do with a data tree, and I will be kind of talking about some of them, but I need you to understand the logic, the logic behind them, right? And how they work. Once you know the logic, then you can start operating with them, right? So that's the first thing. Do we? No, we shouldn't, because if I give it thickness, then the time is ticking and it's not a part of data trees. Apologies. We move on. Okay, so with this done, I can increase, by the way, the number slider back to like 10 or so. And we get a pretty nice grid structure. And also, if you want to, you can take the naked edges, you can take the scaled surface, the scaled inner edges. You can deconstruct them or explode them. Explode the scaled geometry into segments. So you have these separate segments here, and you can use edge surface. It needs them to be separated, but that's fine. If I look at them with a panel, you'll see that the segments are actually, again, back to separate elements, and there are literally always 4 curves, for every polyline became 4 curves. So I can use list item to easily just get, okay, give me curve 1, curve 2, curve 3, curve 4, bam, 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 bam. And then I get my my inner surface that I can custom preview with a swatch. It comes in as data tree. We don't really care, but and that's gonna be white. Sure, why not? And then this brep custom preview with a swatch. And it's going to be not white, but rather some beautiful blue color. Oh, very beautiful. Beautiful blue color. Hide all of those. Congratulations, you have done some sort of a weird fetish looking thing. Okay, so that's done. Right click, internalized already. That's great, everything works. Let's move on to more conceptual things. Because just creating a script that would showcase that with geometry would be way too much and would take up too much time. So here under, let's see, clean tree, we will be using that, but not yet. I will be showcasing that in one of the further chapters. For now, we skip over it. Flatten tree showed it. Graft tree, literally the same thing as right-clicking and choosing to graft. Prune tree, remove small branches. So if you have a list, can I just borrow that? I'm just borrowing our cat, dog, mouse list here. If we have this tree, bam, which is not grafted, and we look at it, right? Okay, I can say with prune tree tool, I can say, Actually, the maximum size of a branch that I want to allow is 4 elements in size. It just got rid of the, you can see now there's no list with item, no list with address 0. If I say that actually, nah, the minimum is 4, then it gets rid of the number list here, right? It only keeps the animals and the alphabet. So that's what prune tree does. Moving on. I have a hunch that I will need this entwine, so I'm taking it, Control C. We'll move to here. Hello? Oh, we move here. We continue from here. Ooh, trim tree, very useful. Okay, this bad boy here. Right click, graft this. So now remember, when this is grafted, how it looks like, param viewer. All of this, separate branches, right? Problem. Well, not a problem, but like very complex data tree, 3 main branches because 3 main lists, and then every item in the list becomes a smaller branch. So it has like a depth at which it's constructed, right? It's constructed with a depth. We can trim the tree, and just imagine this. You need to do it for every element. You know, you need them to be grafted because you're doing something with offsetting, lofting, and so on, and you need all of them to be kind of separate and so on. And at the end of it all, what you want is to end up back with 3 lists, right? So you can't just ungraft this, you know, not graft it. You want to end up with 3 lists. So what are your options? Well, you could say, actually, let me do one thing. So if I just say text, scribble, a bunch of stuff happens in between, and you can't not have it grafted. Beautiful. I should be a university teacher with these kind of explanations. Okay, so this, right? This happens. And you have this text, right? That you know, a mess of a data tree. And what you want to end up with is 3 branches. Trim tree is your friend. If I just read what it does, reduce the complexity of a tree by merging the outermost branches. It's going to take all of these points here and it's going to merge them back to the main branch. Going to take all of these points, merge them back. All of these points, merge them back. So it's like an ungraft type of a thing, but only in one step. So you're back to a data tree that has 3 branches. And that is like cat, dog, mouse thing. Cat, dog, mouse, horse, chicken thing, right? So back to 3 lists. Trim tree, very useful because you can't flatten, right? If you just flatten it, well, first of all, it complains, but then if you flatten the output here, it just gives you a single list. And there is no way of how you can go back to those 3 lists. Flatten is like all or nothing type of a thing, while trim tree just goes back 1 step. Or if you give it a depth of 2, it goes back 2 steps and so on. I assume you get the idea of the depth, but trim tree is quite useful. Right now it's complaining because it says, yo, there's 1 list, what do you want me to trim? But if I unflatten this, then it's, yeah, it does its job. So that's trim tree, very, very useful tool. Then what we can do is, well, there's unflatten. But that unflatten is very annoying because you need a guide and we don't deal with those. That's too much. Entwine, I already showed you. Ooh, flip matrix is kind of cool. Can Can I show you it in geometry wise? Yes, I can. Ooh, finally, an example with geometry. One curve, second curve. A little bit annoying, but sure. Is that the ortho? Yeah, that's the ortho snap. Okay. Curve, component, right click, set multiple, yoink, get those both in there. Divide curve. Guess what it does? You know, you have two curves and it needs to make points on them. Clearly, it makes a data tree. Param viewer, data tree, 2 branches, 11 points in each branch. Easy, each branch for each curve. At this point, you're probably already anticipating, right? What's going to happen? I want to connect index 1 or index 0 with index 0. Index 1 with index 1. I want to connect these points together. What do I do? How? Think. I will simplify it just for you. It's not for me, it's for you. Simplify. I want this point to connect with this point. I can even show you even easier. List item. Index 0. Polyline. Hello? Wait. Oh yeah, index 0 and then flatten and then polyline. Oh, come on. Annoying. Flip. There we go. When you flip it, the points that are generated also flip their like the start and the end of the curve flips. So now this is 0.0 and this is 0.0 rather than it being here. Anyway, I want this line, but also I want it to be everywhere. So what do? Do I just keep, you know, index 1 now? And so on? No, of course not. I want some logic in there. And for that, I'm going to use a tool that's called Flip Matrix. Flip Matrix, located right here. Flip Matrix. Actually, will be almost the last tool. I might show you the path mapper as the last tool, but we're getting there. So Flip Matrix. Okay. When you have this kind of a data tree with 2 branches and 11 items in each branch, what it's going to do is going to take item 0, and it's going to put it in one branch. It's going to take item 1, and it's going to put it in the second branch. Item 3, or item 2, third branch. Item 3, fourth branch. Item 4, fifth branch, and so on, right? So it's going to flip the logic. And instead of data with 2 branches and 11 items in each branch, it's going to become 11 branches with 2 items in each branch. So it matches up the indices, right? So Flip Matrix, if I use it like so, now it becomes 11 branches with 2 items in each branch, meaning 2 points. And I can just simply use polyline on it. And it just works. Like that. So that's what Flip Matrix does. It takes the indices and it just flips them over. Okay. Internalize data. We're so close. Path mapper. Okay. So under here, path mapper is basically Flip Matrix only works when you have a simple data tree. When there's only list of lists, right? Because it needs to, you know, where the branches become the indices and where the indices become the branches. But the moment you have a more complex data structure, such as this, I'm getting that as, again, the grafted cat, dog, mouse list thing, example. This bad boy right here. Everything's in their own little list. And I can also show you, one second, thinking real hard right now. Param viewer. There we go. That logic. This Flip Matrix will not work here. Well, technically it could, I think, but no. It's going to, all paths may only differ at a single focus or locus, right? So here it goes like, no. There's too many paths. I don't know what to flip. This is where this bad boy comes in. This is welcome to the advanced world. I want to see a bad swear word, but I won't. If you double click this, basically you can define any kind of an address, and you can see how that address should be changed, right? To in what way. So for example, I could connect this data tree that we have here, right click, and I can say create flatten mapping, right? And then what it does, it says, okay, that means the address of A and B becomes just 0. Whatever address there is, just push it in 0. And that would actually work with the syntax. I think everything would just be pushed. Yeah, everything just gets pushed into one line, right? But that's not what we want. What I want is, also I need to remember I think, index in brackets I think that's the syntax. So we have the big branch address, the small branch address, and the index, right? If I check it here, that's A, this number is A, this number is B, and this is 1. If this had more numbers, then it would be C, D, E, and so on. And what I can do now is I can say, actually, AB1 should be redone where it's I, that weird thing, dot comma thing, I keep forgetting, I, B, and then A is actually the index, right? So I reshuffle it according to how I want the data to flow. Hit OK. Now I have, this is going to be trippy, a data tree that says cat A1. Why does it say so? Well, it takes cat, it takes A, and it takes 1, and it puts it in one in the first branch. Then it takes dog B2, puts it in the second branch, and that's because I'm reading the index as my main branching thing, and then everything else just follows along. Then it takes I would assume mouse C3 goes into the third branch. Then we have on the fourth branch we have horse D, and there's nothing here, right? So it can't do the third item. And then the fourth branch is just chicken because it doesn't have anything here. It's tricky, isn't it? So this one is a little bit more advanced. I strongly suggest that you first learn about the flip matrix and how to use that, how to use graft, flatten, and simplify, and so on. And once you get accustomed to it, then start exploring there. Specifically, when you will see that flip matrix is not working, and you actually have a longer address and you only need to flip over the end part of the data tree, right? The furthermost branches of the data tree, then the syntax of the flippening would be ABI becomes AIB, right? That would be the syntax. So everything kind of stays, the start of it stays exactly the same. And I can show you here, honestly, like that. Wait, why does it do that? A stayed the same, right? So the main branches stayed the same, and then indices became, so it took 0, 0, 0, then it took, okay, yeah. So it literally acts as a trim tree right now. Okay, never mind. That's a shittier example. I'm gonna keep the original one, but hopefully at least some of you get the point. This is like non-mandatory to learn right now. I will even change the color of it to something like gray. But in the future, you should definitely kind of put focus on this path mapper tool. Okay, What else? That's kind of it, honestly. That's it with the data trees. Oh, explode tree. I guess that's a useful one. So the fun one is that you can just use bang, type in bang, and it just suggests explode tree. So of course, for any data tree, you can just use explode, and then it's going to give you, the first branch, which is in this case a cat, second branch, which is a dog, and so on. If you explode the adjusted data tree right here, the first branch is cat A1, then second branch dog B2, third branch, fourth branch, fifth branch. And then once you take the 5 branches, then it stops complaining, right? Because suddenly you're exploding the whole data tree. Quite a useful thing. I'll kind of keep it for you to check. Like something like this. Ooh, we're done. We're done with the data tree structures. 1 hour, 17 minutes. After some cuts, it's going to be closer to an hour as expected, an hour. That's fine. Let's move on. Move on to the next chapter. Okay, let's do some physics simulation. It's going to be better. It's going to be faster and more fun than data trees. There is a built-in plugin add-on, I guess, to Grasshopper that can simulate physics. Made by Daniel Piker. It's a pretty powerful tool. So if we go here and we just find the Kangaroo 2 tab, all of that deals with physics simulation. And most of the stuff that you do here in Kangaroo is done with meshes. So we will be working with meshes. I will show you just one single example just to get you started. And also I'll show you where you can download example files for those of you who are interested in this kind of a workflow, this kind of a stuff. So I guess for architects, tensile, I guess like tens and fabrics are most useful. So we'll start with that, or we will do that. So first of all, we need to define the shape of our fabric. And the way I like to work with it so that my geometry is quite clean is by constructing patchwork from which I will be building up my tent. So I go to the top view, and I will just do a quick one. I will first draw a skeleton for basically the distribution of my shape. Yeah, sure, something like that. Distribution of my shape in the plan view. Why not? This is going to be a very simple one as well. Actually, let's make it a little bit more fun. Let's do something like a herringbone type of a thing. So that's my like a skeleton. I'll lock it, right? Then from this skeleton, I will draw 1, 2, 3, 4, 5, 6 patches. More 7, 8, 9, 10 patches. And what I mean by patches is these rectangular shapes that I use to thicken up the skeleton. And I make sure that my patches produce a grid. Something like that. See how they all match up corner to corner? They must match up corner to corner for them to work. Well, shit. Okay. Here we needed to do... Give me a second. Yeah, something like that. That's gonna work. And then here, when I'm talking, I just stop thinking. Okay, something like that. And then here it does this, and then it can do that. And then finally does this. Okay. Should have made a simpler shape. Anyway, we have this these patches that build up a form, and I'm going to get them in Grasshopper as curves. Right click, set multiple curves, and I'll make them into surfaces. Boundary surface. Okay, as I mentioned, Kangaroo deals with meshes, not surfaces, so we need to do a little bit of meshing here. And what I'll use on this is mesh surface tool, mesh surface. Ew, boundary surfaces suck. That doesn't work at all. Okay, we just use surface instead of boundary surface and we just pray. That works much better. Okay, never mind. Don't use boundary surface, just use surface. Component, just a regular one, the black hexagon one, and it converts a curve into a surface much better. At least a rectangular curve. Then for U count and V count, I will use the same number. So for now, I'm just going to use like 8 or something like that. 8 and 8 here. And that should be good enough. So that's our mesh. Actually, it's not one mesh, it's 10 meshes. We need them to be joined up into one mesh. A way of how I can do it is by using the mesh join tool. But the problem with it is that it remembers the seams. It remembers where the mesh is joined up, and I don't want that. I want them to be eliminated. And technically, I could do align vertices command that eliminates all of the duplicate points and unify. You don't need to do this, by the way. Just look, unify mesh normals or unify mesh tool that makes sure that the mesh is, the whole mesh is looking in the correct direction, and then it's gonna work. But the tool that does all of this is called combine and clean. And that is indeed a Kangaroo 2 tool that's available under mesh, combine and clean. I connect it here. Ew. Okay, combine and clean does the trick, but we still need to use unify mesh, unfortunately, for it to actually work. Because some of these rectangles were drawn clockwise, others were drawn counterclockwise, so it didn't like it. Anyway, combine and clean and unify mesh. Now we have a result of a clean mesh that is ready to be simulated. I want this to be a tensile structure, you know, like Antoni Gaudi's hanging chain models or Fry Otto's experiments with tents, and well, he experimented with soap bubbles mostly, but it's sure in that theme, right? So I want this to be affected by gravity, at first to dip down or up, doesn't matter. And I want it to be locked, you know, in certain places so that it doesn't fly away. Okay. Kangaroo is a simulation-based engine, simulation engine that deals with physics. And under main here, you have the main star of the show called solver. This node right here, and Kangaroo, by the way, is one of the tools with which I work backwards. So I first put down the solver, and then I service, or I input enough stuff into it so that it works. Let's look at the stuff that we should input into it. First one being, I'll go, as I said, backwards, so bottom up. First one being, is it on? That is going to be a toggle, Boolean toggle. If it's false, it's off. If it's true, it's on. For now, I'm going to keep it as false. Tolerance and threshold, we don't touch those. We touch those once we understand Grasshopper much better. For now, we anticipated that the creator of Kangaroo knew what the default values should be. Reset, that's a button. Every time a simulation finishes and you want it to run again, you press the reset button. It starts again. Goal objects. What kind of goals should be reached during the simulation? All of the goals are available here in Kangaroo. Goals for points, or sorry, points are here. Where are they? Okay, goals for meshes, goals for lines, goals for collision, goals to keep, for instance, all of the points concentrical or co-circular, goals for angles, and goals for 6 degrees of freedom elements. That's much more structural engineering type kind of thing, rigid body sims. Anyway, you will have multiple goals, such as gravity. such as pinning of points down so that they don't move and so on. And the goals should come in here as either a single list or a single data tree. I prefer if they come in here as a single data tree. I will be using entwine to get them in there. Now let's construct the goals that we need. Goal number 1 that will connect to branch 0 is going to be show me the geometry after the simulation has finished and during the simulation. Show goal is located right here. Under main, there's the show option. That connects to branch 0. This is immediately going to turn red because, I don't have anything to show you. You haven't connected anything to this. The geometry that is going to be shown is going to be the mesh. We connect it. Now the solver is happy again. It goes, okay, here we go, mesh. If I run the I can run the simulation, by the way, now. If I turn this on and hit reset, it goes, sure, easy goal. Here's the geometry. I have fulfilled my goal. The simulation has converged. If you reset, sure, here's the geometry. I'm showing it to you. Goal fulfilled. Easy. That's goal number 1. Goal number 2, apply gravity to the geometry. And for that, I will hide the original mesh just so that it's not, in the way. And now we're only seeing the simulated mesh, right? Apply gravity. Okay. Under goals mesh, there should be vertex loads. This bad boy right here. Apply equal vertical is important, loads to all vertices or points of the mesh. Great. Asks me for 2 things, mesh and how strong it should be. You can see that the strength is set to be minus 0.1, meaning it's going to push downwards. If it's positive, it's going to push upwards. So for now, I give it a mesh. That's the same mesh. I connect that to my first branch. And it just goes, okay, I'm running. If I reset, it goes, yeah, I'm doing it. So what the hell is happening? Well, if I reset it again, you can see that at the first frame, the geometry is there and then it's not. Well, that's because the geometry is falling. And it's falling fast. Why is it falling? Well, you're applying load to it, force to it to fall. There's nothing catching it, so it just keeps falling. So we need to catch it. We need to somehow lock it in place. That's where the third goal comes in. Make sure to stop the solver, by the way. It's going to crash eventually if you just let it fall to infinity. Third goal. Third goal is anchoring. You want to nail down the structure so that, or the mesh, so that it gets anchored. You want to anchor points of the mesh. So I'm going to go for goals, mesh. No, that's not going to be mesh, sorry. Goals. Goals point, yeah, anchors. These bad boys right here. You want anchor goal. Asks you to give it points for anchoring. Oh, I need to somehow select the points here. How do I do that? Well, by drawing more on this. So first of all, I'll internalize data for these curves so that I can just delete them and they're not in the way. I'm also going to unlock and delete the spine. I don't need that as well. But what I do need is I need to somehow grab these points and lock them, grab these points and lock them. I want a way of how I can select the points that I lock. Easiest way to do it, considering that our patches are flat on the ground, is by drawing a closed curve around the points that I want to lock in place. I'll draw it 3 more times so that you kind of understand what I'm doing. These are regions that I'm drawing that will be used to check if a point is inside of a curve or a region, or if it's outside of the region. And the ones that are inside of the region will be selected. That's the script. That's the idea for the script, right? So I get these 4 regions in here as curves. Curve, right click, set multiple curves, internalize it. Oh, actually, for now, let's just have it set. Then I need to somehow get all of the points of this mesh, deconstruct mesh. Deconstruct mesh, get the points in here. We get the vertices, right? Also, another way is like naked vertices component. This one right here, naked vertices. That also gives you the naked points, and it's also part of Kangaroo 2, naked points, right? So you could use this, you could use deconstruct mesh, whichever you want. In this case, maybe for the sake of teaching you as many tools as possible about Grasshopper, I'm going to use naked vertices. We have our naked points right here. We have our curves right here. I will ask in curve, point in curve. Actually, is there like in curves multiple? Yes, point in curves, in either one of the curves, right? Multiple, point in curves. Naked points, those are the points. So only the perimeter points are naked in this case. Curves, those are the curves. Gives me a relationship. Either inside, outside, or coincident. So what I want to ask with the relationship, by the way, outside is 0, right? 1 is coincident, meaning on the curve. 2 is inside. So I'll ask it, is the relationship equal to number 0? And that is going to give me a true or false statements for equality. And then I can just simply call pattern, use call pattern for the naked points with the equality. And then I get everything except what I need. So it's going to be inequality. There we go. Flipped logic, right? And I get my list. And those are going to be our anchors. You know, let me show you again. The highlighted ones are now the curves inside of the curves that we get. Those are our anchors. And we connect our anchors as our third goal in this script. Like so. Reset, run. Well, they sure anchor. There's a problem though. It's a wavy problem. Let me stop this. The problem is called infinitely stretchy material. That will be our 4th goal. And actually our last goal. We need to somehow introduce stiffness to this material, or else it just gets affected by gravity and just stretches forever, you know, being held by these points. So I zoom into the entwine, I expand it. I have one more input. And now I will use goals mesh edge lengths tool. So the edges, the lines of the mesh will try to keep a certain length. I connect the mesh to the input here. The length factor will be set to 1. So basically the mesh edges will try to keep their original length, and the strength of it will be also set to 1. You technically can balance the strengths of different inputs, but in this case whatever. And actually just for the sake of wiring, I will disconnect the anchors. I'll reconnect them to input 0.3 and edge lengths to 0.2. It doesn't matter, just visually the lines don't cross, so it's nicer. I reset, run this, voila, hanging chain model. That's done. Let's hide a bunch of stuff so that it's not in the way. Now for this to work as a dome, we actually want the vertex loads to be up. So I'm going to give it a strength of 0.2. So that's a positive value. And now it goes up. And you can even see the curvature and the way it behaves. You know, it's all behaving, well, to a certain degree in a natural way. I can't say it's actually very accurate simply because the way we meshed it is not that accurate, but it's getting there. It's close to a proper vault, right? Let's stop the simulation and let's increase the U and V count from 8 to something closer to, oh, by the way, when you change it, it's going to freak out. Don't worry about it. Edit maximum Let's go for maximum is 15, and actually let's run the slider to something like 12. Reset, run. You can see that the vault increases much higher, like grows much higher, and that is simply due to the fact that it has more lines that can stretch. So the vertex loads, I would suggest that to decrease in their power to something like 0.1 to kind of counterbalance the increase in resolution. So the output now, to only get the mesh, because the output now is kind of dirty, it has a lot of geometries. You can see it comes out as separate, a data tree with 4 separate branches. What a coincidence, we input a data tree with 4 separate branches. Question, which branch is the one that we need? Well, let me give you a hint. It's the first one, the show branch. So I will just bang, explode the tree. 1, 2, 3, 4 branches, and the first item in our first branch is going to be our mesh that we care about. Hide everything else except the mesh. Actually, custom preview the mesh. Might look nice. Keep it pink. Looks great. Look at it, beautiful. What a beautiful little mesh we've got there. So this is, if it was upside down, it was tension only based structure, a structure that is purely tension based. Since it's upside down, it's compression only based structure. So suddenly Philip blocks, block research group, all of that stuff that you see, that is, you know, walls that don't need any mortar to hold themselves up. This is one of them. You can construct this with correct tiling, of course, and tessellation, I mean, of course, but you can construct it without any glue, without any mortar, just by stacking bricks together, because this is compression only based structure. Very nice. So that's Kangaroo. That's simulations in Kangaroo. Clearly, you can do a lot of things. Actually, this is going to be the first time that I show you, oh yeah, internalize. Bam. This is going to be the first time that I show you an actual website. If you just Google Kangaroo example files, here under GitHub, Daniel Piker, Kangaroo examples, you will find, and they're 7 years old, but that's fine. You'll find all of the different examples for different definitions in Kangaroo. Some of them will require you to download plugins, but the next chapter is going to be about plugins, so don't worry. But for example, tensile structures, right? That's what we were learning right now. Or actually tensile structures, I guess, is not that interesting anymore. Let's go for folding. Folding, origami, origami 2. I assume 2 is better than 1. Click on that. And here on the right hand side, you'll find download raw file. Click on that. That downloads origami 2, the Grasshopper file. Then in the folder, come on, give me. In the folder, your downloads folder, you'll find it. And what you can do is you can just drag and drop it in. Bam. And this gives you a full kind of example of the origami structure. Where is it? Who knows? No one knows. Probably need to reset. Yes. Click the reset button. The solver, the explanation, or lack thereof, I guess, but the script is there. And then if I run the folding simulation, it folds a beautiful flappy origami thing, right? So there's plenty of these examples. If you want to learn further, go through the examples, try to understand, you know, the planarize, the show, well, the famous show, deconstruct mesh, get the vertices, make them anchors, or in this case, plastic anchors, and so on, right? I'm not going to go in depth here. But that's how you work with example files for Kangaroo 2. Okay? Okay. Next chapter, plugins. Let's go. Okay, so now we are done with the base Grasshopper course, or the base tutorials or training for, you know, the vanilla Grasshopper. One thing that I mentioned at the start of this course was that Grasshopper actually is, the strength of it is all of the add-ons that are created by the community, by the developers and so on, that can be added into Grasshopper. And you can see you know that I'll remind you that here I have more tabs than what you see on your screens, right? I have the human, honeybee, dragonfly, V-Ray, Anemone, Horster, and so on, sandbox. All of these tabs, they add in additional functionality. For example, Ladybug adds in the possibility of calculating solar exposure, right, for your models. They add additional functionality through additional nodes. So once you get a hang of Grasshopper in itself, then you start looking into, okay, what kind of extended functionality can we get? And the first thing that you need to know, I guess, is how do you get these add-ons? Where do you find them? How do you install them? Two ways. I'll show you both right now. Way number one, and we will use it to actually install a thing. I guess I can close it for now. Here in the command line, I can type in package manager. And this package manager basically contains all of the more official, I guess, add-ons that you can download directly through Rhino, right? All of these ones. And of course, I will not be going through them because that would be another 10 hours or so of a video. Instead, I will show you one in the package manager that I find to be very important and very, very useful. If you search for Weaverbird, Weaver as in weave, bird as in the floppy thing that sometimes you see in the sky. Weaverbird, select it, and here you just hit install. I already have it installed, so I don't want to do that, but here you hit install. Once it's done, you hit OK, and I think it's going to ask you to restart Rhino as well. It should, at least. So what you should do is you should save your Grasshopper file, save your Rhino file, restart it, and then Weaverbird will be not just installed, but also loaded in. Grasshopper plugins load in during the actual loading of Rhino, right? They load in together with Rhino, so you need to restart Rhino for them to work. So once you have that done, and then you go back to Grasshopper, enter, then what you will see is this WB tab right here, Weaverbird tab, which means that the Grasshopper plugin for Weaverbird has been installed. I will cover this in just a second because this enables you to do a lot of really nice things with meshes. But for now, you know, we're all about installing the plugin, so I'm going to skip over it. It's going to be in the future chapter. So that's installing through the package manager. Very straightforward. A little bit trickier thing, but still, in my opinion, once you get the sense of it, it's quite easy, is going to food4rhino.com, www.food4rhino.com. Let me do this for you. Why do I have Rhino 7 not open? Close that. So it does a weird thing. Oh, come on. No. There we go. I'll put it here. As a note for you so that you don't forget. Food4rhino.com. That's where the add-ons live. I think including Weaverbird as well, but it's a little bit trickier to install. So if you can get it through the package manager, you get it through the package manager. If you can't, you go to food4rhino.com and you search for what you need. So for example, actually let's install all of the plugins that I will be showing you. And we start with a plugin called Anemone. Anemone. Hit search. Oh, apologies. I forgot. You actually need to create an account with them. Very simple. Email, password, probably sends you a confirmation email. Accept that. You've got yourself an account. Log in. You're good to go. Food4Rhino does not spam you, does not send you any marketing emails. So it's fine to use whatever email you have. Anyway, once you have logged in, and then you search for Anemone, you can just find it here, Anemone, click on it, and this is like a website, or not, a page for this particular plugin. It explains how it works, it explains, if you click on more, you know, what kind of components it has, which components were released when, and blah blah blah. If you scroll down, then here also you can see all of the complaints, you know, in the comments, because people only write comments when they have something to complain about, or if they have a question, to be honest. But here, under downloads, you can find a bunch of different versions for Anemone. So rule of thumb for any plugin that you download is bigger version number equals better plugin. So here you can see that at the top we have the oldest version. Oops. At the top we have the oldest version. We have newer, well, older, newer, and the newest, 0.4, right? That's the one that we download, Anemone 0.4. Hit the download. Bam. You just get this GHA file, right? In this case, it's a single file. That's fine. That's the, really doesn't matter if it's 1 or 50 files, but you get this GHA file. GHA is Grasshopper assembly. It's basically a bunch of nodes. If I right click on this file, if you're in Windows, if you're in on a Mac, it doesn't matter, but if you're on Windows, if you right click this file, you go to properties, make sure that under security, this file came from another computer and might be blocked. To help protect this computer, you unblock it. You trust this file, or else it will not work properly in Grasshopper. Hit apply, hit OK. You have your Anemone plugin downloaded. For now, just keep it in the downloads folder. That's fine, right? Let's get some more. Let's get Bowerbird. 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 Search for that. There's only one suggestion. Get that one in here. Oh, this one comes with pictures, so you can even see what it does. Bowerbird plugin is used to create waffle structures for laser cutting. For me, it's such a nice tool. I mean, I use it all the time when I need to prepare something for laser cutting. So that's why I'm going to be showing it to you. Only one version, but you can see there's like a for Rhino 8, for Rhino 7, for Rhino 6. So in this case, we're using Rhino 8. I'll hit click on install it, and this is like different, right? It's not the same as what we saw in the previous one where we had to download it. This is actually install, which, you know, open Rhino 8, sure. Wait for it. There we go. And since it is available to us via the package manager, it, instead of downloading it, it just opens up the package manager for us. So I can select it, hit install. You know the drill. We already did this with Weaverbird. It seems like birds are available via the package manager. So you install it this way, right? You don't need to download it. Then the last one that I'm going to show you is called Cocoon. We go back in here, search, Cocoon. I think it's one C, C-O-C-U-U-N. No, double C, C-O-C-C-U-U-N. Oh, come on. Cocoon. Okay. Google Cocoon Grasshopper. Seriously? One second. It used to be very, very available. Okay. I guess here. I am going to also put this in because it seems like it's a little bit of a trickier way of how to find it. It's not available over Food for Rhino, which is weird. It should be, but even with that's fine. Let me go back in here. Scribble. And just by simply copying this link, you should be able to get Cocoon. Okay. The logic is exactly the same. You scroll, you find the file, you hit download. downloads a zip file for you. Let's look at it. So if a zip file is downloaded, both in Mac and in Rhino, you need to unzip it. If you don't unzip it, it will not work. Right click, extract. Extract here, that's fine. Right? Gives you a folder. Now we can delete the zip file. We don't need it anymore. Gives you a folder. We'll look inside. 1 GHA file and 4 just Grasshopper definitions. If you see the blue files, the blue icons are example files. If you see a green icon, that's the plugin file. Right click on the plugin file. Don't forget, go to properties. Oh, and this one is not blocked, so we're good, right? Sometimes Grasshopper plugins come with DLL files as well. DLL files should also be, like they are also part of the plugin and should be copied together with the plugin. Either way, now I'm going to take this green file and I'm just going to Control X, cut, or Control C, doesn't matter. Control V it into the downloads folder so that I have my Anemone and Cocoon files both, or plugin files both in the same folder. Just easier for me to see what the hell am I doing, right? Which ones am I going to be copying? And now the installation part. You need to take these two guys. You go to your Grasshopper window. You go to File, Special Folders, Components folder. Come on, Special Folders, Components folder, which will open up a special kind of folder in your on your hard disk, which for some reason, hello, I misclicked. Yes, I misclicked. Which in your case is most likely going to be either empty or will only have like a Bowerbird plugin, data here. These are all of the plugins that I use, that I have, or add-ons that I have. And then what you do is you just take your downloaded files, the Anemone 1 GHA, Cocoon GHA, and drag and drop them over to the libraries folder, right? I will not do that because I already, well, actually I could. It just asks me to replace them, right? And I just, instead of replacing, I'll just click skip. But anyway, once you have them in your Grasshopper libraries folder, or in other words, file special for components folder, you restart Grasshopper, restart Rhino, and then they will be here. You will see Weaverbird, you will see Bowerbird, you will see Anemone, and you will see Cocoon, which does not have its own little tab. It's actually under Mesh. There's this Cocoon subtab here. And I think that's honestly it. Don't forget to unblock things. Right-click Properties, Unblock if something doesn't work. You can't unblock multiple files at once. So if you have multiple files, you need to unblock them one by one. You use Package Manager. You use Food for Rhino. And sometimes, in case of Cocoon, you use just a random website, that you found on the internet to download a shady plugin from it. Okay, that's it with installation. Now let's actually look at them. So the first plugin or add-on that I want to start with is Cocoon, because it's itching for me. Remember when we did that kind of a weird field structure? Where was it? Hello, fields, data trees, fields. There we go, fields, remove duplicate lines. This one. When we add this one right here, I really want to make a three-dimensional shape of it so that it can be 3D printed. That's what we're gonna do. So for this to work, I will need to use Cocoon. The way Cocoon works is it takes a selection of points or lines along, I'll get there. Give me a second, I'll get there. It takes a selection of points or lines in a 3D space and it wraps it around with a mesh by creating this kind of almost a field effect around it. It's a wrapping algorithm. So technically with Cocoon, you can have any kind of a messy data as long as it has points, and you can create a three-dimensional object from it. It's much easier to say, to show than to say. So in this case, what we can do is we can create a metaball charge from a group of curves, or rather, let me show you first a simple example. Then we will do the nice one. So a simple example would be point, 2 points, reference them in, right? Easy peasy. In Cocoon, give it a point charge, like that. So we use point charge tool in Cocoon. Give them a radius. Well, I'm looking at the grid, 5, 10, 15, 20, 30, around 30 in radius. And give them a charge strength of 1. I tend to always give it 1. So now we have this point charge component for marching cubes algorithm. Don't worry about the algorithm. Actually, I love the marching cubes algorithm. I have a whole thing on the YouTube channel about it, but whatever. We have our point charge component. Then what we can do is we can click on, or we can use Cocoon, wrap geometry with marching cubes, bam, and we connect the point charge component as our charges, just like this, right? And then what we need to specify is a number between 0 and 1, preferably between 0.2 and 0.9, something like that, for the ISO value. And I will show you what that means. If I create a slider, oops, that is not a slider. If I create a slider and I just use 0.5, oh yeah, and the cell size, we need to define the resolution beforehand. I'm sorry. The cell size, it's basically how accurate is the calculation. So for now, what's the radius? 30. I'll say the cell size is like 1. That should be fine. And then execute, toggle. True. Bam. We get these two meshes, right? Once we set it to true. Seems like the meshes, the resolution of the meshes is a little bit too dense. So I'm going to reduce it to cell size of 2. So larger cell size means the voxel grid is larger and the interpolation of the mesh is less dense. So that's the radius, 30. And the ISO value is 0.5, which means that currently, if I were to look at it, this should be, let's just grab this point, move it to M, enter, 0, enter. Come on. There we go. Oh no, it already shows what it does. No, disconnect. Later, I'll show you later. But with radius of 30 and ISO value of 0.5, it should be around 15. It's really not. Is it? No, it won't be 15. I'm being stupid. No, because the ISO value is actually for the voxels, so it's a little bit different. But either way, if it's 1, it shrinks to 0. If it's 0, it shrinks to infinity, or it grows to infinity. So as I said, it needs to be somewhere between 0.2 and 0.8. 0.5 is a good place to start, and then you can shrink it accordingly. And I already showed you this, but if you move the points together, since they are creating a field effect, you know, they make this kind of nice peanut looking shape. The topology is atrocious, but then for this mesh, you can use quad remesh, for example. And I'm not even going to give it any more settings. And the quad remesh gives you a pretty decent result, you know, as the output. It's pretty heavy though, so keep that in mind. Okay, so that's the most basic way of how we can use it. It's basically for merging of like different geometries into one shape. And you can see you always get an offset of those geometries kind of for free, or even if you don't want to. Internalize data there. Now let's do the same thing for these lines, right? All of these lines. So Cocoon, again, I will use curve charge for this. Or sorry, curve charge actually is the same thing as point charge, right? Except for lines. So I'm not going to use that. I'm going to try using curve group charge. I never used it before, so that first time, let's try. Curve group charge, connect the curves into here. Maybe less, 8,000. Nah, it's going to be fine, right? 8,000, let's go. didn't crash. Give it a radius. The radius should be, I'm gonna give it like a 10 or 11. 11 for the radius. And charge strengths, I will just say everything has an equal charge strength of 1. Like that. We have 8,000 curve charges. Then I run the Cocoon algorithm with this, with the ISO value of 0.5. The cell size, this is important. If I choose too small of a number, it's just going to crash. So for now, I'm going to use a number that is just barely smaller than the radius. So the radius is 11. I'm going to say the cell size is like 10. Okay. Now we save our files and we toggle execute. This is going to be heavy. That and toggle true. And then we pray that this does not crash because it's a lot. So what it's doing, it's basically taking all of these elements. While this is calculating, I can kind of explain it. I have time to explain it. It's taking all of those elements, all of those lines and the points in the lines and so on, and it's basically generating a mesh from it. And it's using a marching cubes algorithm to do so. So basically there are 13 different variations, 13 different ways of, maybe this is better, of how a polygon could be added into any kind of a voxelized space, and is just choosing the correct ones to wrap a geometry around with new polygons. And that's why the topology looks the way it does. You can clearly see the divisions, right? The way it's divided up into X, Y, Z grid. That's because it needs that X, Y, Z grid to actually choose what kind of polygon should be added, right? So going back here, 18 seconds, not too bad. The resolution is horrible, absolutely horrible, but we're getting somewhere, right? We're getting to somewhere. So for now, I'm going to stop the calculation. That was 18 seconds. So if I drop this by half and I drop this by half, that means it's going to be around 2 minutes to calculate. So I'm going to do that, and then we will continue. We will continue from there. So give me a second. Okay, there we go. I have noticed that point charges work much faster than curves for this particular geometry, or for this kind of a set of curves. So instead of using group curve charge or whatever it's called, mesh, cocoon, curve group charge, instead of using that, I just simply use point charge. So the way I do this is I have all of these lines. I divide them up into points, 10 points per each line. I actually divide by distance, would be by length would be better, but in this case, whatever. I get my the count of points is 10, so there's 10 points on each line, and I basically just say, oh, just wrap each point around with a isosphere. And these are the values that I use: radius of 5, ISO value of almost 0.5, a little bit lower, and the cell size of 4, just slightly below the radius. You always want to be, with your cell size, you always want to be smaller than the radius, but not by too much, or else it's gonna get really heavy really fast, right? And the output that I get is, let's see a custom preview. It's this. Don't be scared, by the way. It looks like that. Let's actually bake it out so that I can show you. Other comments, okay. Sometimes it's gonna tell you, by the way, baking is only possible when no other comments are running, and that means that in Rhino you are running some sort of a command, so just hit escape in Rhino, and then baking will indeed work. If I move this here, over here, oh, there's more than one mesh that's being created. That's fine. We can only get the big boy. And from here, I will just go for Arctic view and just look at it. And it's all bumpy or all lumpy and so on. But finally, we're creating some sort of a structure that can be 3D printed. Clearly, there are multiple ways of how to do this. Multi-pipe, clean up the curves more, have more control over it. This is just one of them. And just by itself, Cocoon is not that great. It's not aesthetically pleasing, but once you add in Weaverbird into the mix, the next plugin that I'm going to show you, add-on that I'm going to show you, then it starts becoming real cool, real fast. So let's automate, before we move on to Weaverbird, let's automate getting only the largest mesh from here, right? Because if I were to check right now the list, we're getting multiple meshes and only one has a decent number of faces. Everything else is just kind of garbage, right? So how do we get rid of garbage? Well, we say deconstruct mesh, or actually, is there a faster way? I know. I'll show you that in the Weaverbird plugin because that's going to be quite nice in the Weaverbird plugin. So next chapter. Right, chapter whatever, 25, I don't know. Weaverbird. Weaverbird is used to manipulate meshes and to subdivide them, to extract like material from, not material, like sub objects from them, such as curves, lines, edges, vertices, faces, or polylines around faces. It's used to smoothen the meshes. It's used to offset the meshes to give them thickness. So with Weaverbird, you can do all sorts of stuff. Also, it has this picture frame that I'll show you as well. Very, very powerful plugin, very powerful tool that I use quite a bit, especially for smoothing of things. So here I have my lump of whatever, weird lump of things here. I have my mesh. I want to extract the biggest one. I need to check which one is the biggest one. In Weaverbird, I can go to extract and I can say, well, give me all of the vertices. Weaverbird's vertices component, give me those. Bam. Oh, that's such a big one. Okay. It actually, I'm used to it looking like this. Draw icons, draw full names. I'm used to it looking like this. So when I see it like that, it's just, wow, okay. But either way, I plug that in and it gives me all of the points of them, every mesh, right? And clearly, you know about the data structures. If I look at the param viewer, nope. Param viewer, you know, for every mesh, it creates a separate data branch, right? And it puts the points in that data branch, lists of lists, right? So I want to know which branch is the biggest one. I will use list length tool. List length. Basically, I just get the points and I measure how many of them are in each of the lists, and I get numbers for them, right? I want the big one. I want the big one to get it somehow out of all of these. Right now, the numbers don't see each other, so they can't be compared to each other. So I need to push this into one list, right click, flatten. Now they are in one list. And I can use a tool that I haven't shown you before, but now I am showing it to you, which is called sort, S-O-R-T, sort list. Keys to sort are the numbers. You know, what is it that you want to sort? The numbers. And as I sort the list, now I get the smallest number in the top and the largest number in the bottom. Okay, so what? I need to somehow get the mesh, not the number in this list, because fetching it is quite easy, right? List item -1 index. But how do I now get the meshes from these numbers? Well, see this values A input? Optional list of values to sort synchronously. So if I have a list of meshes and a corresponding list of amount of vertices that they have, if I sort the number of vertices, you know, into the new list from the smallest number to the highest, I can together with it sort the meshes that the vertices came from, right? In tandem. So like that. Meshes going here and they get sorted the same way as how the numbers get sorted. So now I get the biggest mesh at the bottom of the list and the smallest mesh at the top of the list. Kind of yucky to get the bottom mesh from the list. I could use list item index -1, But that, that requires me to write this panel, and I'm lazy. I don't want to. I want the index to be 0. I want the biggest mesh to be in the top of the list, because then fetching it is much nicer. So what do? Well, I right click on values A and I choose reverse. It just reverses the order of the list. Once I reverse it, now the biggest mesh is in the top of the list. I use list item to fetch it, and now I have myself only the biggest mesh with all of the trash removed. Okay, let's actually disconnect the custom preview. It's a little bit in the way. What now? What now? Oh, by the way, this is like, I need to be very pedagogical about this. This is, oops. Shush. This is Cocoon. Bear with me. Cocoon. Add to group. Change that to some Cocoon color. That's gonna be the that's gonna be the Cocoon color, and this is gonna be Weaverbird. Okay. So now, as I have this large mesh, I don't need the curves anymore. As I have this large mesh, I want to do some operations with it. I want it to be a little bit nicer, because right now it's a little bit yucky. First thing that I want to do is I want to get rid of those bumps as much as possible, right? I want it to be less bumpy. The way you do it is by using smooth mesh. Smooth mesh tool. There's this smooth mesh here. Also, Weaverbird has Weaverbird's Laplacian smoothing tool here. Both are kind of similar, so I'm going to show both of them. If I connect my list item to the Laplacian smoothing, like so, and I give it a level of subdivisions, I increase the level of subdivisions to 2. Actually, I shouldn't, right? Give me a second. Smooth naked edges fixed. That's fine. Or smoothed. Thin. The final one-shot thinning with the original mesh. I don't like that. It does not give me a lot of control over how much it's being smoothed. That one as well. Blur mesh. Fine. Weaverbird smoothing is not that great. Let's use smooth mesh. Apologies for jumping around, but let's use smooth mesh. If you do not, if you cannot find where smooth mesh is, then check mesh, utilities, smooth mesh. If you still cannot find it, then it might be a part of let's try food for rhino, mesh edit, pump. Doesn't seem like it's part of mesh edit. Pufferfish? Could it be Pufferfish? Pufferfish, by the way, is another really good plugin. Really nice for mesh manipulation. So you can check that one out as well. But that I will not be giving you a tutorial on that because it's just way too that's way too much, way too long. But sorry for not stopping the recording. I just want to keep going here. Just give me one quick second to take a look. Doesn't seem like it's part of the pufferfish as well. Okay, so I will just boldly assume that smooth mesh is part of the just general Grasshopper tool, right? Help. Nothing there. Okay, so I just connect my mesh into the mesh smooth, right? Already is doing a little bit of the reduction of bumps. I will give it some more iterations for smoothing, so it only goes once now. I will give it like 5 iterations to smooth. You know, the big bump is staying, but everything else is being removed. Maybe a bit more, like 8 iterations. And also I could limit the amount of, I can limit how many, I'm gonna get there, how much the points can move maximum during the smoothing process, but in this case I'm not gonna do that. This seems to be a little bit nicer. Let's look at the smooth version of it. seems to be a bit nicer. The problem that we now have is that this is quite low resolution still. So what you want to do is you want to subdivide it. Remember sub-D geometry, subdivision? You take a cube, and when you subdivide it infinite amount of times, it becomes a sphere. Same thing here. The tool that, or not the tool, the approach that sub-D uses is actually also present in Weaverbird, but Weaverbird retains the mesh, right? So under sub-D here, you see all of the different ways of how you can subdivide geometry. I'll show you only one, which is Catmull-Clark subdivision, the most typical one. Catmull-Clark asks you for three things. I will first show you Catmull-Clark on a separate piece of geometry just so that you can see better. I'll just go to mesh tools, bam, mesh creation. I'll just create a single mesh face, first of all, something like that. Simple mesh face, easy. Mesh, right click, set one mesh, get that one in there. And you can see that now after smoothing, or after subdivision, this single mesh face becomes 4 mesh faces. The way it works, it takes the middle point of the edge, divides it like so, takes middle point of the edge, divides it like so. That's level 1. Level 2 is it takes those 4 polygons that we had and from level 1, and it subdivides them further. Level 3 subdivides it further. We end up with an ellipsoid, right? So this is how it works. And notice how it's always smoothing during the subdivision. I will not get too deep into that particular algorithm, but it's basically averaging out the position of the vertices. If I were to change the look of the mesh to something like this, hide that. Now we can clearly see, let's jump back to level 1. Right? Level 0 is this. This is still a quad, right? And then it divides it up into 4 quads that are very distorted still. Level 2 divides it further into 16 quads. And level 3, 16 times 4, 64 quads, right? And now you get your potato chip looking thing, right? So that's Catmull-Clark subdivision. For a triangle, it works a similar way. Set one mesh. A triangle becomes 3 quads. Let me flip this. A triangle becomes 3 quads. Those 3 quads become 12 quads. Yeah. And those 12 quads become 48 quads, right? Level 4 will not work, or level 5 for that matter will not work. There's a limit, a hard limit to how much you can subdivide. That's imposed just so that you don't destroy your computer, right? So let me actually show selected. Let me get both of them in here. Set multiple meshes, internalize data, delete. Okay, that's Catmull-Clark in a nutshell. So here, we will use the same thing. Because Catmull-Clark, as it subdivides, it gives you more resolution. It also smooths things further. So we will use that. This is going to be a little bit rough with the thinness of things, but most of it should be quite nice. So let's look into here in particular, right? Catmull-Clark subdivision. I'll connect that to my custom preview. For now, I will give it level 0.0.3. So in between 0 and 3, for now level is 0. And for the mesh, I just connect the mesh here, right? So right now, this is not doing anything. Why is this orange? Subdivision level, oh yeah, because this is 0. It's not doing anything because level is 0. If I change this to level 1, every triangle becomes 1, 2, 3 quads, right? 1, 2, 3 quads, 1, 2, 3 quads. So we get this kind of a nice pattern here. And this becomes a little bit smoother, a little bit nicer. Before, after, before, after. Level 2. Even smoother, even nicer. Of course, there's a limit to how much you can smooth it, but for now we will keep it at level 2 because level 3 is too scary. Level 3 will, I think even now it's like above 1 million, yeah, 1.6 million polygons, so level 3 will be times 4, so above 5 million polygons. Anyway, that's our shape right now. Let's look at it in Rhino. Forget about quad remeshing, by the way. This kind of a shape, that's too much. Now you get, there are some spiky boys here and there that didn't manage to connect simply because the radius was too much, too little, sorry, the radius, the point charge radius was too little, so they didn't manage to make a connection, you know, in some cases, but in most cases, it's kind of a nice structure, right? You could do some shenanigans with, let me hide this. You could do some shenanigans with, come on, clipping plane. Mesh reduce and then subdivide it further and so on and play that game. But in this case, we stop because I'm tired. That's mostly why. But you can see that this sections quite nicely, and if it sections nicely, that means it 3D prints nicely. If it 3D prints nicely, that means it can be manufactured and it can be scaled up to a larger thing, right? So when you think about the scale of this, I tend to think about this as a, you know, human is here, right? It's some sort of a weird looking ass pavilion for, I don't know, bats or something. Anyway. This is just an experimentation. Of course, you add the reasoning and you add the logic to the things that you do and the why you do it, either beforehand or on the way as you're working. Read up on the thinking hand method. Very, very useful thing to kind of have in the back of your heads, because there are 2 ways of how to do things. Anyway, but not a theory course. We stop with the theory, just training course. So this is how you mesh things, and this is how the most useful things about the Weaverbird plugin. I want to show you a few more things with Weaverbird. So for now, I'm just going to group this up. That's our Weaverbird. And then I am going to just go through this real quick. Delete that actually. Go back to shaded. Okay, let me just quickly, my favorite, you know, curve, different curve, make this bulge out a bit more, drop it in here, loft, surface, reference in the surface. So any surface, honestly, set multiple or set 1, this is just one surface, internalize and delete it. Okay, we have our surface here. Then I will use mesh surface tool to just divide it up 10 by 10. Easy. We get some sort of a mesh, right? It's a little bit yucky the way it looks, but it is what it is. It should be fine. Then under transform, a few things that are quite useful here are Weaverbird's mesh window and Weaverbird's picture frame. These 2 nodes right here, picture frame, mesh window. So I guess the first thing is the picture frame that we use. We give it a mesh, bam, and it gives us the framing automatically. And you can see that it doesn't act as an offset, it acts actually as a scale. So that's a little bit rough. But if I change the inset type instead of % to parallelogram, so you can see 0, it's set to 0 here, but the parallelogram, it needs to be set to 1. So I can right click, parallelogram. Then it's much more of an offset, right? And then suddenly the distance that I use of 5, let's try 0.25. That's too little, 1.5. There we go. So now it actually acts as an offset. Tends to die much often or break much often. So sometimes you do need to actually use the actual whatchamacallit, percent rather than parallelogram. Then we have our mesh polylines for the mesh window. Bam. Distance, I will use the same distance, 2.8. Inset type, right click as well, parallelogram. These need to match up, right? Then suddenly we have our frames, we have our windows, right? And for our frames, I can thicken them up by either using mesh offset, or I can use here Weaverbird's mesh thicken. Connect the mesh here. Give it a distance of, I don't know. Actually, this is pretty decent, but what is it? 5, okay. So 2.5 as well. You can see that it insets inwards. That's fine. If you give it a negative number, it's going to offset outwards, like that. Then offset type. Or actually, I do want it to offset outwards, so I will negative. I'll use a negative for the distance, like that, and now it goes outwards. Offset type. Distance on diagonals. I think that's the most reasonable one for this particular application. If you don't like the type, you just play around with these three to get the ones that you find what you want. Okay, other two don't even work, so we use this. So now this is thickened up, right? And I can just use this to convert it into a Nurbs polysurface if I want to, or I can work with it as a mesh, continue working with it as a mesh. If I were to bake this out, you will see that the shading is weird, right? It's like there's no sharp edges, and that's because it does not, Rhino does not understand how to shade this. If you want flat shading on this kind of a geometry, what you need to do is you need to use unweld mesh tool, and you need to give it an angle of, I always do degrees, of something less than, I would say like 30 degrees, 30. I think that's gonna do it. Yeah, you can see now it unwelds all of these edges while these stay welded. So if you want these to also not be smooth, then your angle, I guess, should be just 0, right? Or 360, I never remember. Let's see, 0. Yeah, 0 works. Then it just makes everything sharp and welds everything, right? So you get your frame, and then of course you also have your windows, that are currently without any thickness. You would need to add thickness to them for them to work, but that's how you work with the thickening the picture frame of the mesh. So that's a useful one. Internalized already, that's good. Then we have whatever, don't need. Different types of subdivision. Use Catmull-Clark for now. Don't use smoothen, not enough control. Much better to use smooth mesh, gives you more inputs. You can extract the outer boundaries. Face polylines is literally as the same thing as boundary. Where is it? Face boundaries. Face boundaries tool. Let's drag it in here. Face boundaries tool as well as face polylines tool are exactly the same thing. Then we have mesh edges, so it gives you all of the edges in one output rather than separating it into naked and interior edges. Then we have the naked boundary, so you can get only the naked edges here. And vertices component that we already used to check which of the meshes is the biggest one. Gets you all of the points of the mesh. Oh, I guess the dual graph is kind of cool. So the way it works is, do we have anything that would be nice to show? One second. So for example, I'm just going to show you a quick little example. Quick little example here. Come on, gimme. Sphere. Another sphere. Boom, 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 boom. And the third sphere. Like that. Boolean union. Boolean difference. Or actually, this one as well can be Boolean union. Why not? Boolean union. So we have these three spheres. We go get them in here as a brep. And then I will create a mesh that I don't want it to be a quad mesh. I want it to be a triangular mesh because the dual graph shows up better in a mesh that's made out of triangles. So I'm going to use try remesh tool. It's like quad remesh only for triangles. I get a sphere in here or spheres in here and I just remesh them into these this triangular mesh. Easy peasy. I will not even go through any of these settings because this just works. But just so that you kind of understand properly, you can keep the sharpness of the intersections. You can define the length of the desired length of the triangles. So for example, if I say, well, actually the triangle length should be 100, then it's going to give me a much lower resolution. If it's 50, it's better. 20, even better, right? And then iteration, so how many times should it run this to get to the end result? So the more iterations, the more accurate it gets. And I get that triangulation. I do get the dual graph, just like this one, for free with try remesh, but let's just ignore it and let's just say we don't have it. It's just a triangular mesh that we have. Then what I can do for the triangulation, I can just connect the mesh into it, right? And then for every triangle, let me show it to you this way. I think this will be the best. Like that, and then that, and this goes kind of white. Hopefully you can kind of see it. Unfortunately, that they all intersect quite heavily. But notice that for every triangle that we have, a center point is very important. So what it does, I can draw one triangle, two triangles, three triangles, 4, 5 triangles, 6 triangles, 7. Okay, good enough. Right, I have this as an input, and then what dual mesh does, it takes the center points, 1 triangle, 2, 3, 4, 5, 6, 1 here for some reason, and then it connects them, right? And then it will just keep going out there. So we end up with pentagons or hexagons depending on the topology of the mesh, right? That's the purpose of dual graph, is that's what it does. So if you're tired of triangles and quads, you use dual graph, and then you're gonna get hexagons, heptagons, pentagons, and so on. Unfortunately, the dual graph never gives you a mesh. It always gives you curves. So then you need to somehow make geometry out of them. And these curves are indeed polylines, right? They are closed polyline curves, but they're not necessarily flat. And since they are not necessarily flat, it becomes quite tricky of how to actually make them into a mesh. And like there are different ways. One way is to use Weaverbird's mesh from lines tool right here, which asks you to give it lines. These are polylines. It asks you for lines. Lines, polylines, lines, polylines. Not good. You want the polylines to be exploded into separate line segments. Of course, when you have so many polylines and you explode them, you create a data tree, right? All of them are pushed into a separate data tree, and then you connect those segments into lines. Okay, shits the bed immediately. Edge count is too low. Weaverbird was unable to produce a valid result because of this. Really? What the hell? Just give me a second. I am checking the smallest value in the list. So basically, well, that's 5 curves. What do you mean that's not enough? It's being stupid. Okay, so this is not working. That's fine. I will not then teach you the tool that is not working. Instead, I will show you a different way. So here we have our vertices after we explode them, right? And what I'm going to do is I will just average the vertices to get the middle point here. And I will merge, remember, the average of the coordinates of a point cloud is the middle point of said point cloud. I'll connect the vertices and the arithmetic mean, so the middle point of each of the hexagons. You can see I have those now. I'll connect those. I'll check. Yeah, it seems that the data tree is not freaking out. And then I'll use the Delaunay mesh, something like that. And it kind of does it quite well. For the plane, I could use plane fit tool to try and fit a plane through those points and then use that. This might help for the Delaunay mesh to create a mesh, right? And then I can, but it just literally just creates a triangulation again. So that kind of sucks. Unfortunate. Okay. But anyway, that's how you can close it off. And then you have a bunch of separate mesh entities. Insert. Oh, there's some invalid objects. That's fine. Bake invalid objects and stop asking. It's crashing. There we go. I get these in here. And these are like separate hexagons that are mesh hexagons. So that works. That works quite well. You would need to clean them up and so on, but combine and clean should do the trick. Okay, so that's how you create a mesh from it, right? A proper mesh paneling from it. Then in terms of creating Nurbs polysurface or anything like that, it's basically you would just need to draw a set of triangles from the middle point to each edge, right? And then join them up into separate B-reps. That's the same procedure. You could planarize it, but that would make it a little bit not nasty. I can show you planarization actually. I think that's pretty cool. We take all of this, what we have so far. Actually, we don't need the average or the merge. We need to fit the plane through the vertices though. So let me hide that. So we have our vertices, our points for each of the hexagons, and we fit a plane through them. And the planes are just kind of floating about, don't worry about it, but they are fitted, right? We have our planes. So what we do is then we take those vertices and we project point, that's on the geometry, no, project plane, project an object onto a plane, great. We take these vertices and we project them onto their average plane. We get the geometry, we create a polyline. We make sure that it's closed. Toggle yes. We have our polylines and then we do boundary, or actually surface, will that work? Yeah, just surface works. And now we have our surfaces here that are all flat. Of course, you have to sacrifice things to flatten things, right? Suddenly they don't match up. You know, the seams don't match up. But that's actually how it is in the real world as well. You know, you have your mounting seam or whatever it's called that eats up the error, you know, in this case, for planarization or for the curvature. So that's a simple planarizing algorithm. The real ones are a little bit trickier and a little bit smarter than that. So that's another one. Third one is my favorite, multipipe. Bam. That's it. Node size, let's increase it. What is it right now? 0.5, 2. Multipipe. Nice, isn't it? Once you get the sense of how you operate with Grasshopper, you can do pretty cool like 3D print. It looks like a weird, doesn't matter. You get, sorry, for some reason I lost track of what I was thinking. You get multiple directions of how we can manufacture things, how we can make things, and how we can design things, right? You just need to understand the tools and the principles of how those tools are used, and in which cases which tool should be used. And that comes with just time. Expertise comes with time, of course. Internalize data. Group all of that up. Change the color for white, for example. All good. That's Weaverbird in a nutshell. We are done with Weaverbird. Group that one up. Color, white as well. Okay, a few more left to show, and then we will be done. So next chapter. Next chapter. I still have two things to teach you. Anemone and then Bowerbird. Okay, let's begin with Anemone. It's a loop type of an add-on. A loop meaning something that repeats itself. Grasshopper by itself is very linear in how it works. There are, of course, loops coded into these nodes that are used from time to time, but most of the workflow is from left to right, and the data that flows from left to right never repeats or never goes back, never feeds back into the left, gets changed and goes back into the right again, right? So you never produce a loop. For stuff like growth, for example, stuff that is growing and building upon the previous iteration, for anything that is iterative, you need loops. So that is where Anemone comes in. I guess this seems like a nice spot for it. Basically, if I, where are you, Anemone? Hello, I just saw it. There it is. Basically, out of all of these nodes that Anemone has, you really kind of care about just two: loop start, loop end. And I'll explain what they do right now, actually. Loop start, loop end, right? And we look at these nodes just through their inputs and their outputs. We learn about these nodes from that. So first of all, what's the amount of repetitions that you want the loop to do? How many times do you want the data to kind of get looped, spin in between these two nodes? Well, I can just give it a number. For now, we can do an arbitrary number of 3 repetitions. A trigger, which is basically a button. You have a looped iterative system and you grow it or whatever, it does its thing, and then you want to do it again. You need to reset it. That's the button. The button triggers it. And lastly, what's the data that you want to loop? So I can just do cat. No, let's not do cat. Let's do a number. Number 5. And connect that as my data. Now I have 3 outputs from the loop start. This one just simply says, connect this to loop end. This one says, connect this to loop start. If I have remember, yep, there we go. So we just connect them. This is basically a feedback loop or feedback line for, data from here to be connected back into data here when the loop. I'm moving my mouse in a circular fashion, by the way. I'm not sure if it's being picked up by the recording. Basically when the data moves. Then here we have counters. A counter. This basically tells us at which repetition are we currently at. Panel. The repetition currently is null. It is what it is. It's null because the loop is not running, so since nothing is happening, it does not have anything to show you in the counter. Once the loop actually begins, then it will show you. And actually you can make the loop begin very easily. Data, we just can connect it straight to data, like so. Hit the restart button. And now you can see it really quickly jumped from 0 to 3. Keep an eye on the panel. 1, 2, 3, restart. 1, 2, 3, restart. See, the number jumps, right? It just counts up to 3. I can increase this to 500 so that you can see better, right? It's looping the information 500 times now. Back to 3. Oh, one of the important things is, even though I connect 3 here, since it already did the 460 loops, those stay. So if you want to stay with 3 loops, you need to reset it. Question, what kind of data is being looped? Well, number 5. So the way it works is basically 5 goes through here. Let's talk about repetition 0, right? First repetition. 5 goes through here, exits here. This is still 5. Connects to here. And that's it. Repetition 0 is done. Repetition 1 means 5 goes through here, connects to here, then loops back into loop start, goes through here, back to here, back to loop end, right? That's repetition 1. Repetition 2, same thing, only 2 times, and so on, right? You get the idea. How is this useful? Well, 5 plus 1. You know, first it's 5 at repetition 0, plus 1 is 6, goes to loop end, loops back. Then once it's looped back, now it's not 5 anymore, it's 6, goes to here, now it's 7, loops back. Now it's 7 here, goes to here, now it's 8. After addition, loops back, and so on, right? So, whoop, you can keep adding things to a number, for example. A very, very simple example, but an example nonetheless. So this is the most basic way of how you can construct a loop, you know, just add a number. Let's construct something a little bit more tricky. It's going to be a little bit of a harder definition, but I think we will manage. So let's do L system growth, meaning a branching type of a behavior. And for that, I kind of want to, let's do a 3-dimensional one, might as well, right? Why not? So let's draw ourselves in the top view, a Y shape. Something like this. Then let's make planar surface out of it. Make it into a planar surface and extrude that shape up. Give it thickness. Now, Control Shift, select the ends of the shape. All 3 of them. Holding Control Shift or Command Shift if you are a Mac user. Extract surface. We have successfully extracted 3 surfaces from this poly surface, right? Now we need to get those in. So first of all, brep, a single brep, set one brep for the shape, then surface, 3 surfaces that you have extracted. So right click, set multiple surfaces, and choose the one that is like a, you know, you have like 2 branches and 1 trunk. So the one that is the trunk should be the first one. And the branches are, that doesn't matter which one is the second one, but the trunk needs to be the first one that you select, and then you select the other 2. Enter. Now you have your surfaces and you have your brep. Great. Let's internalize data, delete these guys, and let's work with them. So for now, surfaces, ignore them. You don't need them. Let's make this into a lightweight shape. So for this brep, I'm just going to cap it. I'm going to make it solid, so cap holes. And I'm also going to mesh it, because meshes are much faster. And that's it. Now it's ready. Then for these surfaces that I have, I want these surfaces to be planes, because what we're going to do is we're going to take this shape by its origin point, which is here, this area right here, this surface right here, and we're going to move it and rotate it onto these two branches. In doing so, we will be creating two more aggregates, right? And so on. It's going to keep growing. So for that, we will use orient plane or orient object. I don't remember. It's under transform, morph, nope, transform, Euclidean, orient. This one right here, right? Asks us for geometry, which we would like to orient. That's going to be our mesh. Asks us for the source plane and the target plane. Okay, we have our three surfaces here. We need to make them into planes. Is planar. Test whether a surface is planar. This node right here gives you the planes of the surfaces. And then using list item, I can separate them into 1, 2, 3. Source is the first one. Target is the second one, and the third one. You will notice that it works, but the target clearly needs to be rotated or flipped, right? Because right now it's weird, right? So these planes, or actually the root could be flipped, and that will work. So let's just flip the root plane. To flip a plane, you can go to the vector tab, plane, and you can just find, whatever works, whatever you think might work. In our case, do you have this flip plane tool? I'm not sure if you do. I will assume that you do not have this flip plane tool because it has a different color, and I assume it's a part of some sort of a plugin. Even though it doesn't say anything here. No, I'll just do it manually. So for the root plane, I will just deconstruct plane, deconstruct the root plane, rotate the plane, or is there like rotate plane around an axis? No, it's only around the z-axis. Okay, so we use rotate 3D. Rotate 3D, that's fine. Rotate 3D asks us for what do we want to rotate. That's the plane. Asks us for the angle. We changed it, right click, change it to degrees. And we give it //180. Like that. Asks us for the center point as well as the axis. The axis that we can use is either X or Y. It doesn't really matter. I'm going to use X. And now this rotated geometry, I'm going to connect as my source. Like that. And now it works, right? For now it's two-dimensional, that's fine. We'll fix it a little bit later. But it is branching out. That's what we want. Well, now when we have this transformation, technically we could then take this geometry and I think we could apply, one second. Come on. I'm just going to try real quickly. Yeah, we could take this geometry that we got, the two branches that we've got here. And it remembers the transform, right? It remembers how the geometry was transformed. So we could technically keep doing it, keep using the same transformation, right? If the origin is here, then add two more to the branches, right? So it remembers this orientation transform. The only problem is that if I use the transform tool, which takes the geometry and uses the transform, then the first element that we've got will get the first transform that we used, and the second element that we got will get the second element that we used, right? Because it matches up the list with the geometry list with the transform list. So what you want is you want to separate out the geometries into separate data branches so that they get both of the transforms applied to them. So right click, graphed, and then voila, you've got it going, right? Problem. Now to continue doing it, I would need to graph this, transform, and keep doing the transform. Loops. This is where you start looping things. So we build it. We build the loop. Let's delete the transform for now. Loop start. Loop start. Loop end. Connect the two together. For now, repeat like 4 times. That's fine. Trigger button. Or actually, for now, repeat 0 times. We don't want it to be repeated. Trigger the button. Data to loop. Okay, what's the data? So I will just say that the data is our original mesh. And all of this thing that we've done here with the planes and so on is for us to, let's not graph it, for us to get these transforms, for us to get the transforms of the original mesh, right? So there's going to be a little bit of data manipulation as well. So for now, the data is actually our starting element. Bam, like that. It goes here. So it comes out as a, first as a mesh, then it's going to be a list of meshes. Then, 1 second, thinking. Then we use transform, of course. Then we just transform for this geometry, and we apply the transform that we got from here. Because the transform is just static thing. It figures out where the geometry is and is going to move it, offset it from the origin of that geometry, right? So we get the 2 branches and we can connect those to the data output here. Then we have a problem, and the problem is called, it does work. I'll kind of hide everything except the loop end, I guess. Right? The problem is that we had this mesh here, then it became, or we generated the 2 meshes from it, these 2 bad boys here, right? And then those got transferred into the loop end. Then go back in here to loop start. And during the next iteration, those 2 original elements will continue being transformed, right? And then loop end gets these guys. Well, if I were to graph them just like we did with the transforms, that's going to get us all of the branches, right? So now these 2 became these 4, and these 4 are fed into the loop end, which feeds into loop start. So in the next iteration, we only get these 8 and so on, right? So iteration 3, iteration 10, whatever, right? But we always only see the final result. We don't see the previous results saved. So that's an issue. That's an issue that we need to fix. Also, the data tree is just horrible. So there are 2 things that we need to fix. Let's fix the data tree first. Here, let me simplify because I can't see anything. Zero, 1. What if we just... Sorry for taking so long. Because here they are becoming separated, which kind of makes sense. But we don't really need them to be separated, so I can just flatten this, I think. And then they become 4. No need to simplify them. Then we just have a list of elements at iteration number 1. And then iteration number 3, still a list of elements. Okay, so we're getting rid of the data tree altogether. That works. So first thing that you need to do is flatten this. We still have a problem of it not saving any data. So how do we actually save data? Well, you need to do, and this is on purpose, by the way, you need to add one more thing that you will loop, and that is going to be your save state. Technically, you could also, like a shortcut for it, or actually, let me show you a shortcut because it's less, it's more intuitive. It's more intuitive. You already are probably just, the hell is going on with the transforms and so on. So I don't want to feed you even more intermediate level information. So for now, the way you save things is by, for the loop end, right clicking it and choosing record data. I think that's gonna work. Let's see. That records, right? Right click, record data. 1. Okay, that gives us 4, that's good. 2, that should give us 8. That gives us 8. Excellent. 3, and now it's recording. And we can grow our forest. That is flat, but that's fine, right? So let's make it pretty. Oh yeah, and it's nice because every generation is now saved as well. Great. Custom preview. Swatch. Really hard to see though. Arctic. Yeah, I guess you can kind of see it, right? So that's our L system. Now let's have fun with it, right? Here we rotated the origin by 180 degrees around, but that does not prevent us, and actually let's do less, only 3 iterations for this, right? Something like this. That does not prevent us from rotating the target planes, the branch planes. So for instance, for list item plus 1, for one of the target planes, I can also do the same thing, or actually for these, I can do a much simpler one. Rotate plane tool, plane, right click, degrees for the angle, 90 degrees, bam, connect that here. The plane just got rotated 90 degrees, and that gets connected to the target. Don't forget to connect the second one, because now the second one was disconnected. Don't forget to connect that one as well with the shift key to the target, reset. And now, why is there like a ground thing going on? 1 second, I'm just going to do this. It should be good enough. So now you can see that one of the branches is moving outwards. Oh yeah, and I should also, the original mesh should also be shown. So just using the shift key, I can connect it like that. Ignore the relay. If you double click on the line, just double click on any line, this relay gets created, and it's quite useful for just making sure the wires are going in the correct direction. For now, use it for that. And also you can connect from relay to multiple objects as well. Anyway, so that's our rotated plane. And now if I were to take this and I were to change the rotation of it, let's say 55 degrees, press play, my branch rotates, accordingly. And all of the branches actually keep rotating accordingly. So now if I were to increase this to like 5, you can see I get a completely different character for the tree. Cool, huh? And now we can play with this. So I can change this to 30 degrees. I assume 30 degrees will be kind of nice. Yeah. Quite organic. So 30 degrees is whatever. Let's do 5 degrees. Only 5 degrees at every generation. Yeah, that always produces a spiraling thing. Let's look at it. Let's hide the plane. That's a little bit in the way. Neat, huh? Welcome to the world of aggregation. So you can't really do that without loops. So that's an anemone for you, right? Right. I think we're done with anemone. We can move on to the next one. 1 second, I'm just gonna group it up and make it, I haven't used purple in a while, make it purple. And Control C, Control V, Anemone. Add to group. Okay. Next up, Bowerbird. Okay, so when it comes down to Bowerbird, it's purely used for manufacturing purposes, right? Well, at least that's how I use it. Bowerbird tab is located, of course, if you have installed it, it's located here. It does have some nice polyline Boolean operations where you can use Boolean difference between different polylines, which is nice. It has a nice text that can be laser cut in a nice way, so it has a nice font to it that's laser cuttable. But most importantly, it has this BB layer, right? Or BB sections, Bowerbird sections. There's also curve on surface, these all tools, but I will be ignoring those for now. I will be mostly focusing on the BB waffle, because if you know this, then you will understand how all other three of these work. So we will be using BB waffle. For this, I will just give you a very simple example. Let's go for mesh tools, mesh creation, and let's just make a donut here. Something like that. Actually, vertical edges 20, around faces 20. Yeah, that's nicer. Okay, so that's our mesh. The mesh that you input needs to be a closed mesh because it needs to calculate proper slices through it. Closed slices through it. I will internalize data and I will hide the mesh. Right? Or not hide, sorry. Delete the mesh. There we go. So now Bowerbird waffle structure asks you for the count, first of all. Honestly, if you just click on this little balloon here, it says what it needs to start producing, and it only needs the thickness. So that's the thickness of your material. Let's say we're cutting it out of 3mm plywood. I have no idea how big this is though. I mean how big the object itself is. I should probably... Okay, 1 second. Oh, what the hell did I do? No. Oh, no. Go back. Standard. I'll just distance it. From here to here, how long? 400mm. Yeah, that's fair enough. So 3mm thickness for the material. Then for the X count and Y count, I will give it like 20 slices each. Something like that. And that's it. It generates a series of sections through your material that can be laser cut. There is this plane tool which basically describes the direction of the sections. I tend to just keep it set to world XY as it is right now. If you're cutting something and you want the overlap, the way the sections go into each other to be... Oh, actually, I should probably first... You understand what a waffle structure is. You know, it's a series of cuts with that connect to each other, like so, right? So that's what it does. So if you want that to go deeper, then you create an offset here. You type in millimeters how much deeper. If you want to project the slices to be ready to be laser cut, you just toggle. True. And now they're laid out and ready to be cut. Then the minimal distance between projected slices is set to 1mm. Clearly, you know, along this direction it's not, but it's fine. It's fine. And of course, you would need to do some more Grasshopper shenanigans to actually give it some numbering and so on. So for the U slices, at least, I would suggest that you just measure the polygon center. And then around this, you would use a text tool. Location would be the center point. The text to display. Why are these grafted? Right click, flatten. You don't want them to be grafted. Right click, flatten. Then for the text itself, I would just say, give me the item index of these slices and add a U to them. How do you do that? Well, you can use item index tool, item index, both list and item go into item index, and then you get a counter basically, 0 is 0, 1 is 1, and so on. It's basically just counting which one is which, right? And giving you a list for that. And if I just connect that to text, and then and for the size, if I give it like, I don't know, like 4 millimeters, let's give it more. Then this becomes item 0, item 1, item 2, item 3, 4, 5, and so on, right? You get the idea. But then I need to also tell it that it's the U direction. So for these items, I will also create a letter U. Right? And then I will, let me check one thing if it's going to work or not. If these items are then grafted into separate data branches, will the letter U be attached to every item in the branch? So if I just text join, and I just merge these two, merge the U and the numbers, does it work? What do we get? Absolutely not even close. Okay, so we need to do a little bit of a harder thing. U needs to be, letter U needs to be repeated X amount of times, and X being amount of slices that we have, which is quite easy to do actually. Repeat data. Data to repeat is our letter U, and the length of repetition is the length of the list. List length. Nope, wrong one. List length. There we go. Connect slices U to the list length. The output is 32. I wanted to say what a coincidence, but I won't. Anyway. Oh yeah, because it's a donut, so you get like 2 of them, which is weird. Anyway, the list length is 32, that's fine. We connect that to the length, and now we get 32 U's in the list, right? And if I graphed that list as well, and I merge it, now we have 32 U's in separate data branches, 32 numbers in separate data branches, and they are merged into one data tree. And if we use text join, then what we get is probably something very nasty. Yeah, okay, it doesn't work, but we will make it work. So a reason for it not working is the addresses, as per usual. You can see, the numbers, the data tree of the numbers, which is this, only has 2 digits for the address. The data tree of the letters has 3 numbers. Right click, simplify, right click, simplify. Now it's the letters have 1 number for the address, the numbers have 1 number for the address. Text join works perfectly. We connect that to our text here. Oh yeah, and we flatten it because the location is unflattened, right? So we just flatten the output of text join, and now it says U0, U1, U2, U3, blah, 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 right? These kind of overlaps you fix manually. After you bake out your drawings into Rhino, you just move them, wherever you want to the correct position. Okay, so that's the BB text, right? To clean it up, because you want the text to be for the slices V as well, usually I just group this, Control-C, Control-V, make a copy. That's going to be nasty. Okay. Polyline connects to slices V. Oh yeah, those need to also be flattened. List length, this connects from there, but connects to slices V. What else? List and item from list item connects to slices V. And there we go. And now we have ourselves some numbering data. Oh yeah, and it's not U here, it's actually V. V5, V6, and so on, right? V2, right here. V2, U2. Honestly, that's it. I mean, there are different ways of how you can slice things. You can have radial slices instead of a waffle structure, but most of the time you honestly just do a waffle structure. That's it. Are we done? I think we're done. Wait. No, clearly something is wrong. Clearly I have forgotten. I should probably have forgotten like 50 different things. My brain is fried. Anyway, I guess we're done. I'll go drink some coffee and then I'll do an outro. And if I remember anything during my coffee drinking time, then I will say it in the outro. But see you in the outro. I remember one small thing that I also wanted to note. Or rather two small things. First one being data dams. So when you're doing some sort of a very, very heavy calculation or very heavy script, and there is clearly a portion of the script that is super heavy. For example, remember when we did the Cocoon thing, and this takes like a minute, right? So maybe, yeah, I will add it in here as to show you. A data dam is basically cat data dam. Nope. Data dam is an object that does not let data through, meaning that if you calculate something and the data dam is between point charge and Cocoon calculated something, right? And then you can change whatever you want on the left hand side of the definition without Cocoon recalculating all the time. It only recalculates when you push the play button. The way it works is here on the left hand side I have cat or some data, and imagine that this panel takes a long time to calculate, right? So okay, once I'm ready I press play and it calculates the output here. You know, in this case it just shows cat, but imagine, right? And then I go, well, I meant dog, right? And I'm kind of working on it, and you can see that this is still cat. It's not recalculating anything. And now the data dam, there's a play button here that appeared. Actually dog. That's what I meant, dog. And it's still cat. And once I really kind of nail down the parameters, then I press play, and then it transfers, and you know, the rest of the definition calculates. That's a very valuable, like DataDam is very valuable for that. Of course, if you zoom in, you can have multiple inputs and outputs for the DataDam, and one button that releases all of them or pushes all of them through. Very powerful tool for optimization. Another really nice tool that I could show, I guess with this, let me grab that Bowerbird script. Another great tool is this part and this part are very, very much the same, right? They are very, very similar in their logic. Kind of weird to just kind of keep repeating the same thing. So what you can do is you can, let me just delete the the bottom hand side. And for here, I can cluster it. So what I mean by that is, first of all, I need this to put all of the variables that I want to be able to change on the left-hand side. So I want to be able to change the text, and I'll just create a text component here as well, just in case, like that. And I want to be able to change which slices I use. So I will use that slices are curves. So curve component. And oh, by the way, a quick little trick for you. Control-Shift, disconnect, and drag this in to curve. Drags in all of the curves all together. Very useful. And then connect that to slices view. Okay, so curves will need to be, I will need to be able to change. And then this slider right here for the size of the text, that also, right? So I have 3 of these. Then the output are going to be curves, right? So I'm just going to create a curve component. Once this setup is done, then I can select all of the nodes in between, right? Including the text and the curve node. not including the output curve node, only these two. So do a mental print screen here. I click the scroll wheel and I choose at 12 o'clock, not group, but cluster. Bam. Makes a node for me out of these. So when you see a small definition, a small Grasshopper script, it might not be that small, right? And the output is curves. This cluster, I can right click and I can change its name to make text. Yeah, just make text, whatever, make text, right? And this cluster operates, there we go, there it is. And I can change the size of the text. I can change the text itself to zzz. It counts by itself the amount of slices that it needs. And it can be very easily copy pasted here. And it can use the V curves. If you want to adjust a cluster, you can just double click on it. And your nodes are here. It's like accessing a block or accessing a family in Revit, right? So you mess around with it. And once you're done, you just save and close or discard and close. So I'll just save and close. And that's that. That's how it works. So that is going to be clustering. That's going to be DataDams. Not dams, dams. Okay, now we're done. Now we're done. It's always good to drink some coffee and remember all of the things that you forgot to teach. So this is our final script that we have available. Time for an outro. All right, so after this training session or course, you should understand you should have enough foundations for your further Grasshopper development, right? So you should understand how Grasshopper operates, what kind of nodes there are available, not all of them, but some of them, enough of them, to now start figuring out what kind of a script would you like to create, would you like to use or make, right? One suggestion that I really, or two suggestions. First one being, right now for you, the fastest way of how you will learn Grasshopper is by simply making things. But do not make difficult things. Do not come up with, oh, now I will go and invent AI that draws buildings for me. I'm unique, like every other student that I have. So don't start thinking that or trying to do that, because you're going to hit a wall that you will not be able to climb. And a wall that you're not being able to climb does not really make you learn that well. It's much better if you just find something very simple, let's say floor skirting, right? Like the perimeter of the floor where you have the skirting on the wall, right? That's touching the floor. How do you generate that in the most elegant way in Grasshopper? Think about that, right? A window generator, right? Where you just have curves that you draw around an opening in the wall, and it generates window frames for you, right? Automatically. A roof slope calculator, or not necessarily roof slope, landscape slope calculator that colors, the landscape different surfaces according to how much they're tilting. Those kind of definitions are simple. Well, now for you, they should be simple enough so that you can do them while also learning things. Later, you build up the knowledge base and you start making harder and harder things, but right now, don't really try to overstrain yourselves, right? So that's one thing. Second thing is, and also I've shown you, I gave you all of the examples of what can you do for architects, but for product designers or for industrial designers or for engineers, it's kind of the same thing, for engineers, a thrust system. How do you create a simple, bridge thrust system, in a nice way, so that it's kind of assembling nicely and so on, and all you need to do is just input the top curve and the bottom curve, for instance. For product designers, how do you create a nice grip pattern, right? For a bike grip, a bike handlebar grip. Okay, I stop here. Second thing that I want to note is students that tend to learn Grasshopper get really, really excited about computational design and the premise of automation, or the allure of automation. I am going to automate everything that I do. Wait, maybe now I should be bigger. I will automate everything that I do from now on. I will figure out how to automate the staircase that I draw, how to automate the lamps that I make. Like, everything is going to be automated, and there are going to be no inputs from Rhino, because that's yucky and that's plebs. I'm a patrician. Those are plebs, right? Don't do that. It's a very, very dangerous mindset to have. I have seen so many students fail, not just students, honestly, many professionals fail who are trying to automate a task, and they spent months trying to automate some sort of a task that could have been done manually in a few days, right? Or they spend a few days automating a task that could have been done manually in a few hours. It scales, right? So always think about, does making a system that generates these things, insert a thing that you have in your head, does making a system that generates these things, that makes these things, is making a factory worth it? Does that make sense, right? Or does it make sense to only kind of do the thing in Rhino manually, and then maybe use Grasshopper only as additional stuff for optimization or finding like different variations of it, but the base of it is made in Rhino? I personally, the way I use Grasshopper is, I would say between 80 and 90% of the work that I do is done in Rhino. And then last 10% is done in Grasshopper in cases where I need to optimize something, like structure according to stresses, or architecture according to solar analysis, or whatever. So I use it for that. I use Grasshopper for form finding in some cases, where I need to grow a thing, or I need to simulate some draping fabric thing, or a balloon. Sure, I simulate with Grasshopper. And then last one is I automate boring stuff that I need to do constantly. For example, I mentioned window generator. I do that in Grasshopper. I don't model windows for every proposal that we do. I just, I have a script that does that. From time to time, I'm also generate some sort of a nice paneling system for a bedroom wall or whatever. But that's besides the point. The point is that you need to, and you will find it yourselves, where you need to use Grasshopper in. What's the use case, and where does it make sense? And that comes with time. For now, do simple things, learn more, keep learning, never stop. Takes around 3 years. After 3 years, you will be fluent. You will think through these systems, and you will be able to virtually design anything. Well, to a certain extent, of course, but like the only limitation will be your knowledge package rather than your skill set, right? I'll see ya. Peace. Oh yeah, and all the files are available to Patreon supporters.